All
Welcome
right.
back. It's day 2 of the 5th Applied Active Inference Symposium, November 13th, 2025. And the first session will be the future of active inference.jl with Peter, Jonathan, and Samuel. So, Peter, thank you to you.
Thanks, Daniel. All right.
Back. It's day 2. Please mute the YouTube. You to you.
Sorry, I have some sound problems here.
Thanks, Dan. One second.
Okay, here we go again. Can you see the screen? Otherwise, I'll just reshare it. And there we are. Thank you, Daniel. Sorry for the sound issues there. I had another tab open that I shouldn't have had. Also, thanks for organizing this symposium, which is incredible, the work that's been put into it, and worth being grateful for. So that's worth saying probably a lot of times during this symposium, again and again. Hi, everyone. So today, I and Sam and Jonathan will present on the ongoing and upcoming developments of ActiveInference.jl, which is a Julia software tool for running and applying active inference models to data or in simulation. And I'll start out with just a background and a conceptual thing, and then Jonathan will take over and Sam will take over, and they will go through code and give a demonstration of how to use the package in its newest version that's not yet released. And there's a link in the YouTube channel if someone wants to follow along the code to a GitHub repo, which can be cloned and used with this new experimental version of the package. Say again? Oh, okay. So I'll briefly just start with background. We're conceptualizing active inference as a kind of cognitive model. And what a cognitive model means is just that it's a formal model that produces behavior of some kind. So all of artificial intelligence, etc., can be conceptualized as cognitive models. And that's this broader framework where you have some agent and you have some environment, and the environment produces observations to the agent produces actions that affect the environment. And then the agent has a cognitive state, called the theta here, that changes over time. That could be its beliefs about the environment. And the agent has some cognitive parameters that could be, for example, learning rates or its priors that govern how its cognitive states change and govern how it produces actions. And in general, cognitive modeling, and therefore also active inference, has three kinds of uses that I know of. One is theoretical modeling. So that's when you run simulations to see what a given agent would do given different parameters. So there you know the theta here, and you simulate the environment and you want to see what happens. And active inference is full of these. So all the simulation work where you're going to show what happens if active inference fish swim together, etc., could be considered theoretical models. And much of the backbone of the field is built on this. Then there's applied cognitive modeling, and that's where instead of having the parameters, you have the observations and the actions. So you have the behavior, for example, because you recorded it from a human in an experiment, and you want to reconstruct the behavior that govern the parameters that govern the behavior. You want to find out what was the generative model, or what was the priors, or what was the learning rate of a given participant. That's what's used in computational psychiatry, but also much beyond that. And finally, one uses artificial intelligence, where again you have the parameters, but you don't simulate the environment. You have real environment, for example, a burning house or whatever. And then you want your artifact, your tool, to generate the right kinds of behavior. For example, a vacuum cleaner that's supposed to move in some ways and not other ways. You can use active inference in all three ways. Our lab specializes in applied cognitive modeling, so the second of these three. And last year, we focused quite a lot on how to use active inference for that. This year, we will not, because instead, we will focus on new structure of the package and how that makes it more flexible for the kinds of active inference models you can implement, whether you want to use them for theoretical or applied modeling or for artificial intelligence. And I just want to briefly mention that there are many other modeling frameworks than active inference. Frameworks where you optimize for expected value, frameworks where you run symbolic code operations, frameworks where you think the mind is kind of a dynamic system, connectionism, and later been renamed to deep learning, control theory, etc. And there's also a bigger family of Bayesian mind models where you think that the mind uses Bayesian inference. So we should have models that use Bayesian inference to describe the human mind. An active inference, which is the kind of variational Bayesian predictive processing model, is a type of Bayesian mind model that does three things. So it commits to specifically using variational Bayes, which is one way of approximating Bayesian inference. It usually uses message passing schemes to do this, and I'll get back to that. And notably, it does not only model perception, but also action as Bayesian inference. Just to place us in the larger field that we live in. And you can combine models with these other frameworks if you want as well. Active inference can be combined with them. So as we know, Bayesian inference, you have some data, some observations, and you have some parameters or some hidden states of the environment. You have a model M. And what you want to find, so the generative model is just how the data and the parameters usually co-occur. Could be just some joint probability distribution. It can be quite complex also. And as usual, what we want to find the parameters that are most likely given the data we get. And we have Bayes' theorem, and we all know this. Crucially, we can't calculate the bottom part because we have to the bottom here, to the bottom right. To calculate that, you have to integrate across all possible parameters. And if you have parameters that are continuous, you have so a full continuum for each parameter. And if you have many parameters, hidden states, that becomes impossible to do. That means that usually you approximate Bayesian inference instead. There are generally three methods. So one is sampling. And I've mentioned these because we can actually use them with active inference if we wanted to. We'll show that later. So it's worth mentioning that they exist. In sampling, you just pick values randomly, stochastically, with an algorithm that ensures that you're going to pick a value proportionate, an amount of times proportionate to how probable it is in the posterior. And there are many ways to try and do this. They can fail, they can succeed, but the main advantage is that they can get any shape of posterior in principle. The main disadvantage is that they take a long time. And they're not so mathematically beautiful because you don't use equations to get it analytically. Another one is simulation-based inference, where broadly you generate lots of behavior or lots of data with a model, and then you do something to get the posterior out of that. And so one of the classic and the most used method here is amortization, where you simulate data with your model and given different parameters, and you train a deep neural network to revert that process and then further parameters given the data. And finally, in variational inference, you minimize a free energy to get the posterior. And notably, this is not anything new, so it's been used in machine learning and in statistics for a long time. What's new in active inference is that it's used as a model of human cognition in general, and it's combined with action selection as well. Again, I'll just briefly remind us that here you have the true posterior, which we cannot calculate. We make up entirely arbitrary and approximate posterior Q. And then we can calculate the free energy, which is just the KL divergence between the approximate posterior and the generative model on the right. We have both of those, so we can calculate it. And then, of course, the magic is that if we find the approximate posterior with the lowest free energy, we also find the approximate posterior that's closest to the true posterior. And we see this, that you can rewrite the free energy into a divergence and an evidence term, where the divergence is the difference between the approximate and the true posterior. The evidence is the surprise. And notably, if you change only your posterior, that only affects the left term here, and that means that you can only reduce the divergence by reducing the by choosing the approximate posterior that minimizes the free energy. That's all very exciting. Hallelujah. Now, notably, that does not tell us how to actually find the approximate posterior with the lowest free energy. And there are different ways of doing this that are all variational based, and they're all free energy minimization based. And that's not necessarily an easy task, especially if the parameters of Q. So if you have if you have high dimensional posterior because you have many states you're doing inference over, it gets quite complex, and the way they relate to the free energy might not be very obvious either. So in general, I know of 3 ways that people find the posterior that has the lowest free energy. And one is just gradient descent. So you just wiggle your posterior around until you find the one with the lowest. And that requires calculating the gradient. So how the free energy changes when you change your approximate posterior. And if you have a complex model, that's usually difficult. But there are, as I'll see, methods to do that even for complex models. In some cases, when you're lucky, you can also just analytically, mathematically find in one equation the approximate posterior with the lowest free energy. That's very fast, that's very nice, but usually not easy. And finally, there are message passing methods, and those are the ones we know the best. So there you do an additional approximation, where you take your generative model, that's taken from the PAR et al. Paper. You take a generative model and you split it up. So for each of the components, each of the hidden states or parameters in your model, you split it up and you update your beliefs about them one at a time. Usually you do what's called a mean field approximation, where you assume that they're completely independent. But you can do this in different ways. So there's also these beta free energy, for example, approaches where you split them up into pairs instead of single. So you can retain that 2 parts of your posterior might correlate, but they're still assumed to be independent from the rest. Then you update them one at a time, and because you've split them up and because there's an approximation, that won't always work. So you keep doing that until they converge. That's called coordinate ascent variational inference using message passing. And that's the standard method in active inference currently. And it bears just showing briefly the update equations for each of the components if your generative model specifically is a discrete state transition POM-DP. You can have other generative models. But in that case, you combine 2 things. You combine a prediction, which is your previous belief about the state of the environment, plus or multiplied with the transition probabilities. So you take what you thought the world was before, you let it go through your model of how the world changes, and you now have your prediction. And then you add your evidence from the observation. So in almost all message passing schemes, you have this prediction plus evidence approach. And that's why we call it predictive processing. Because when you do message passing, you get something, often you get something that looks like prediction out of it. Okay, why spend all this time reminding us that there are what message passing is, but also that there are other alternatives? I'll get to that. Probabilistic program languages, are PPLs for short, exist. So that's a general technology where you have some system where you can specify all sorts of generative models. And then they for free give you methods for doing Bayesian inference and prediction. And there exists a bunch of these. So Stan is famous, Infer.net, for example, is also widely used. And they offer different kinds of methods. So Stan, for example, focuses on sampling, but can also do variational inference by gradient descent. Infer.net focuses specifically on message passing. And the whole point here is that you're not limited to one type of generative model. You can just write, depending on the PPL, any kind of generative model and get your updates from that without having to hand write all of the update equations. I spoke to some people from one PPL who said, why on earth would you hand write your update equations all the time, which we do. So in Julia, there are multiple PPLs. And they can all be used to do the Bayesian inference that ActiveInference.jl needs. The classic one is the ActiveInference.discrete.pymdp. That's the in-house that we develop. And that's the one that's identical to the one used in PyMDP and in the MATLAB code. And so that's a PPL in the sense that you can specify many kinds of generative models, but it's also limited because you can only specify discrete PymDPs. So where you get discrete observations, you think the world consists of discrete states that change in state transitions, and that you have discrete actions that affect those state transitions. We're also developing the HGF, which I won't spend much time except to say that that's very, very similar, except that the world is not made of discrete states with discrete state transitions, but Gaussian random walks. Here you also do message passing, and that's different update equations, but exactly the same logic, and they can also be combined, which we're working on. But there are also other more flexible PPLs. So RxInfer is one, which will do message passing specifically, as mentioned before. So that's very fast, but it's also an approximation of Bayesian inference. So that's why some people prefer others. You can also use Turing or Gen, which focus more on sampling or on gradient descent variational inference. So they are generally more flexible in the types of models you can write in them, but are generally also much slower. And they don't have as elegant mathematical single-step updates. That's why they're slower. And are not, they can be, but they don't have to be free energy based. And essentially what we want to show the rest of this presentation is that instead of being confined to have to use the discrete PymDP method, it's very nice as long as you are in a discrete environment and as long as you think your actions can only change state transitions and not other stuff, for example. It's very nice. But we want to allow ActiveInference.jl to use any of these options as backend, and therefore to allow people to use a wider range of generative models for a wider range of scenarios, but still doing full-on active inference. So the last part here, I will just briefly remind us of two different ways that active inference-like models can be implemented. One is, let's call it planning as inference, and that's the one where you just put in your possible actions or policies as random variables in your model, and you do standard Bayesian inference. Could be variational, could be anything, to find those actions. And so this is a screenshot from the tutorial on RxInfer, very, very nice tutorial, where they have a discrete PymDP, so you can see this A matrix and B matrix as we know it, and we have a previous state. And then they write out that generative model. So we have a current state, which depends on the previous state and the B matrix and a previous action. And we have our current observation, which depends on our current state and our A matrix. So this is specifying the same stuff we actually do in PymDP normally. And then we have a planning part where you go through each time step in your imagined future, and you predict forward what would happen. That's what happens here in this discrete decision from previous state down in the for loop, etc. And then finally, you have your goal prior or your preference prior in the end, where you, in addition to predicting what will happen, you also have a fixed distribution. Here it's only for the final state. So here the agent actually only has preferences for the very final state. You run this, you can use a sampler, variational inference, and you get out actions that are likely to make that goal prior come true, given your beliefs about the current state and your beliefs about A and B, etc. Here there's no parameter learning, but you can easily add that, etc. And it's just to show you could make many changes to this. It's very flexible, that's the whole point. What this method does not give us, though, is that it does not give us the information gain that is in the expected free energy in active inference. So we get the finding actions that give us our goal prior, but we don't get the information gain. And the RxInfer people, if anyone were at IY, are working at ways to extend this, so to have sneaky, clever ways of having priors about, for example, the ambiguity that will kind of get you the expected free energy anyways, while keeping everything local and using message passing. You could do this with other things too. I will contrast this to, I'll call it modular planning for now, but this is the standard way that active inference is implemented in activeinference.jl, PyMDP, and in MATLAB, where you really have three components to your model. You have your generative model, the agent's generative model of the environment. Then you have a perceptual part, where you take that generative model and you form beliefs about the environment and make predictions about the next time step in the environment. And this is the coordinate descent variational inference that I described before. This is the place where we minimize variation. And then we have a third part where you do your planning. And here in activeinference.jl, etc., you do, for example, a tree search where you go through sometimes you go through all possible combinations of actions in the future. Sometimes you do it in a more constrained way in order to find the set of actions that have the lowest expected free energy. And what's important here is that the planning part is separate from the perception part. So in cognitive modeling, that's often called a perceptual model and a response model, or an action model. And that makes the planning part not local. So it subsumes the perception part. So when you are, and especially if you're doing sophisticated inference, you're running your perceptual inference forward in time many times. So you do your variational inference many times into the future as you plan. The point here is that they are modular. So you can have one generative model, let's say a discrete POMDP with AB matrices. And then you can use many kinds of perceptual inference methods with that. So you could use Rx inverse message passing. You could use our house-made message passing. You could use Turing's sampler with the same generative model. And similarly, given a generative model and a perceptual process, you can also, with different generative models and or different perceptual processes, you can combine that with the same planning method. Because in the planning, you're just saying, if I do that, what will I think in the future? If you're doing sophisticated inference. And you could, that step, what will I think in the future? That can be done with sampling, with gradient descent-based variational inference, or with message passing. And it can also work with other kinds of generative models than the discrete POMDP. I'll note that standard for the planning is to do a tree search, and tree search explode if you go very far into the future. So they get computationally very costly. So you have to find ways to prune, etc. And there's a whole field of finding good ways to search through that large space of possible policies efficiently. But one other option is actually to make the planning stage itself an inference call. So that itself is a model, which we want to allow in the future. So you have a generative model inside of which there is Bayesian inference on a different generative model. You have a generative model which is your planning, and that contains the perceptual part. That, of course, requires us to nest PPLs, and that's something we're working on. But I just want to point out that that's usually what's called metacognition. So you have a model of your model. And sophisticated inference, that's exactly what you do. You have a model of your future beliefs, of your own future beliefs in the future. And I think that qualifies calling sophisticated inference metacognition. And given that it's specifically used for planning, one might call it metacognitive planning. It's just a different word for the same thing, but one that highlights what's happening. You're planning your own beliefs in the future. And to do this, you need to run inference within your inference. And therefore, you need to nest PPLs. And that's what we're building to allow. So the excitement here, the hope is that you can plug in, for example, RxInfer or Turing as a backend so that you can do other kinds of generative models and that we can allow for nesting them. And we're building the infrastructure for that. And in the following, we'll show you an example where we use two different inference methods with the same generative model and the same planning structure. Yeah. Okay, so that's it for me. That's just the background and just to make the conceptual point that we'll build on. From here, Jonathan will take over, but control the PowerPoint. And then in a second, we'll show you some code as well.
Super. Thanks, Peter. Yes, so before we actually show you some code, I'm just going to go through conceptually how the new structure is to be understood, and what kind of needs to be done if one wants to create a custom struct for either generative model, perceptual process, or action process. So Peter, if you would be so kind to go to the next slide. Yes, so here we basically see the same figure as we saw before, where we divide this active inference model up into three main parts, where we have a generative model, our beliefs about hidden states and how they transition over time and how they generate observations. We have the perceptual process, how do we then infer these hidden states? And then we have the action process, how we evaluate policies, and then marginalize them into actions. So the idea behind this is that sort of like Lego bricks, you can kind of interchange these parts, and so you can exchange, as Peter said, the perceptual process, and then it still works with the same generative model and the same action process. So it's kind of becomes modular. And if you go to the next slide, Peter. Yes, and then exactly what is required to make such an extension. And so I'll just briefly introduce how it's kind of conceptually implemented in the code in the activeinference.jl. And here we have, again, these three main parts where you can see the current implementations that we have is the discrete state space bounded piece for the generative model. We have the coordinated ascent variational inference for the perceptual process. And this is going to be the part that Sam, he's going to show how you can create a custom perceptual process, so you can use other methods to do the state inference. And then we have the action process, where our default is just a policy tree search with evaluation over the expected free energies. Yes, you can go to the next one. Yes, and so here we can kind of see the overall structure of the package, and it's basically based on an active inference core module, which kind of contains the template for the structs and functions. So the functions and structs in the active inference core module are not really used, but they are made so that they can be extended into other modules. So as you can see here, the module that we have currently implemented is the discrete POM-BP. And I'll show you briefly, shortly in the code, how you can actually extend these generative models and the functions like the perception, planning, and this kind of stuff into the discrete POM-BP, so that you can actually create an active inference loop with the discrete POM-BP generative model and with the perceptual process and action process that we have. And then you can extend this by creating other modules as well, which we will in the future, and which is going to be where you would add the custom structs. And if you go to the next one again. Yes. And so basically here, the idea is that we use abstract types, where we're saying that for a generative model, if you want to add another generative model, then you have to make it a subtype of this abstract generative model. And basically what we allow for here is that in the generative model, you can also specify what sort of action or observation or state. If you go to the next one, Peter. Just briefly just showing here that you can, for example, have a POM-BP that can be both where you have continuous action or continuous observations and states, but you can also have a POM-BP where you have discrete actions and discrete states. And this way we can use this for the different functions the word is escaping me, where we have different functions that multiple dispatch on the different types, even though it's the same, could be the same POM-BP with the given the different sort of actions or observations. We can do multiple dispatches, and this way it becomes very modular and very easy to work around. If you go to the next one. Yes, and the same one here goes for the perceptual process. If you want to add a perceptual process, then you have to make it a subtype of the abstract perceptual process. And if you go to the next one, and the same for the action process. And so if we combine all of these, if you go to the next one again, then we have our active inference model, which is composed of these three parts: the generative model, the perceptual process, and the action process. And here you can see like it's interchangeable in the sense that you can just, and this is what Sam is also going to show you, that you can have the same generative model and the same action process, but then you switch out the perceptual process with a custom perceptual process instead of the Kavi perceptual process that we're implementing currently. And just a brief note on the action models here. The action models is a sister package to the active inference package, which is for doing model fitting to cognitive models, of which active inference here is one of those models that we're planning to implement and to do model fitting on, or allow for model fitting. If you go to the next one. Yes, and so there are 4 main functions that one needs to be aware of if one wants to implement a custom struct. This is the perception, the planning, selection, and stored beliefs. And this is, I'm going to show the active inference loop, and you'll see why one has to at least either modify or make sure that these 4 functions will work with whatever customizable struct that you are planning on implementing. So if you go to the next one, here we showcase also like the core module, how you're supposed to extend from the core module into whatever module you're working on. So for example, here, when we're working in the discrete POMDP module, we're extending from the active inference core module, which has the perception function. The perception function from the active inference core module is never going to be used because it only contains or dispatches on abstract types, where it will then give you an error and say you need to create a concrete type. And this is what you need to do. You need to create concrete types for each of these parts. And then, as you can see here in the PMDP module, you then extend it from the active inference, where you then have the active inference model, where each the generative model, the Kavi, which is the perceptual process, and action process, are all prefixed with this discrete POMDP. And then you have the multiple dispatch on the specific type of active inference model that you have. And if you go to the next one, and you can see this is the same for the planning. So the perception one creates the posterior state, the planning creates the posterior policies. And again, we have the multiple dispatch on the discrete POMDP, and it's an extension from the active inference core module. If you go to the next, we have the selection, which basically marginalizes over the actions, so it actually creates the act or the distribution over actions that we then sample from when we want a concrete action. And if you go to the next one again. Yes, and this is store belief. This is just like a utility function where we then take all the output from the previous 3 functions, and then we put it into the active inference model for use in the next time step. But basically, all of these 4 functions need to work with whatever customizable or custom struct that you're making, and needs to be kept in mind. And yes, and the next one. Yes, and here you can see this is kind of like the high level active inference loop that is in the active inference core module, and basically because we have the multiple dispatch, this loop can work with any active inference model as long as each of the functions perception, planning, selection, and store beliefs have a multiple dispatch on the active inference model type and subtypes that you're using. And Sam will show how this is the case. And then the next one is just briefly showcasing here that in the perception action loop, you have the active inference functions, in active inference function, which gives you probability over actions. And this probability, you can then use the Julia distributions package to then sample an action that you then give to an environment, gives you an observation. And in this sense, you have the perception action loop. So it should be high level. It looks, it should be very clean. And now Sam, he will show you how this is implemented with a walkthrough of a notebook. And in the next slide, you will see a link to a GitHub page where you can clone it and should be able to follow along. All right, I give it over to you, Sam.
The link is also in the YouTube chat. And I'll keep an eye on the chat meanwhile in case anyone has questions. And finally, do note, I'll just add this, do note that creating your own alternative version of active inference models is maybe a bit of a power user thing that it's good to be able to do, but we also retain the old interface where you can do classic active inference.jl models. Okay, sorry for the
No worries. Okay, so let me just share my screen quickly. Okay. Can you at least confirm that you can see it well?
Yes,
Super.
we can see it.
Thank you. Awesome. Okay, so there's this little notebook that we've prepared for you to show you basically like the current implementation. We'll be using the development branch because it has not been published yet as a new version. But basically, I don't know how familiar people are with Julia, but in the beginning, there are some formalities that we need to go through, like activate the current environment. And we have prepared some utility functions just for plotting and the environment. And then we bring our dependencies to the scope. And so in this example, we'll be using a simple multi-armed bandit task, which you can imagine as a slot machine with 3 arms. And each arm is associated with either a reward or loss with some probability. And so in this example, we'll initialize the environment with arm 1 being the best. So we would have the probability of 0.9 of receiving a reward. And the second best would be arm 2, and then arm 3 would be the worst with only 0.1 probability of receiving a reward, otherwise loss. And after each 25th trial, these probabilistic contingencies will switch. And we will make our active inference agent initially uninformed about what are the reward probabilities. And we'll let it play the game for 100 trials, and we'll let it learn these contingencies while trying to stick to the preferred outcomes, which are the rewards in this case. This is just a visual of how it looks over 100 trials and the probabilistic switches between arms after each 25th trial. So now we are ready to set up our generative model. We'll just start with specifying some structural components. So we have three hidden states where each hidden state corresponds to an arm in the bandit. We have 2 observations, so reward or loss. And controls, those are actions. So we have 3 actions. Each action basically just means pull arm 1, pull arm 2, pull arm 3. And then we're going to use a policy length of 1, so we're only planning 1 move ahead when making decisions. And we're just going to pass all this to create matrix templates, and we're going to tell it to populate it with uniform probability distributions. And this is going to give us the A, B, C, and D objects. And now we can populate it. So for the observation likelihood, this will give us a 2 times 3 matrix where each column corresponds to a hidden state, or an arm in this case, and rows correspond to observations. And we're just going to leave it populated with uniform probability distributions because we want the agent to learn these probabilistic contingencies. And we specify a transition likelihood. So we have 3 B matrices. In this case, each B matrix corresponds to one of the 3 actions. So we're basically telling the agent that when it's in the arm 2, for example, and it pulls the arm 1, it's most likely to actually end up in that state. And we make it a bit stochastic here just to introduce some uncertainty to it. Right, so we have our B objects created, we've created above. And we just take like each slice and populate it with our matrices, each corresponding to one of the 3 actions. And the 2 last things we need to specify are the C vector and the D vector. So the C vector is the preference. In this case, just a 2-element vector, where the first element encodes the preference over rewards, and the second one, the preference over losses. So here we're basically just saying that prefer rewards over losses. And for the prior initial hidden states, we're going to tell it that it's going to start in the arm 1, or at the arm 1. All right, so now we have the generative model, and we can move on to the definition of the active inference model. And so I'm going to start with the default implementation. So sort of the out-of-the-box way of specifying the generative model, or the active inference model, rather. So we are still keeping the old way of doing that, where we're just passing the individual components of the generative model to the AI model constructor. And then we don't really need to care about anything else. We're basically ready to use our model. However, we would like to focus on here is the new modular extensible approach. And so here we need to specify the individual parts of the active inference model separately. So here we'll create the generative model object by passing the individual generative model components to it. And this is the default discrete POM2P generative model. Then we'll need to specify a perceptual process. And as Peter and Jonathan mentioned, in our package, the perceptual process would consist of two main parts, which is the algorithm to perform inference about hidden states. So here in the beginning, I'll just use coordinate ascent variational inference from the discrete POM2P module, which is implemented by default. And then we need an algorithm to do learning. So which basically means to update the parameters of the generative model itself. And here by default, we are just using the Dirichlet categorical model. And we're going to learn the A matrix. We're going to pass some parameters to it, like the concentration parameter or the forgetting rate, because there's some volatility in our environment to make the agent a little more flexible. And then lastly, we specify our action process. So the action process here is really just a planning algorithm used to evaluate our policies. And this can be standard inference. This can be sophisticated inference, tree-based methods. By default, in the discrete POM2P module here, we're using standard inference without graph. And in this case, we're telling it to use the policy length of 1, which we have defined above. And then we're going to use all the three terms to calculate the expected free energy. So states information gain, the parameter information gain, and the utility term. And once we have all these three parts ready, we can just collect them all three and give it to the AIF model constructor. And this will generate the model object for us. And then we'll just need a couple of more things. We'll need to initialize our environment. So here we have some pre-made environment, and we're going to tell it that the best arm has the reward probability of 0.9. And then we're going to switch the contingencies after every 25th trial and some random seed. And then before we actually simulate, we're just going to set our initial observation, our initial action, and we're going to simulate for 100 trials. And here I just have some empty vector so we can store the beliefs of an agent during simulation later for plotting. Now we get to the action perception loop. So the main function here is the active inference function, which takes the model, observation, and action as arguments, and it outputs the probability distribution or actions. Now, because it's a categorical probability distribution, we sample an action from it, and then we pass it on to the environment, which gives us the observation for the next time step. And it goes on like this for 100 trials. And then I'm also saving the first row of the A matrix and the posterior overstates later for plotting here. Right? And so how does that look then in practice? So in this plot, the first part, the green dots are the reward observations, and the red dots are the loss observations. In the second one, we have the first row of the A matrix, right? So this corresponds to the probability of receiving a reward for each of the three arms as the agent was learning it throughout the course of 100 trials. And then posterior overstates, which is a little noisy here because we introduced some stochasticity to it in the transition model. So this was the default out-of-the-box way to do it. And now I'm going to show you how to create a custom perceptual process. So here we're just going to import two things from the package that we'll need, and that's the type of abstract perceptual process and the learn A type from discrete POM2P module. And here we're going to create, we're just going to call it a container, really, because this mutable struct, like it's like its task is really just to store all the important variables that we'll need for a perceptual process. And importantly, we're going to make it a subtype of abstract perceptual process so that our functions or the functions of our package can accept it. Right, so we have our inference function, which we are going to define later. We have our A-learning algorithm, and then it stores, of course, posterior overstates, posterior overstates from a previous time step, empirical prior, current observation, expected states, expected observations, and then the B-learning and D-learning we're just going to leave empty here, right? And then we're just going to create a constructor function, and we have our container for the custom perceptual process. So now what we need to do is we need to create the inference function that the agent is going to use to form beliefs about hidden states. And here, this is a very simple generative model. It's just a single state factor, which means that we can do exact Bayesian inference based on these two equations, which is basically just a softmax of the log prior plus log likelihood. And on the first time step, we just switch the prior with the d vector, and otherwise we're going to use the empirical prior, which is calculated based on the transition likelihoods, right? And to put this all together, I'm just going to load the softmax function from the log x functions library. And we have our exact inference function here. So it takes just 3 arguments, which is the AIF model itself, the prior, and the observation at the time step. I'm going to take out the A matrix from the generative model. I'm going to get the index of the observation. And again, we're going to calculate the log likelihood and the log prior plus some small value for numerical stability and bring it all together in a softmax function to get our approximate posterior. But actually, in this case, it's an exact posterior. Yeah, and now we have this ready, and we can bring it all together again to the AIF model constructor. So in this case, again, our generative model is just discrete POM-P with the components which we have defined above. But now to the perceptual process, we are going to use our custom perceptual process, where to the inference function, we pass our exact inference function defined here. And we're going to tell it to use learning as implemented by discrete POM-P module. And the same goes for the action process. With the policy length of 1, and we're going to use parameter information gain. And the rest is basically exactly the same configuration. Give it the first observation, first action, similar for 100 trials, some empty vectors to store the beliefs of an agent. And this one is basically exactly the same, but the only difference being here that we are using an exact Bayesian inference to form posterior overstates. And this is how it looks. So far, we've talked about using our default implementation and then using custom, basically handwritten perceptual process. And now I want to move on to how to use PPLs as a part of an active inference model. So in this case, I'm going to use Turing, but this can also be an argsinfer or gen.jl, and can be really any Bayesian algorithm. Can be sampling. It can be a variational method. It could be other optimization methods. But in this case, we're going to use sampling via Turing. So the only thing we need to do is to again create our Turing model, which is going to be our perceptual process function. And again, it takes 3 arguments. So our AIF model, prior, and the observation per time step. We're going to take out the A model from the generative model, get the index of the observation. We're going to tell the function that our likelihood is defined in our A matrix. And then we create a Turing model. And in the Turing model, we're just going to tell it that our hidden states are coming from our categorical distribution defined in our prior. And then our observation are coming from categorical distribution defined in our likelihood, dependent on hidden states. And once we have the Turing model ready, we can sample from it. So in this case, I'm using a Metropolis-Hastings algorithm, and I'm taking 5,000 samples from the posterior. This will give us our chain, and then I can just average over samples for each category, because it's a categorical distribution, to get to our posterior states, and just return it as a vector. And that's it. And then basically the rest is exactly the same. We bring it all together in the AIF model constructor, define our generative model, and then in the perceptual process, for the inference function, we set our Turing perception function defined here. And then, yeah, the rest is basically the same. So we define our observation, action, number of trials, define some empty vectors to store beliefs, and the action perception with Turing is exactly the same. And when we plot the result, we see that we have made 3 different models with different perceptual processes now. Yeah, and that's the end of the notebook. If you guys have anything else to say, or if there are any questions, we're ready for it. And otherwise, thank you.
Thanks, Sam. Amazing. Amazing. You know, so the maybe the last thing to say to round this off is just that we're trying to make this very flexible. So especially maybe some power users may be interested in adding new ways, custom ways, such as you use an exact inference method or a sampler, etc. But also make some of these methods ourselves so that they can kind of just be, you can say, I want to use Turing instead. And specifically when we use the discrete POMDP as generative model, we will rarely need to use a sampler because the message passing usually works quite well. But in some other generative models, we might need maybe not a sampler, but maybe a gradient descent variational inference, where we can use the full flexibility of these PPLs. And another, the exact inference method you showed, Sam, should be faster than the standard message passing method, probably, because it doesn't have to converge over time and that kind of stuff. So yes, so we're trying to make it both flexible and able to rely on the huge power of some of these PPLs like RX and FER, but at the same time keep an easy-to-use interface on the top, like Sam showed in the beginning. Okay, we have a few minutes left. If there are questions, I guess, Daniel, you can decide how to spend those few minutes. And I've been responding a little bit in the chat, so I don't think any of the questions there.
Yes.
Up to you, Daniel.
Okay, yeah, if anyone has a question, they can write in the live chat. Because your defense is tomorrow, Peter, even if it's kind of related, what is the title of your dissertation? What are you defending tomorrow?
Tomorrow I'm defending, it's called Modeling the Mind, and it's on cognitive modeling quite broadly. So we're including this software that we're showing here, but also the HGF software and the action model software. And there, so the whole point of action models is that when you do applied cognitive modeling and you fit models to behavioral data, and you can either fit them one at a time to each participant separately, but there are much better ways to do that. So you can fit them in these hierarchical models where you assume that there's something common between people. You can even fit them at the same time as you relate them to, for example, questionnaire data. If you want to find out how people's learning rates relate to their schizophrenia, for example, fit that in one model. Or even have one model where you fit neural data and behavioral data together, if you're interested in how your active inference model relates to brain data, etc. And so we're making software to do all of that. And since that's compatible with the active inference stuff we just showed you, and that all comes for free is the hope. And then the thesis otherwise is on, so we use that to model hallucination, where you model hallucinations as false inferences. And in our results, they seem to come from having too strong priors and relative to the observation. And the theory is that that's because of sensory noise, so noise in the sensory system, which makes you learn over time that the observations are noisy, and then you trust your priors more. Your priors, your predictions, same thing. And we do that with people in different modalities and find out that that's modality specific. So just because you hallucinate, you hear stuff that's not there. That will correlate with having too strong priors in the experiment, but it won't have effect on visual necessarily. Yeah, that kind of stuff. And then I think last year, now that you ask, Daniel, it's very pleasant, but also I'll talk for ages. So I'll just run off by saying that the last thing we also used is to not reconstruct the generative model of a person's underlying a person's behavior, but instead using it to reconstruct the generative model underlying a collective's behavior. So you simulate a bunch of little agents, you treat them as one agent together, you fit a model to it like this. Some of the stuff that we can do now that Sam has shown us this, we can use model comparison to test, do people use message passing, or do they use gradient descent variational inference, or might they even use a sampler? And it might be good theoretical reasons to not think that they use a sampler. There are people out there who do think people use samplers, but just allows us to specify these active inference models more flexibly so that they can do, so that we can properly compare the full space of what they can be like. Yeah, is that enough response to that question, Daniel?
Cool.
Thanks.
And then what will be next for the package, or how do you see it going forward after this year?
So, and you can jump in, Sam and Jonathan, but I think one thing is we want to make this interface as easy as possible and have a flexible. So that's what we've been talking about today, but make some good tutorials for that. So in case you want a continuous state space, continuous action, discrete observation model for your whatever purpose you have, that you can do that and still use full active inference stack on top of it. Apart from that, one piece of excitement, I think, is exactly this nested inference stuff, where so theory of mind is an example of nested inference, where I have a model of Sam's model of me, and that means that inside my model, when I do Bayesian inference, I have to do Bayesian inference, so it gets nested. And the same with metacognition, so I'll have a model of my own model of stuff, and the same with sophisticated inference also, actually. And we've tested this a little bit, and it looks like you can literally put RxInfer inside Turing without any problems. And so we haven't tested that much, but if we can get that to work, then we'll get basically theory of mind, full explicit theory of mind, full explicit metacognition, flexible, sophisticated inference for free. And that's quite exciting. But like I said, that's still on the, let's say, vision space. And then there are other things like we want inductive inference in there, one of these faster. Like we want these bells and whistles to be faster. Like we want these bells and whistles to be there, but also be easy to add more of them. And that's kind of the hope with the package. And then we can rely on something like RxInfer for the heavy, fancy, message passing and all sorts of weird data models. Yeah, lots of excitement. And if someone ends up being interested in collaborating or contributing, that kind of stuff, they should just get in touch. We'd be very happy to do this. One point of making it as modular as we can is to make it easy to contribute also. So someone might like to add this specific generative model, and if they do, we'll add it to the package so that other people can just press, I want that model, and then it's there, for example. Yeah.
Awesome.
I hope that makes sense.
Okay. Thank you, fellows.
Thank you. Thanks for everyone who's listening.
Thank you.
Bye.
All right, we're back with RxInfer in action with Bart van Erp and Fraser as special guest. So thank you, Bart. Go for it.
Thanks a lot, Daniel. Before I start, quick shout out to Peter for the great talk before this. Also, Peter, best of luck tomorrow with your defense. Exciting times, so yeah, go for it, I would say. Today's talk is RxInfer in action. So my name is Bart. I'm one of the core developers of RxInfer, also one of the co-founders of Lazy Dynamics. So we have been basically at the cradle of RxInfer, and I thought this symposium would be an excellent moment to share our latest developments with the rest of the crowd, get some new inputs, new opinions. If there are questions, feel free to hop in, right? I think want to make it very interactive as possible. So feel free to interrupt when needed. So what are we going to talk about today? So for the people who've never heard about RxInfer, I want to give a short intro on what RxInfer actually is. I'm aware that most of you already are familiar with this technology, but just to get everyone on the same line, I want to make sure that everyone has the same background information there. And from that moment on, I actually want to start building applications. Want to show some cool applications that we've been building over the past couple of months. Starting with an actual drone demo. We'll also introduce gears.jl, a new package that we've recently released. We'll talk about our RxInfer MCP server that we've been releasing. And at the end, we'll have a sneak peek in stuff that we're currently working on. But I won't tell you what it is. So if you stay like long enough for the end of the video, I think you'll get some cool insights. So let's get started. So what is RxInfer? So in short, RxInfer is an open source library for scalable probabilistic programming. So what does this mean? Probabilistic programming, scalable. Well, it has to do with active inference, Bayesian inference. We can do planning, control. Some people call it explainable AI or better AI. But I think at the core of it is uncertainty quantification. We want to create programs, algorithms, which are probabilistic in nature, which do not only propagate just values, but also uncertainty margins, allowing for more robust programming or more robust algorithms. And what RxInfer does very well is that it scales very well over dimensionality. So compared to Turing, for example, which is mostly sampling based, RxInfer has a different technology under the hood, which allows it to scale to problems with a lot more variables and a lot more dimensions. So how do we do this? So at the core of RxInfer, we have vector graphs. For the people unacquainted with vector graphs, basically these are probabilistic graphical models, which allow us to describe some model of the outside world. This can be the dynamics of a robot. This can be some assumed dynamics of a signal that we're observing, for example, financial data. And what we can do is we can create these probabilistic or generative models and decompose them into smaller terms. Each term is here, for example, one of these nodes in this graph. And the edges that connect these nodes, these represent variables. So you can think, for example, that there is a state that progresses over time, and each time it goes through some particular transition f. And that's kind of, these equations govern the process on how the state evolves over time. And we also make observations. So the observations we plug in as these solid black nodes. Basically, once we observe something, this information will be captured in the hidden state and will be used for, let's say, making predictions or doing state inference. The benefit of using these vector graphs is that they are explainable and white box. So we can basically dive into the underlying model and figure out, okay, what's actually causing the behavior that we're observing. And because these models are mostly generated by domain experts, by domain knowledge, we can actually figure out, okay, which piece of this graph, which small box is causing specific behavior to happen. And it's just like Lego, right? So you can tie together all kinds of different nodes with all kinds of different edges, which makes it very modular. But all the computations are performed locally. So although you create a huge model, the computations will be on a very local and small scale compared to when you would do, let's say, all the operations at once in the entire large model. So what we've developed in order to create these vector graphs in code is our domain-specific language called GraphBPL. And it looks roughly like this. So we introduce in Julia the add model macro, and this add model macro allows us to specify our model. So here we have, for example, a Gaussian state space model where we have observations that we call Y. In this model, we specify two parameters, theta and tau, and we say each of these parameters will get a gamma prior with rate and shape of 1. The hidden state, we say, okay, it's going to be from some submodel, and that submodel we can also define in the model macro. So by doing so, we can kind of create this hierarchy of models, basically nested submodels. And this submodel is one, let's say, time step in our Gaussian state space model. You can see here that the next state, so S is short for state, will be distributed as a normal whose mean is some function over our previous state, and the precision is governed by theta. And our observations can then be extracted from this state through some function g, where we model the observation noise with the precision parameter tau. So this is one slice, let's say. And these function f and g, these can be very different depending on the application. Can be drone dynamics, can be robotics, modeling financial data. So it can be very diverse. And we can basically use this submodel macro to expand our Gaussian state space model, basically putting the different slices after one another. And this basically allows us to specify this vector graph in a couple of lines, quite similar to the domain-specific language that, let's say, Turing.dl also uses, but a lot more easier to use than some of its counterparts, right? There are also a lot of programming languages out there which do not offer such a nice DSL. So I think this is very nice, very great to interact with the tool. Makes it easier also for outsiders to actually get started building these models. Without having, so just some story. So all the way at the start, we had to manually create these nodes and then also manually these edges, and we had to connect everything together. Yeah, that turned out to be very, very annoying. So this is basically its evolved version. And in general, we're all very happy that this language actually supports these features. But basically, they allow us to specify a probabilistic model in which we want to do the computations, right? The way that we do the computations is through variational inference. So what variational inference basically does, although most of you are already familiar with this, is basically it allows us to approximate complex, often multimodal and skewed distributions with a distribution that is from the exponential family. So basically, instead of doing all these exact computations, which are very difficult, intractable, what we do instead is we say, okay, we're gonna come up, let's say, okay, we're gonna approximate our result with, let's say, a normal distribution. And with this normal distribution, we'll try to find the normal distribution whose mean and variance best approximate the distribution that we actually, the actual true distribution, let's say, that we can obtain through sampling, but sampling is oftentimes too slow. So here we use variational inference, basically turning this Bayesian inference problem into an optimization problem, right? So what we minimize is this variation of the energy functional, where we try to find, okay, what Q minimizes this specific functional for our probabilistic model P. And P is the one that we previously defined in the vector graph. This looks all complex, but in the end, everything is automated in RxInfer. So there's no need to worry about these equations. What's nice about variational inference is that scales very well, and it's very efficient in comparison to sampling-based methods, because we oftentimes have closed form expressions, and we leverage those to basically prevent having to sample thousands and thousands of times. And this free energy functional inherently has a trade-off between complexity and accuracy. That's also well known in the active inference community. So basically, you can think of it as kind of an optimal approach for actually finding these posterior values that you're interested in. Also for this, we have some domain-specific language. Basically, we allow with RxInfer to give like an easy interface on changing these approximate distributions Q. So these distributions Q are the ones that we set. Let's say the simple normal with which we want to approximate a more complex distribution. And we can also apply different constraints on that. So here in the bottom, we say, okay, we want our posterior over S, over our hidden state, to be normally distributed, just using very common Julia syntax. And we can also say that, well, these different states, as we have them evolving over time, modeling them all as one big Gaussian is not always desirable, because that grows, of course, pretty badly with the amount of states. So what we can say is we can say, okay, we want to actually impose a mean field constraint. So for each individual state in our model, we create a different Q, which is not correlated with the following one. So by that, we basically can reduce the computational complexity of this simplifying distribution in order to make inference run even faster. Then putting it all together. So we have vector graphs, we have variational inference. What can we do with it? Well, RxInfer, as I hinted already on earlier, it doesn't do sampling. It's quite a bit faster than sampling-based methods. Instead, what we do is message passing. Basically, what that means is we use the local structure of this vector graph, so these nodes which are very sparsely connected to each other, and we perform these computations that basically optimize the free energy. We optimize this free energy on a local scale. So each node basically tries to optimize or minimize this free energy on a local scale, and that allows it to do computations, approximations of our posterior distributions. So basically what we can do is we can compute these posterior distributions Q by passing information between the individual nodes. And this information flow, that's what we refer to as messages. Oftentimes, or almost always, these messages are distributions themselves. So basically what we are doing is we're propagating distributions across the vector graph, across the network. What's special about the way that how RxInfer works on this is that it's fully reactive. So if there is no data coming in, also nothing will happen, because it's lazy by nature. That's also one of the reasons why our company is called Lazy Dynamics. So we only really do stuff when it actually is very much necessary. And that's also the same principle that underlies RxInfer. So if there is no data coming in, the model doesn't have any information or need to update its beliefs, right? So it then also doesn't do any computations. So this is quite adaptive, robust. So also when there are sensor failures, we can adapt to that. Once, let's say, one of the parts of the model breaks down, like in real world, then we can stop passing messages there. And because it's reactive, it also allows us to do every computation in parallel, such that they don't wait for each other, but they can just pass the messages along each other in parallel, making it possibly also scalable to new chips that become available on the market. So RxInfer is, for the ones who haven't seen it, it's open source. Like the core of RxInfer is fully there. On GitHub, you can basically find all the information to get you started. We have a bunch of examples to get started with, ranging from small drones flying around to discrete state space models, POM-DPs, Gaussian processes. And basically, we're expanding this list of examples. Like every couple months, there will be a few new ones. I also recently saw that we have new examples on icing models, doing some very cool projection techniques for approximating posterior distributions. So there is basically a lot of information in the example. So if you want to get started, I would definitely recommend to check it. Just go to rxinfer.com, and there you'll find the link to the examples. We also have discussions there where we are very much open for feedback. If you have questions, want to know something, just post it there and one of us will definitely reply to you. Also, if you want to see like enhancements to the tool, we very much encourage you to post like your opinion, your wishes there. We are currently looking into the possibility of creating some kind of logging interface where we actually are requesting people to also share their ideas, thoughts, such that we can basically have a look inside RxInfer in real time to see what messages are being passed and also how the computations actually happen. So basically just running it in real time, debugging it in real time. So that's what we are currently requesting ideas for. So if you have them, please share. And of course, we also have issues. I wish we didn't have the issues page, but unfortunately we do. If you want to help us out, very much welcome to contribute. I think we have quite some nice ones or easy accessible ones out there. If you want to help out, also just send me a message or just post something on GitHub and we'll definitely get back to you. So good. That's RxInfer. So RxInfer, everyone now has kind of an idea of what's happening under the hood. And what we wanted to show to you is some drone demos that we've been developing over the past couple of months. So what RxInfer basically allows is to create high fidelity control and planning systems. I think, a bit more than a year ago, we also presented a nice presentation here on the Active Inference Institute, where we build a drone with RxInfer, a very simple two-dimensional drone, just to show everyone, okay, how can we actually put these complex dynamics of this drone into our RxInfer interface, and how can we run it? So I would definitely, if you're interested in this kind of topic into robotics, definitely recommend to check this out, because I think it's a very nice video. I won't play it here because I think it's rather long, but I think it's definitely nice for people to get started. What we've been doing for the past couple of months, basically, we've been expanding upon this. So in this model stream, we worked on a two-dimensional drone example with simplified dynamics, and we went all overboard, basically. We're now in 3 dimensions, 6 degrees of freedom, and we're modeling the drones up to a very, very precise. So we're modeling the dynamics in a very, very precise manner. We're incorporating drag coefficients of the body, not only translational, but also rotational. We are modeling the electrodynamics of the rotors. So basically all the dynamics that we could find of a drone are now basically inside a model. And I wanted to basically share with you the results that we obtained. So we started off with dynamic obstacle avoidance. So we have this drone here in simulation, because it's a bit difficult to have these bulbs. With this modeling, turn the dynamics, the electrodynamics, everything there. And the idea of this drone is that it needs to follow this trajectory. So there is this blue kind of arrow, indicating the target or the goal that the drone should follow. And this target moves along this trajectory, right? What's very cool about this particular demo is that all these spheres that you see flying around, the drone doesn't know about them. So while actually flying, it doesn't know about them. Only when the drone gets into a certain proximity, it sees them. And then, of course, it needs to adapt, right? So this drone, it will fly around. Once it sees one of these spheres, and if it's in its way of actually following this line, it will adapt to that actual obstacle, and also plan around it. So it will try to reroute, find another path that at least follows the goal as good as possible in order to still kind of keep track of this target. So I think this is something that we are very happy with the results. Putting it onto hardware is, of course, a completely different challenge. But I think for first experimentation, I think we're very far away, or we made quite some progress. And this is for the simple one drone dynamic ride. What we've also been experimenting with is actually having multiple drones. Just to give you an idea, so the drones, they start around z is equal to 0, so on this ground plane. And basically we task all of these drones, like 20 in total, to fly upwards. And also in this scenario, there are these spheres which are like in the way of the actual reaching the target within a straight line, right? So each drone basically operates independently from each other, and they also don't know where the other drones are. So it follows a similar algorithm as on the left, but in this case, it actually, once it sees the sphere, it again tries to reroute around it, but it also isn't aware of the other drones. So at some point, some drones also encounter other drones, and here they'll also adjust their trajectory in order to not collide. So you can see that, for example, here with the pink one, so you can see that the pink actually dodges the green one by making a sharp turn. So just to show everyone what's possible with RxInfer, right? So RxInfer, I think the examples already are getting more advanced as we speak, but we can achieve like very cool applications. Drones, I think, is already one that's very complicated. So we're very happy that we actually managed to get these running also in real time. What we've also been working on is a new package. So RxInfer is fully reactive, and what we intend RxInfer to work with is basically sensors which operate on different frequencies. We can have, for example, a camera which runs at like 30 or 60 hertz. Whereas if we have a microphone, it has a sampling rate of 48 kilohertz. IMUs are also somewhere 300, 400 hertz. So we were thinking, okay, this is nice. RxInfer is kind of targeted to solve these particular problems. But how are we actually modeling them in Julia? Because it's not so easy to create a particular simulation environment where every sensor runs asynchronously in parallel. So that's quite complex. That's why we introduced gears.jl. So basically what gears.jl allows you is it enables fine-grained scheduling for simulations and real-time systems. So just to give an idea, what does it mean? It basically allows to create simulations of systems where we have different observations coming from them at different sampling rates. So basically in the situations where we want to be in full control of when we observe what, or when our environment gives us a new observation to process, that's something that gears.jl has been trying to solve basically. So just to give you an idea of how it looks, once you import gears in Julia, you can create a variety of tasks. So in this case, we can say, for example, every 200 milliseconds, we want to print the following line, that the task is executed at some time step. And then we run our scheduler. So we can say run the scheduler for 1 second. So for the next 1 second, update. So basically the task that we previously defined, these will actually be executed during this 1 second duration. And we can make this more complex, right? So for the drone example, we can say process IMU data every 5 milliseconds. Do this or perform the replanning or update the control sequence every 200 milliseconds or 100 milliseconds. If processing audio, maybe process the audio every 10 milliseconds. So we have very fine-grained control of the actual data sources coming in, and we can run this. What's very nice about this is that the clock that basically runs these tasks and basically does the scheduling, we can also replace the machine clock that gets regularly used with some virtual clock. So basically, if you want to do simulations spanning over, let's say, years, like if you're modeling, I don't know, the planets in their orbits, and you want to do something with that, we can actually also add in a virtual clock, which allows us to speed up or slow down the simulations. If we want to model specific behavior on like a nanosecond scale, not sure what kind of applications go there, but I guess there are, then we can also slow down the virtual clock, such that we're not modeling on a second level, as our hardware normally would, but on a nanosecond level. And we have a variety of schedulers to basically create our own simulation environments. We have the intervals that we just saw, so every 200 milliseconds, do this. We also have something called an ASAP scheduler, so as soon as possible. So as soon as something happens, perform a task. So this can be used for chaining tasks together, and also event-based. So when, let's say, an observation comes in, I always make the example where we have, for example, an API request coming from another service. That's also something that you can work. And what's nice is that these tasks, they can run asynchronously. So when you have a lot of different tasks at the same time, it actually figures that out, and you can run them asynchronously in parallel. So that's just a short introduction of Gears.dl. So basically they allow us to create these complex simulation environments. And in general, I think it allows us to experiment with the core capabilities of RxInfer better than just native Julia code would. So that was one release that we did a couple of weeks ago. Something that's a bit more recent and that they're also very excited about is RxMCP. So what we heard from the community is that although we have this nice domain-specific language, using RxInfer is not always the easiest, right? So it's still challenging. So what we wanted to do with this project is basically what we wanted to give the capabilities of RxInfer a broader audience. We wanted to have a lot more people interact with the tool without knowing that they're actually interacting with the tool. So instead of downloading Julia, which is another programming language, people are a bit hesitant if they want to go away from Python. We just wanted to make it easier for people to interact, even like senior executives, right? People who don't do any programming anymore, right? Those are the people that we also want to target. But what these people often require is some form of analysis, some form of basically like processing data with uncertainty, because that's where it shines. So with RxMCP, I think it has never been easier to use some parts of RxInfer. So what it allows is basically grounding LLMs with RxInfer using our model context protocol, where MCP for short. So effectively, you can just chat with RxInfer. So if you have a data set that needs processing, you can throw it in, ask it a question, and it will basically figure it out. So together with the strength of LLMs, basically converting numbers into some natural language and using, let's say, the uncertainty processing of RxInfer, you can actually get the best of both worlds. We already have integrations now with Mistral, with Claude, Cursor, OpenAI. You can find the docs as well, so we added in the QR code in case you're interested. At the moment, it's free to use, so we definitely recommend everyone out to basically to check it, use it, give us feedback, and our goal is to improve it further along. To give you an idea of how it works, RxMCP, it starts with some context. So you can think of, I have this huge data set, I'm going to throw it in this in one of my favorite LLMs, and I'm going to ask it to do something. So I'm going to query it. Well, RxInfer will then basically learn from the data that you have supplied. So it will try to figure out what are underlying relationships between variables. And it will also predict. So it will give you suggestions, actually. It will compute the posterior distributions. And those posterior distributions will then hand back over to your favorite LLM, which can interpret these distributions. So basically, it can give you then recommendations based on the query that you provided and the uncertainty-aware results that RxInfer provided. So basically, you get the best words, you get best of both worlds. You get to use the analysis capabilities of RxInfer, whereas you have your LLM basically explain what it returned and why this is important. Just making the audience of RxInfer a lot broader. So I think we're very happy. We're also getting quite positive results here. A lot of positive feedback of people who otherwise would have never been able to use our tool. And we're very excited to also engage them. I also wanted to show a short video. It's 2 minutes of our CEO, Albert. He basically recorded a video demonstrating the capabilities of RxInfer. What he did, because it's a relative fast video, he basically illustrates the use of RxMCP using a problem that a lot of companies, startups, are actually struggling with. So suppose you have 1,000 contacts and you want to figure out, okay, which contact should I actually pursue in order to make a deal? Which one is the most, or which one has the highest return of investment? What is the most, basically finding the person will get you the best deal in the shortest amount of time. He created a data file for this, and I think I'll just play it and be silent for 2 minutes. Can let Albert do the talking for now.
Every startup has the same nightmare. You are making critical decisions with limited data. Which feature to build, what price to charge, who handles which lead. And every wrong decision burns runway. Using just LLMs for this, well, those don't reason about cause and effect. You need grounded mathematical decision making that actually learns from outcomes. Let's watch how RxInfer solved this. I'll use lead assignment as an example, but this works for any decision: pricing, feature, content, anything. Well, here's a bit of an irony. I'm using LLM to interface with RxInfer, and even it struggled to parse with the unstructured data at first, but well, RxInfer underneath, pure Bayesian reasoning. So we've got 5 new leads, RxInfer assigns them, Jay gets small companies, Lisa gets enterprise, and these aren't guesses, they are mathematically optimal given uncertainty. Now, let's imagine we've got the results back after following these predictions. Well, Jake's sure bets lost 20K, Lisa enterprise deal made 40K. And here's the really cool thing about RxInfer. So I feed back these results and instantly RxInfer updates its beliefs. And turns out that Jake isn't the right for founder-led deals. Try Lisa instead. And this isn't just pattern matching or token prediction. It's a causal reasoning about actions and rewards. Next founder lead arrives, model says Lisa, not Jake. It learned the causal relationship from 5 outcomes. Obviously, you won't be typing these comments yourself. Your agents will call RxInfer MCP directly. And this works for many things, right? For pricing, you can learn price elasticity per segment. For features, you can discover what drives conversion. And for content, you can understand the engagement causally. You need decisions that are grounded in reality, not just text generation. RxInfer is open source. RxInfer MCP is free with integration docs available now. We invite you to start learning from every decision today. Check out placedynamics.com.
So wonderful. So that was a very short demo. I was thinking about doing a live demo, but you always know live demos never work. So that's how I wanted to let Albert show you. So what he also mentioned, and I think this is very, very interesting, is basically RxInfer also relearns. So it learns based on new data. And once new observations come in, it will actually adjust its beliefs. This is very different from the LLM chatbots that you have with a lot of companies. I was trying to book a flight over the weekend actually, and I ended up chatting with this chatbot, of which you of course know it's an LLM. And despite saying, well, just connect me through, it was quite stubborn. So I think this is also one of the places where our Extrovert could shine, basically update the beliefs of these LLM as data comes in, instead of just appending it to the context, right? So that's currently what's happening. And then a sneak peek, the latest developments. So this is very, very rough, and I want to kind of warn you that functionality is not fully there yet. But we are still wanted to show it because we're very enthusiastic about it. And we wanted to get as much feedback on this topic as possible before we actually further develop it. I think it's very cool, so let's just get started. So what we have been thinking about is doing uncertainty quantification in LLMs. So there is this huge problem of hallucinations, figuring out whether LLMs can actually work. And on the other hand, we have RxInfer, which is fully probabilistic. It can quantify uncertainty very well. So why not marry both? So we've been thinking about, can we actually combine LLMs with RxInfer, not in the same way that we do with MCP. So with MCP, we say, okay, LLMs, go use RxInfer. But basically what we are thinking about is using RxInfer to upgrade these LLMs. Basically that it doesn't just provide you with an answer, right? But that it also provides you with an uncertainty margin. Instead of saying, you're right, you're fully right, definitely. Good question. This is the answer. Maybe it would be better if the LLMs become a bit more nuanced, so that it says, I think this is right with, let's say, 50% confidence. So we've been exploring ideas basically for RxInfer to integrate with these systems. We have a very short here on the right, visual representation of how something could look like. So next time you're using ChatGPT, it asks, do you want to use RxInfer for, let's say, verifying Q&A accuracy? You can say, yeah, I would like that. I would want to know how certain the LLM actually is. You confirm, and you can just then say, okay, RxInfer will run on the backend, and it will figure out how certain the LLM actually is in its answers. So this is still very much a work in progress, but we wanted to get some initial feedback, whether you think this is interesting, what else would you like to see? If you have great ideas, let us know. And if you want to test it out, you're very much welcome to, and we highly appreciate it. If you want to know how to get started, otherwise just send me a message or reach out somewhere, and then we'll definitely give you, let's say, the API keys to get started. So with that, I would actually like to conclude, and I'm open to start a discussion. Very interested in what you guys all have to say.
Thank you, Bart. Fraser, if you'd like, maybe say hello and check in, and then feel free to start with any questions that you have.
Yeah, hi, thanks, Bart. Hopefully you can hear me okay. So I'm Fraser. I'm a PhD student at the University of Glasgow. I also do a little bit of open source work with the Bias Lab. Very honored to do that. Excellent stuff. I'm particularly interested in this, gears framework for scheduling tasks and so on. I'm trying to think about how to build certain active inference agents using RxInfer that interface with a world that might itself be reactive and so on, which, as you say, is quite difficult right now. I'm just thinking, gears is excellent. in some sense, it is just a way to schedule tasks. We had our environments before as a way to kind of talk about actual entities that are out there. I'm thinking, well, if potentially that could integrate with gears, that'd be a really powerful way to afford those kinds of environments and things that we could then place agents in to kind of give them a home. Is there anything you can talk to there about potential cross-pollination between RX environments and gears, or if there's maybe some other replacement package for environments? I'm not sure. I'd be interested in your thoughts there.
No, that's excellent. That's a very good remark. I don't think we have actually done any integration there ourselves. For the very simple reason that, yeah, we didn't get around to it yet. But I definitely foresee that like joining both would, yeah, we have this package already out there. So I think we can leverage both and use both strengths to make it even easier to create these reactive environments. And I think Gears allows us to not only make them reactive, right, but to also do the actual, let's say, precise scheduling when it's needed. So, for example, for sensor data, it's, yeah, in a sense, it's reactive, of course, but at the same time, it just samples every so many hertz. So I think RX environments, like these are like fully reactive, and that's very nice. On the other hand, sometimes you do want to have this control over when actually sensor data comes in. And I think that's where this Gears is really shining.
Yeah, the combination of both seems like it'd be a real winning strategy. So, yeah, okay, maybe I'll think about that myself, what I can do there. So
excellent suggestion, thanks.
I'll read a question from live chat and have some related questions. So Bert Berkers wrote, could RX MCP also work for POMDP models in the future?
Yes, definitely. So these POMDP models, right? In general, I think I'm not even sure whether we maybe already are supporting them. So just to give you a very quick overview of what RxInfer MCP actually is. So we have RxInfer, which is our software tool. We have RxInfer server that basically runs RxInfer in the cloud for some selected models. And then we have RxInfer MCP, which connects the LLM to this server. So for RxInfer server, which is also open source, it's possible to implement these POMDP models by themselves. I'm not entirely sure whether they then also directly become, let's say, connected to the LLM. So that's something I would need to check. But at least you can send easy, simple API connections or requests to RxInfer server and have the POMDPs running there. Although I do foresee definitely that connecting this with MCP as well could be very valuable when you have indeed some data that you just want to process. You don't want to write all these data loading functions and you just want to throw it in there. It's Friday afternoon, you want to finish this up before you leave to home, let's say. I think that would be excellent. In the end, the idea is for MCP to start supporting as many models as possible, as relevant. But at the moment, yeah, we're prioritizing the ones that we have kind of open requests for the very simple reason that we can put everything there, but we're trying to be a bit smart about our time and our time investment there.
Yeah, on the RxMCP. So you said that it learns from the query and the data. So what structure of graphical models does it start with or sweep over? And do you get back at model blocks which you can separately execute? I mean, is it doing an end-to-end RxInfer metaprogramming and then reporting outcomes? Or what is really happening underneath the call?
Excellent question. So what I mentioned, so we have this RxInfer server where we have some models running. For the demo that we just showed, we have a particular model in RxInfer, the one that we created that already. but it's still very generic. So basically everything that has to do with contextual decisions, where you have some data, you want to make a decision, that's where basically MCP currently is targeted for or tailored for. So the MCP is basically a connection going from your LLM to RxInfer server in the cloud. It does return quite a bit. I'm not sure whether it returns the full model macro. I don't think so, to be honest. Although this is something that if there is a real need to return this model macro, sure, that can be made possible. But what it's actually returning is all the posterior inference. So basically all the raw results that you could normally obtain with RxInfer itself, that gets sent back to LLM, and then the LLM is used to interpret these results.
Okay, makes sense. So the MCP facilitates within the repertoire of what the server has access to.
Exactly.
Yeah. Okay, I'll ask a question from the chat, and Bart, and then Fraser, you could add any thoughts too. Okay, Rob wrote, broad question. Where is uncertainty valuable in applications? I see its benefits in fundamental science, but I struggle to find effective examples in applications.
There are plenty. But I like the question quite a lot because we've been looking through this uncertainty lens already for a couple of years, right? So we can see where it's valuable in almost any application. But yeah, I can definitely give some examples here. In robotics, we have sensors, for example, and these sensors, they make particular observations, but these sensors can also be noisy. So if you move, you say, the arm of a robot, or you drive a cheap robotic kind of around, it will give you some measurement of where its next location is, but at the same time, well, the sensor readings aren't that accurate. Maybe it slips a bit, let's say, on the ground. So yeah, there will be some deviation in the end result. So that's one place where you could use this uncertainty, basically these margins. And you can use that to correct also for it at some point. Another one, which is, I think, very, very important, is everything concerning financials, like financial markets. I wish financial markets were deterministic, because if that was the case, we could just pour in money into one stock that we are aware that goes upward. But in reality, no one knows which stock goes up, unless you have inside information, of course. But for most, it's just a guessing game, a game where you try to figure out, okay, which stocks are going up, which stocks are going down. And oftentimes what the term that they use in these financial markets is called volatility. So basically it describes how volatile the stock is. So if you have a stock that's very non-volatile, its price will be very smooth over time, whereas the volatile stock will go all over the place. And that's something that you want to be aware of. You want to be aware of this volatility, or actually uncertainty about how this stock is progressing over time. If you're going to use that investment fund for, let's say, throwing in your pension money, that's something you probably want to have stocks which are more secure, have a less limited volatility. Whereas if you're like private equity, that kind of stuff, you want to take a bit more risk. So that's also an application area where you can think of, and I think that makes uncertainty shine.
Yeah, like having the point estimate without the variability measure of some kind is just half the picture. Because if there's something that's, you expect it to be 1% improvement, if it's an engineering process or financial, but you don't know if that is a 1% plus or minus 10 or 1% plus or minus 0.001%, then you wouldn't really know if that was actionable. And then you would need to go another level. Okay, 1% plus or minus 2, but how confident am I about 2? And then that kind of dovetails back into why we want to have these composable, flexible Bayesian models where we can interpret those different uncertainty structures.
Yeah, exactly. And for some occasions, propagating no uncertainty itself is also fine, right? So for some applications, you don't need it. However, what you see is for like very critical applications, it's actually good to have some kind of quantification of margins, uncertainty. So yeah, definitely.
Fraser, want to add anything?
Yeah, just maybe for a really speculative question now. I attended IY earlier in the year, the International Workshop on Active Inference, and Laser Dynamics and RX Infer, the team from the buy side you guys presented. There was some work on kind of recasting the EFE for planning in active implementations as the VFE, so that we just have one free energy one free energy functional that we're minimizing in order to do active inference. And that'd be quite nice because we have two sort of canonically floating around in the active inference world, and maybe that's a little bit annoying. Obviously, this is the fruit of ongoing work at the Bias Lab, so it's all very speculative. But is there anything you can comment on with respect to the way in which this might eventually land in RX Infer? Is there a way in which you can see how the Beth free energy might change in consequence, or a way in which users might be able to plug in, they want this kind of unified functional thing for the message passing to happen here, as opposed to not? Is there anything you can say about that at all? It's a very, very broad question, sorry.
No, it's an excellent question. Now, indeed, so our colleague Wouter Knight, he has been working on this particular topic, trying to frame the expected free energy as variational free energy minimization procedure by doing some smart tricks basically on this vector graph and in this message passing procedure. I think so the expected free energy has, compared to, let's say, variational free energy, some added perks, right? So you get, I think one of the most important ones is that you get this information seeking behavior. At least that's one of the perks that variational free energy by itself might not always have. So for some applications, this is very critical. It could help you a lot in actually trying to learn, let's say, the parameters of your robot or the parameters of the financial markets. Although for those you don't really have an influence yourself. So I think robotics would be a better example. But indeed, it's ongoing work. How we see it is we see it kind of as a different flavor to what we're already doing. It's also still very much under development, but I think, yeah, progress is very good. The results are very encouraging. So I can't wait basically for the results that will be popping up in half a year or a year from now. And once they do this, there's definitely incentive to integrate this in RX Infer as well, right? So it's not that we are thinking, oh, this is better free energy or variational free energy. It's kind of the holy grail. For some applications, expected free energy is just more interesting, more nicer. It gives you properties that other targets wouldn't give you, let's say. So that's definitely something that once this research kind of matures a bit, once we have a cleaner idea of how we can integrate it in an improved manner on a larger scale, then that's definitely something that we are planning to work on. That's also why we're, of course, performing this research, because, yeah, we want to keep on improving the toolbox, not only for, let's say academia, but also for actual industry problems.
Excellent, cool.
What are you most looking forward to, or what do you think will be able to bring it into most people's hands in the coming year?
Ooh, that's a tough one. I think we're making very, very nice progress with MCP. So as I mentioned, the motivation behind MCP was really to get RX Infer into the hands of as many users as possible. I think providing it through an LLM, basically just having something that everyone can access, even if you don't have like university background or you don't know mathematics, you can still use it you'll also understand that these uncertainty margins can be useful for specific cases. I think getting it out in as many hands as possible is what we're really striving for. And that's why this MCP, in our opinion, it's a very first step, right? It's kind of a first step in getting RxInfer out in the public. And we are currently looking into applications where we might benefit most. So basically maybe specific application areas of this MCP where we can put it in as many hands as possible. So not just selecting these leads as we did, as Albert showed in the demo, but maybe there are also other application areas out there which are very much relevant, but that we currently are overlooking. So yeah, if there are any suggestions regarding this, feel free to reach out because we would be happy to extend the functionality of RxMP with these kind of new applications. So that's basically one thing that we're looking very much out for. Another thing is what I already mentioned is, so we're kind of not reviving, but we always had this idea of creating this amazing debug tool for RxInfer. So from a developer point of view, I'm very excited about that as well. So what you can do now is basically it's very hard to debug because everything's reactive. We do have some very deep developer options to actually figure out what's causing what. But we wanted to make that process simpler. So there is now an open discussion on GitHub, basically requesting ideas, enhancements from everyone on how we can make this debugging or interface experience better for a lot more users, a lot more developers. And from the lazy dynamic side, we have already been experimenting with some of the tools, let's say. We haven't integrated them with RxInfer, but we have starting to get a better understanding of what's happening, what would be a nice interface, what could help. I don't think we want to go, let's say, all overboard and let's create our own full UI ourselves. So probably we want to leverage on existing technologies. But yeah, we're very much open for ideas, suggestions. If you think, oh, this would be cool, let us know. Definitely. Any feedback there is recommended or appreciated.
Thank you. And it's been really fun with Fraser facilitating the RxInfer learning group and a lot of cross-pollination. And I think compared to where we were a year ago, you've really highlighted this bi-directional relationship with the LLMs. On one hand, there's the MCP direction, which is the LLM using RxInfer as tool use. And then on the other direction, there's kind of two flavors. There's the uncertainty quantification of LLM outputs. So you can just ask the LLM repeatedly, what's the GPS coordinate of this location, and then use those estimates to get a posterior distribution. And then the next step there is to choose the prompt to the LLM with active inference to make informed sampling of those latent spaces. And so that is kind of building out that two-lane highway, going both ways between larger models and how they're increasing in power, and then all of the interpretability and benefits that graphical models and factor graphs bring. So that's very fruitful, and it's a very pluralistic, exciting time for building those kinds of hybrid models.
Definitely. I think, like from our perspective, LLMs are very good with natural language, and we are all using them. Even people who claim that they're not using them, we're all using them, right? Drafting emails from time to time, and well, you know, right? But it does provide an easy interface, and I think that makes it very accessible for people to use it. So definitely would be personally, I'm in favor of leveraging on the, let's say, the basically using both tools. I think combining them and using best of both. I think that's what we really want to strive for.
I'll just ask one final short question from the chat. Jay Graves wrote, several projects, including AI Knowledge Sidekick, are scanning selected information sources to create personal curated summaries. Could RxMCP be applied to monitor such a feed?
Excellent question. Yeah, I just need to think a bit on how it is. So in general, probabilistic models are very much useful for doing personalization. Just to give some context, it's a bit out of scope from the actual problem described here. But what we were designing RxInfer for from the very beginning is actually high-speed applications, and most specifically hearing aids, because that was the one the company basically was funding RxInfer from the start. What we were using RxInfer for, one of the parts, right? Not only the signal processing, but also for incorporating user feedback. So when you do an interaction with a human being, and I'm speaking for myself, right? So I had this was struggling with this chatbot for booking a flight over the weekend. If I say, well, this answer is not listed, I want the model to kind of learn from this. Don't want to keep interacting. I don't want to say it 20 times, like connect me through, connect me through. After 2 times, I think it should be very clear that I want to be connected through. What we used RxInfer for personalization in hearing aids was basically figuring out, okay, what specific sound sources do we want to listen to? So normally these algorithms, hearing aids or earbuds, they have this active noise cancellation, so they cancel everything. Or they have this hear-through mode where you basically hear everything again. What if you only want to, let's say, listen to one specific sound? When you're maybe in a car, you just want to listen to sirens. Well, not that you want sirens to be all over the place, but once like an ambulance drives by, you want to listen to that, and you don't want to listen to the car engine. At least that doesn't make sense. When you're out in the park, for example, maybe you want to listen to the birds, and you don't want to listen to the people who walk past you and have these conversations. So train station is also an excellent example, right? When you want to listen to basically all the announcements, but you want to zone out the actual sound of the trains. So figuring out what a human person would want to listen to is something that requires user feedback. And it's also very much context dependent, because if I'm at the bar, I want to have a different experience than when I'm working in the office. So we have used RxInfer, just very long detour. But what I wanted to say is we have been using RxInfer for preference learning, where we have interactions with human beings and creating these personalized reports. I think that definitely falls within the scope of what RxInfer can achieve. That having said that, I'm not sure whether it's directly applicable to, or that, sorry, that is not applicable, that RxMCP directly supports this personalized summary generation. I think that was the original problem, right? So, but definitely there are possibilities there. Definitely we can bridge this gap. It's not that we aren't able to do it. It's mostly we just didn't do it yet. I think that's yeah, that's the current status of it.
Any final thoughts, Fraser?
I could stay for hours and hold Bart hostage for a long time, but no, I mean, I think that was really excellent. I enjoyed everything. I'm looking forward to everything that we can do together. There's a lot of leads there and what you presented. So yeah, thank you very much.
Yep. Thank you to you and the team and for engaging with the open source. And next year we'll have another spiral of learning with RxInfer. So thank you guys. Bye.
Definitely. Thanks a lot.
Thanks.
All right. Next is going to be a 2-minute and 30-second video by Michael Lennon. Here it goes.
Hello, I'm Michael Lennon, a member of the Active Inference Scientific Advisory Board, and delighted to be presenting today on reflections on some economic myths that I've been encountering around AI over the last year. And however, as I prepared this slide deck, I noticed that there was one point in particular that I wanted to draw attention to first. So this is a rapid clip about a specific opportunity that I wanted to put in front of the community and speak about. And if there's more time, then to go into the formal, fuller presentation offered. So the rapid headline is about the formation of a new consortium of major social impact investors in the United States who have pooled about $500 million in funding, basically aiming to influence the present and future of AI towards more pro-social social impact. And so they are, as you can see, an impressive group. They have 3 explicit goals that they've set: to expand the group of people who are involved in the decisions of AI, to strengthen the organizations that are bringing people together to shape AI in the future, and supporting the creation of public good. So this is very well suited to what the Active Inference Institute has been up to. And so I wanted to start here, drawing attention to 2 of the slides that I have later on in the second clip that speak about both bioregionalism, a form of local environmentalism that is organized around natural ecosystems rather than political or jurisdictions, and how, in addition to having networks of allies, that we have established methods and specialized tools that can make us really stand out in this space. And we have been, for some time, been working on this, but that as a community, would like to draw attention to how might we be building additional collaborations and how might we be building additional synergies to really make a collaborative difference in the world.
All right. Next up is going to be a 3-minute video from Joel Dietz. Here we go.
Showing you a tool that I made originally for Levin Lab that I've sort of been extending to Active Inference. But first I will show sort of how it works and the concept behind it. So the goal over here is to show the summary of a research and field and extending. Showing you a tool that I made originally for Levin Lab that I've sort of been extending to Active Inference. But first I will show sort of how it works and the concept behind it. So the goal over here is to show the summary of a research and field on a time series to show how well various hypotheses are validated. And if you kind of roll back the sort of clock within a field, you'll be able to see, over what time series, you start validating various hypotheses. This is ideally to cause people to make more and better hypotheses and to sort of automate this. It uses probabilistic knowledge graphs. So the concept here is that everything is, extracted sometimes from peer-reviewed papers. That's mostly what we're working off of, into various evidence and assertion things. The weight of evidence is done by an LLM. And so all of these things are kind of bundled together and then published in a nano publications format, which is on an immutable ledger. So it basically will give you, a record, and it also helps if the LLM, you don't totally trust it or it's flubbing or whatever else. Obviously, that's still an issue, and it may be more an issue for more contentious topics. so that you can basically have a different LLM scored or have multiple different versions, or gradually improve it. So certainly this technology is technology that's in flux, and so it's not always perfect. This is a sort of importing function, so you can easily kind of import various RDF files. So you get these kind of nice sort of summaries, and sort through the various aspects of it. So yeah, originally, again, this was really just for some 11 things. There's also had an economic calculator, which I'm not going to show, but it shows the sort of downstream economic impact of various things, including projections, and it has a bit of a comparison feature to see for people who are interested in investing or putting more money into these things, what that might evolve with. So we kind of have a similar sort of concept here with active inference. More or less replicate the same model, but obviously the hypotheses are not the same as they come through. You can see the kind of evidence accumulation and sort of hear what it thinks are sort of validated hypotheses, including just a sort of variational free energy kind of concepts with respect to sort of neural systems that are providing Bayesian inference. Decision making, control, and reinforcement learning, cast as inference down to the things that are like not entirely validated, as it says, to basically psychopathology, decision making, and things like that. So we have some work to do, I guess, in a way, because this has been a bit of effort to sort of build software in between. But I just thought I would give it out as a sort of discussion point that could be a useful way of doing new forms of meta-analysis. And also for things that are maybe in the more contentious category, to have sort of multiple different versions, besides the fact that this can kind of be automated and potentially used to drive different types of experiments. Thanks for your time. If anyone wants to use this software, please get in touch with me. I'm very happy to make this available to other researchers.
Okay, next up is going to be a 5-minute lightning talk by Alexander Sibi.
Hi, my name is Alex, and here are some ants. These ants are all mathematically driven. I think of them as Markovian agents, and the memory is actually stored in the actual environment itself. So these are Markovian agents exploring their environment, and you can see them starting to build little defense mechanisms here. And you can also play with different variables and different parts of the script. You can add different layers to the network, and so you can see what's going on. And I've done this with lots of different biological and physical systems. I'm really interested in what happens when variational free energy reduces, and I see it as coherence increasing. That is, coherence is memory density through time. Here we have a mycelium network, and you can see the coherence field there, growth activity, network formation. So all of the scripts are all mathematically driven using the same formalism, which I'll show you in a moment. Here we can see mycelium network underground, glucose exchange, and moss starting to exchange nutrients in the network there too. And some L system trees up there as well with the photosynthesizing sun. Hurricane. So on my talk, you'll see that that has a higher omega value because it's more in an exploratory campaign. So it's sort of higher temperature. Here we have thunderstorm. And I'll just explain as coherence increases in the cloud as charge, eventually it reaches a rupture threshold. And we get thunder and lightning. The sounds from these scripts where their sound is all diegetic from within the script itself. Here we have an atom and change the electrons, and it will change the obviously the atom that we're looking at. And just to explain that CRR, or coherence rupture regeneration, which is the formalism I've been using, is a coarse grain formalism. So I'm not saying that this does anything microscopic within paradigms, but it's a good, I find it a helpful way to think between paradigms. So here we have the sun, again, modeled with the CRR. And here again, we're looking at how coherence builds through time, how we reach these rupture thresholds where exploitative campaigns can no longer operate, and we need exploratory new generative model, which reweights from the past states of coherence. Here we can see ice and change the temperature, watch ice forming. So I've done basic modeling as well. This one has a lower omega value. It's sort of less exploratory, more rigid as a physical system. And here we can see a hologram. So here we have perturbation of the coherence field. And this is exactly modeled in the script. Here we can see a maze, or sort of rim solver. So the agent is a Markovian agent, and the memory itself is stored in the field, in the environment. So what is CRR, or coherence rupture regeneration? Well, here we have coherence formalism. So coherence is building memory density through time. It's essentially all past states matter in a non-Markovian sense. And we have this Lx tau here, which is how memory density is built through time. Coherence reaches critical thresholds where the environment provides new free energy spikes and the exploitative campaign can no longer work. So we require an exploratory campaign or creative campaign. And this is where the rupture, or the direct delta, leads to a new kind of generative model. And you could think about this as scale invariant, moment to moment, or coherence built through time, and then rupture being like ecosystem collapse or something in the body collapsing, or a psychological shift or an ontological shift through time. Here we have regeneration. So here we have the historical states here, picking up from the coherence of memory density here, and we have a Boltzmann-like regeneration operator. So regeneration is exponentially building on what mattered most in those past states through time. So this is an exploratory playground. So I think of it like a free energy playground, exploring coherence-based approaches. I put various videos on here, explainers, other bits and pieces for people to play and explore. And I'm just looking for people that might be interested in this. So I'm really happy to be part of the symposium, and thank you. All right, next I'm going to play a video from Yana, and Yana also requested that I read this GitHub post, which I'm also going to put the text into the chat. Okay, here we go. In a quiet village on the edge of a sprawling forest, there lived a peculiar gardener named Andrei Markov. Unlike other gardeners who planted their crops in neat, predictable rows, Andrei saw his garden as a living mathematical puzzle, where each plant had its place not just for beauty, but for balance and harmony. One misty morning, Andrei stood at the center of his garden. To build a Markov blanket around his beetroot, Andrei carefully selected plants that would support and complement it. He planted onions nearby. Next, he chose broccoli, not just because it stood tall and proud, but because it loved calcium-rich soil. The beetroot, by contrast. On either side, he placed Brussels sprouts and cabbage, their sturdy stalks forming a protective barrier while their leaves shaded the ground, keeping it cool and moist. When the planting was done, Andrei stood back and smiled. His beetroot now lay safely within a circle of companions, each plant playing a role in the dynamic Markov blanket. Wiping his hands on his coat, Andrei whispered to the garden, "Together you are more than the sum of your parts." And as the seasons passed, the Markov garden thrived.
balanced, resilient, and harmonious. Welcome to the collaborative code-making session where we explore active inference through companion planting, groupings, and relationships. Okay, next is going to be a 4-minute lightning talk by Ri Xu. Here it is.
Hello everyone, this is Rishi PhD. I'm a mom and a nerd running a business solo, which means that some days I feel like a CEO and other days a vending machine dispensing snacks and emotional support. That's why I would be wearing a soft and warm mom nerd type shirt during this talk. Hi everyone. So have you noticed that when we move a toddler's toy to a new place, it becomes a new toy for them? The object doesn't change, but the context changes. And yet, it feels completely new because their brain learns through context and its playful prediction. And adults actually do the same thing, just with jokes. For example, how to refresh old routines by setting them in new contexts. Using the same punchline, but new premises. And your relationship will thank you. And by the way, punchline is a line that flips the normal expectation for the situation. Premises, which is the scene, topic, situation, example, gym culture, grad school, and parenting. And somehow it feels fresh every time. And that's because humor, like play, is a little prediction game. Your brain expects one thing, gets another, and rewards you with laughter. In parenting, the premise changes every 5 minutes. Say, my toddler is manipulating the system, aiming for something she wants, but endlessly generating new premises. That is, in grandma's room, in the bathroom, in the living room, in a car. This is one of the best jokes I wrote with ChatGPT. Situation. My toddler is basically running a multi-agent reinforcement learning experiment. First, she goes to grandma for 5 minutes of 小红书 short videos. Grandma says, you have to pee after, okay? But it's prepaid screen time. She ignores the contract. And the second situation, then she comes to me, no words, just takes off her pants, sits on the potty like, we both know the protocol. Because in my lab, she only gets the phone if she starts by sitting on the potty. I didn't teach her manners. I taught her API integration, which means knowing the exact steps to unlock the system without understanding the system. So it looks like she's obedient. She pees, grabs my hand, and goes, let's go dance, which means let's go watch dog dance video on YouTube. Punchline. At this point, we realize she's not learning politeness. She's A/B testing our parenting models to maximize screen time. And we're both failing QA. This is Rishi PhD. I'm a science writer and AI strategist. What I've learned during all my projects. We don't have time to become an AI engineer, but we need an AI as an appliance, like a microwave oven. You push the button and something helpful comes out, and you go back to life. But the fun part is, we can use AI to make our everyday life efficient and everyday routine more playful. We can use ChatGPT to think more deeply, not less. And we can use it to understand our kids and ourselves with more softness, letting it expand what we can imagine, analyze, and express. And I'm sharing these experiments through my new podcast that's called Struggling Nerdcast. And the Chaotic Mom Nerdcast. You can also find how I use ChatGPT to write this conference talk script that you are listening to with all the behind-the-scenes struggles. I'm also working on how AI can support parenting psychology, why kids melt down, how emotional regulation could develop, and how to respond with empathy instead of panic.
Okay, there will be a couple-minute break, and then we will be back with the next session. Okay, we're back with Robert Warden, Consciousness and the Free Energy Principle. So Robert, looking forward to your presentation, and anyone watching live can write in the chat. Go for it.
Fine. Okay, I'm talking, as Dan said, on consciousness and the free energy principle. So we get straight into it. The FEP is very closely involved with consciousness, because what I'm talking about is phenomenal consciousness, which is the what it is like to be alive, if you like, rather than access consciousness, which is what we do with the contents of our consciousness. And a very large part of phenomenal consciousness is spatial consciousness, and that is having in our heads a conscious model of local space around us. And that is the main part of our conscious experience, really. It's just understanding things in front of us, things around us, our own bodies, all in one model of local space. And this model, as we well know, is constructed from sense data, and it is a maximum likelihood model. It's the most likely model that we can make, given our sense data, of the current world around us. And so it's a minimum free energy model. So that's why the free energy principle is very relevant to consciousness, because the conscious model, central conscious model that we have, is an FEP model. And there are several FEP theories of consciousness around. The one I'm most aware of is the projective consciousness model by Woodruff and others. But there is a problem about them, because they are all neural models. They all say that consciousness arises from neurons firing in the brain. And as I shall describe, all neural models of consciousness have a very serious problem. What is that difficulty? This is about to appear in a paper in Neuroscience of Consciousness. But what the difficulty is that the brain is a neural computer. It's obviously computing what to do given sense data. And any computer, all the information on it inside it is encoded. In the brain, it's encoded in neural firings. And the point about computers is that they have encoded information inside them. But the key, which you need to decode that information, is outside the computer, not inside the computer. I'll give several examples of this as we go on. So all information in the brain is encoded as neural firing rates. And the neural events inside the brain don't decode them. The decoding is done outside the brain, as I shall describe. But spatial consciousness, the consciousness of space around us, contains unencoded information, and I'll describe that in a minute as well. For instance, information about the boundaries between things, the edge of your screen or the edge of your table or whatever it may be. And so that unencoded information can't be got from the encoded information in the brain without a decoding process. But the key we need to do the decoding is not there in the brain. So the result is that neural events inside the brain can't be the cause of consciousness, because the information you need to decode them is just not present, nowhere to be found. So to go into a bit more detail about this, the first fact about consciousness, the main fact, is that it's a model of reality. And there's a kind of one-to-one correspondence between the world out there and our conscious awareness of it. And the one-to-one correspondence is the boundaries, like a boundary between that little branch and the air, is there in reality. It's there in our consciousness. And we have qualia inside our heads, which, as is well known, you can't actually tell what the outside world is doing about qualia. Your qualia of green might be green or blue or red, but it's very consistent. In other words, if you've got a yellow qualia here and a yellow qualia there, it's the two qualia here and there in your consciousness are the same. The two qualia there's a correspondence between things in the real world. So all this amounts to is that the geometry of consciousness has a very close match to the geometry of the real world. And it's a very detailed match. There's a lot of information in that match. And that's the most information-rich fact that we have about consciousness. So that is the fact that a consciousness theory ought to explain. But the key point is that the consciousness of space is not encoded. There's a direct mapping between this boundary here and that boundary there. So why can't neural theories do that? Because when you have a neural theory of consciousness, you have the idea that there's loads of neurons in the brain and firing patterns in the brain encode information. And that is heavily encoded. That information in the brain is a highly encoded version of the information in consciousness. Here's consciousness. And so there's decoding information, IBC called here, which is very large. There's lots of information you require to decode what's going on in the brain to give you consciousness. Consciousness itself is very like the real world. So there's very little decoding goes on between consciousness and the real world. And the problem for neural theories is that decoding information is very large. And no neural theory tells us where that decoding information comes from. And it's not actually in the brain. It's almost as though information in the brain was encrypted and somehow it got to decrypt it to give consciousness. Nobody knows how you do that decrypting. So I shall step back and talk about computation in general now, not just in the brain. And there's been a recent realization, which actually is a very old realization by Horstman and company, by Stepney and Kendon, that computation itself is not on its own a physical process. It is a way we interpret a physical process. And the interpreter is always external to it. So information inside any running computer is encoded, and the decoding key is not inside the computer, it's in an external interpreter like a person. And so without any decoding, the physical events inside the computer have no meaning. They're not about anything. And this is not a new insight. It's been re-derived recently by Stepney, Kendon, and Horstman. It goes back as far as Leibniz, which I will describe in a minute. So to make this point clear, I'll draw an analogy between books, computers, and brains. And these three devices, they all have information inside them, which is physically encoded. Without encoding, that information has no meaning. The decoding is always done outside the device. Now, this point, so inside the device, there is no meaning. There is physical events going on, but you don't get meaning from them without interpreting, without decoding them. So this fact is actually quite obvious for books. And the question is, why is it not obvious for computers and brains? So meaning in books, physically, the meaning of what you've got in a book is squiggles on a piece of paper here. And there's a load of decoding we do to get meaning out of it. We decode the ink shapes as letters, encode strings of letters as words, encode strings of words as sentences. We decode the sentences as meanings, and we finally decode the meanings as stories. So we're all the time, when we read a book and get meaning out of it, we're doing a load of decoding or interpretation. You get a similar picture for computers. Books are static, but computers are dynamic, but that's not a big difference. In digital computers, physically what is going on is voltages in circuits, electronic binary circuits. And so to get meaning out, we interpret. And again, there are several layers of interpretation. Interpret the voltages in transistors as bits, interpret strings of bits as numbers, interpret the numbers as solutions to algebraic equations, for instance, and we interpret the algebra as models of physical things. That's what we do when we run a simulation in a computer. And we only get meaning about the real world by doing all this decoding. This goes back as far as Leibniz. In 1714, his book Methodology, there's a famous piece, and he says, we must confess that perception and what depends on it is inexplicable in terms of mechanical reasons, that is, through shapes, size, and motions. If we imagine a machine whose structure makes it think, sense, and have perception, we could conceive it as enlarged, keeping the same proportions, so that we could enter into it as one enters a mill, assuming that when inspecting its interior, we will find only parts that push on one another, and we will never find anything to explain the perception. So he was saying essentially the same thing. Without using the language of computers, a machine whose structure makes it think, that is a computer. And he was saying without decoding, we don't get information out of it. It's not meaning inside it. And Leibniz was saying this not just as a philosopher, but as a mathematician and an engineer. He designed one of the first calculating machines called the step reckoner, which is shown below. And what he was saying was, there aren't numbers inside that. Outside, we have numbers, and we interpret the numbers, we encode the numbers as turning the wheels. And then these little pointers on top turn around, and we decode those pointers as numbers as a result of calculation. The calculation is not going on inside the machine. It's us that's interpreting the results of the computation of the machine as a computation. So Leibniz said it first. So if we finally come on to brains, particularly what's happening is neurons are firing. And again, there's loads of decoding going on in our theoretical models of the brain. We interpret neural spike trains as sense data, or we interpret them as probabilities in the Bayesian models of the brain, probabilities of things and events, or we interpret them as geometry. And synaptic connection strengths we interpret as learning and memory. And the interpretation, the main interpretation that goes on in the brain or outside the brain is that it puts out spike trains, and they're interpreted by the muscles as motor commands which make movement. So that's the interpretation which happens outside a brain. So what we've said so far is that if you just have a computer, information inside the computer does not have meaning on its own. It only has meaning when you interpret it outside the computer. So this is a direct contradiction of a doctrine, a philosophical doctrine called computational functionalism. And this is the thesis that performing calculations of the right kind is necessary and sufficient for consciousness. So this is saying that thesis is wrong. It's been a very popular position in philosophy for a long time, but it's wrong. And that means that all the theories of consciousness that are based on it, most of them, are wrong. So if we go through some familiar theories of consciousness, most theories assume that it's caused by neural events inside the brain and that certain computational processes are taking place. And I'll call those processes P1, P2, and so on. And the assumption of most theories is that some of these processes, some special processes, cause consciousness. And different theories have different special computational processes. It might be representing things in the visual field, or it might be in a FEP model, it might be building Bayesian models of reality. Or the higher order theories that say the key thing for consciousness is the process of reflecting on the brain's own computations. Or it might be computing emotional response or so on. But the point about all these models is that those processes, P1 and P2 and so on, don't actually happen in brains. They happen only in our interpretation of the events in the brain. So without that interpretation, they could be completely different processes, Q1, Q2, and so on going on. So neural theories which say the physical things happening in the brain are the cause of consciousness can't be right. Because those our theories of the brain have lots of encoding. We have lots of interpretation of what we think the brain is doing, but physically the brain is not doing that. The brain is just doing neuron firing. So how do we get out of that? And here's the positive proposal. Suppose there was an analog model of space inside the brain, a model that's not heavily encoded. And this is the physical picture here. Suppose we have neurons firing away in the brain, and inside the brain there's actually a physical analog model of space. So there is a lot of decoding of the neurons to create that physical analog model of space. And the analog model of space is, as it says, very like real space. So in that idea, that analog model of space could be the source of consciousness. That is a theory of consciousness which I've developed and which I believe has a great deal to do with the free energy principle. So you say, why does the brain have an analog model of space in it? What use would it be? It could be very useful because it could help to store a Bayesian model of what's where in space, integrated sense data. It could be a short-term memory, persisting that spatial information for short times. It could be used to classify things, to know what things are around the animal, so what things need to be, something to be done about them. It could be used to simulate and plan physical actions, and it could be used to compare the present moment with previous situations. So if you had an analog model in the brain, it could actually, in engineering terms, be very useful. There are reasons for it to have evolved. And there is a possible physical form for such a model in the brain. And the proposal for the analog model in the brain, which is in an archive paper here, is that there is a wave excitation in the thalamus. And as is well known, a wave excitation, a three-dimensional wave excitation, can hold 3D spatial information as a 3D Fourier transform of space, just as a hologram does. A hologram is a physical example of an analog spatial model. It goes through a Fourier transform, but that's not an extensive decoding operation. It doesn't require a Fourier transform to get back from the hologram to the real world. It doesn't require a huge amount of decoding information. It just requires a scale for the Fourier transform. Now, why does that fit the data? How could there be a wave inside the thalamus? The thalamus, as is well known, is a site of integration for lots of sense data of different modalities. They all pass through the thalamus. And the thalamus has a very well-preserved round shape, which is very suitable to hold a wave in 3 dimensions. Now, the other piece of evidence that I won't go into is that if you don't have a wave, that the anatomy of the thalamus, a small round thing in the middle of the brain, doesn't make sense. It would do much better to disintegrate and move nearer the cortex. And another piece of evidence is that lesions of the thalamus tend to interrupt consciousness, whereas lesions of the cortex, for instance, do not. And so the hypothesis is that the wave in the thalamus is the source of consciousness. So I'm doing quite well for time here. We're going to undershoot time quite radically. So how does that relate to the FEP? Current FEP models look a bit like this, a very crude sketch. There's a brain, which is a neural computer, and it has an outer Markov blanket. Inside the brain's encoded information in neural pulse trains. There's a decoding process, which converts strains into muscular action, and that goes around to affect the world, and through the senses, sense data comes in and is encoded. So there's an encoding, and there's one particular kind of decoding, which is decoding spike trains into muscle actions, but there's no decoding of spike trains into a model of space. So there is no consciousness in these models. How do the models have to change to accommodate the proposal that there is an analog model inside the brain? It looks roughly like this. The same picture, but made a bit more complicated. There's an outer Markov blanket between the brain and the external world. There's an inner Markov blanket between the neurons of the brain and the analog model in the thalamus. So there's a lot more encoding and decoding goes on. Sense data comes in, is encoded as neural spike trains, and is decoded into the analog model. And there's a little feedback loop here between the analog model is encoded as spike trains again, and it's iterated until the analog models are good Bayesian model of the external world. So there's an encoding and decoding cycle there. Also, for planning actions, there's an encoding and decoding cycle here. The model is encoded. Neurons work out possible planned actions, and they are decoded to compute the impact of those actions on the world. So there's more encoding and decoding goes on there. And the proposal here is that consciousness arises from the analog model. So the key thing is that we can carry on building FEP models. We need this extra ingredient in them. And it's a very necessary extra ingredient because without them, the FEP cannot account for consciousness. And consciousness is probably the key factor about the brain that we really need to account for. So I'm coming to my conclusion now, well ahead of time. The conclusion is we need to understand consciousness in the FEP. But we can't do it with a neural theory because neural theories of consciousness can't be right. Neural complication, its computation is heavily encoded, but consciousness itself, spatial consciousness, is not encoded. So we need something else in the brain. The proposal is that the something else is an analog model of 3D space held in the thalamus. And so we can extend the FEP in that way to have an analog model as well as the neural model of the outside world inside it. So there we are. That's the proposal. I would very much like to try and integrate this model in the FEP. And if anybody else is interested in working on building FEP models which have analog models of space inside, I would be very happy to work with them. Okay, so I finished way ahead of time. I hope there's been a discussion.
Thank you, Robert. Ahead of time, but you can't be ahead of space. Okay. People in the live chat can write any questions. I'm just gonna write down a question. Was you said physical events don't have meaning without interpretation. So then must interpretation be something other than physical? Or is it that the act of interpretation is inaccessible, but it can hold the access consciousness of the interpretant?
Well, some interpretation is done by us as people in our minds. When we sit outside a computer and we say the computer is computing this or that. There is also interpretation that isn't done by minds. For instance, the main example I gave was where the brain puts out spike trains and muscles interpret those spike trains as physical commands to contract. And so that's an interpretation which is done outside the brain, but it is not done by any other mental entity. It's just purely done by a physical thing, a muscle.
So then is interpretation the consequence of the stimuli or a sense of the relevance? Because
the interpretation is the consequence of the stimuli. In other words, brain spike trains have a consequence that the animal moves.
What would make that? What would
real
make
action in the world?
What would make the possibly waveform implications of like visual stimuli be accessed in an aware sense as opposed to the ostensibly unconscious, or at least not perceived by the central consciousness of a muscle contraction?
Well, the hypothesis is that for some reason which we don't understand, the analog model held in the wave is a thing that causes consciousness, and consciousness exactly mirrors that analog model. So that's, if you like, that's David Chalmers' hard problem, why something physical in the brain causes a mental thing of consciousness. And we don't have an answer to that hard problem, but I'm personally not worried about hard problems because in any science, all of physics, you come down to hard problems eventually. So if you have a decent theory that explains most of the data, and there's a hard problem somewhere, like the hard problem of the mind is how do physical events in the mind make consciousness? And the hard problem of physics is what's the fundamental particles? You go down through atoms, molecules, protons, quarks, and so on. And the hard problem is where is the fundamental particle? I'm not bothered about the hard problem of physics. I'm not really worried about the hard problem of consciousness. There has to be laws which say physical events cause consciousness. And we just have to postulate those laws and keep them as simple as possible. The law here that's postulated is that when there's a certain kind of wave going on in the thalamus, that is the cause of consciousness. But it has to, you can't go down deeper than that.
What do you think the architecture of this model that you'd like to build would be? And then what would it reveal, and what would be the implications of what we could learn from it?
Very good question. I'll just go back to the previous slide. And the architecture of the model is essentially that picture. So it is a fundamental addition to the FEP, to active inference models. I think we have to explore its properties in detail to start asking ourselves, what are the implications? So it's a proposal that we build models along those lines with the inner Markov blanket as a boundary between the wave and neural firing. I think we just have to explore the consequences. They will be unpredictable till we've dug into them. Sorry, that's not a very exciting answer, is it?
Yeah, I'm just looking into the center of the decoded analog model. And that is, I mean, does this just regress another layer into a sort of opaque, nested onion model? Because if
no, it's not an onion model at all. It's not onion, because onion, you would say, will go down to a deeper layer and a deeper layer and so on. And so a lot of the ideas of the FEP, like sort of scale invariant Markov blankets within Markov blankets, don't apply. You have this Markov blanket, then you got the wave, and that's the end. No inside Markov blankets, no onions.
Is what's relevant the statefulness of the center of the donut with the decoded kind of private key exposed? Because if so, then why would the statefulness be the experiential element?
Well, you're coming back to the hard problem again. We don't know why. I mean, it's just consciousness is there as a part of nature. We know it's there. And previously, we've had to invent laws of physics to relate parts of nature. For instance, many years ago, we had matter, like hard things that you could touch, and we had electricity. And the two were very different. And force and electricity were very different. So we invented bridging law to bridge force and matter and electricity, force and electricity. Similarly, we have to invent a bridging law to bridge consciousness and a material wave, a physical wave. And we just have to postulate that law and don't worry about it anymore, basically. It's a hard problem relating to completely different phenomena like force and electricity or like waves and consciousness. That is, you have to just propose that there is a law. Then the law has to succeed or fail by fitting experimental data. You don't worry about the philosophical foundations of proposing such a law. If it gives you a good theory that fits the data.
Yeah, it's a very interesting. I don't know if meta science is the right take, but definitely, proposing a synthesis doesn't need to be constrained by repeatedly the fact of the matter that prior to the synthesis, the phenomena are fragmented. That's kind
right,
of that's the starting point of the proposal, not the conclusion of the execution of the proposal. And then where it becomes the research ahead and the development is, what are those implementations? What kinds of models do we need to sweep out here, and what measurements and what empirical data sets to connect to, of which the data sets wouldn't necessarily be of a different kind than data sets that could even already exist. Like it could be proprioceptive data or spatial awareness data. It could be developmental information on when children or different species have awareness, like object impermanence.
That's right. I think the test of a theory is the fit to data. And as you say, the data is all kinds of data relate to consciousness. The main piece of data that relates to consciousness, I'll go back to the slide, is this one. The fact is that we do have this thing inside our heads that's just very like the real world. That is a huge, important set of data points with lots of information. At any moment of the day, we've got this whole conscious model of the world as a very tight one-to-one correspondence with the real world. That correspondence, that matching, is a huge experimental fact. So I think that's the main thing a theory of consciousness has to account for. So we need to just build those theories and test them against that fact. It's a kind of private fact, which just makes it a bit awkward, but nevertheless, I think it's a private fact that we have.
What is the private fact?
The private fact is that I'm aware of the world right now as a three-dimensional model. You're aware of the world right now as a three-dimensional model. There are things we can't talk about, like I can't talk about my green qualia in a way that persuades you that you're seeing green the same way as I see green. So there's private parts of it, but we can discuss public parts of it. For instance, if we're in the same room, we could look at the same thing and say, that's a straight line, or that's a flat surface, or that's a bump. And we could agree on that. And those things are the correspondence between my private model of the world and the real world, or your private model of the world and the real world. And the fact that they match up in this neat way is a big experimental fact.
Yes. What are your... Go ahead.
The main thing that people, I think, will find uncomfortable is that there have been so many neural theories of consciousness, and there continues to be, there's a website with 350 theories of consciousness on it, and most of them are neural theories, and all neural theories have to be wrong. There is something they're missing out, this decoding step. And I'm saying the decoding happens physically in the brain to create the wave in the thalamus.
I'll read a question from the live chat. So B. Solfum wrote, fascinating and provocative theory. Could you comment on the possible mutual illumination between this conception and of the semiotic thinking of Peirce and the connection with introspection?
Well, probably semiotic. I can't actually comment much, but introspection, particularly, I will comment on. I think introspection is the mind thinking about its own thoughts. And that I think, is not necessary for consciousness. In other words, plenty of animals have no introspection, as far as I know. But in this theory, we would expect those animals to have spatial consciousness. So the theory says spatial consciousness has nothing to do with introspection. It's not a higher order theory of consciousness. It's a base order theory of consciousness.
Yes. Some people, to the question, some people have explored, Majid Beni and colleagues have explored the Peirce connection specifically. And I think where it connects is this question of primary semiosis and higher order theories, metacognition, introspection, these kinds of inner semioses that don't deal with the primary, like, redness of red, the onionness of onion, the at-handness of an affordance, but rather the introspective awareness of that primary semiotic event.
Yeah, I think primary semiosis is the way to put it. Primary as opposed to higher. Yeah.
So, what are your next moves? What would make it a good, productive research holiday season in 2026?
Well, I'm not an expert on FEP implementations, and so I would really like somebody to step forward and who does know how to do FEP models and say, let's build an FEP model. Let's take the FEP toolkits we've got, or new toolkits if we need them, and let's build an FEP model complete with variational minimization and so on. And let's apply this out and incorporate the thalamus wave in it, see what the model looks like.
Yeah, and as we've discussed also in the insect setting, it might be more accessible to integrate a biophysically based fly body or insect body simulator with a full brain emulation.
Yeah, absolutely. I mean, I haven't talked about that at all, but this theory, in that mammals have the thalamus, which could be a possible site for the wave. Insects have the central complex and the central body, in other words, the fan-shaped body and the ellipsoid body, which are very well preserved across all insect species and seem to me to be a likely site for the sensory integration, the same sort of sensory integration, which could lead to the same wave excitation and the same spatial consciousness. And I think insects are a great place to look for it because their brains are so much simpler to think about.
Yes. Lot to think about, a lot of good motivation for tool development and for how we keep working on these questions. Anything else you'd like to add?
Not really. I'm sorry I've undershot and left you some spare time, but
it's all good. Okay. Thank you, Robert. Farewell.
Okay. Thanks a lot, Dan.
Bye.
Thanks. Bye.
All right. Next up is a 9-minute lightning talk from John Graves. Here we go.
Many automated systems take data and apply some kind of reasoning, called an algorithm, to help make a decision. The more advanced ones can even plan and execute a sequence of actions to reach a specific goal. But the most sophisticated systems evaluate counterfactuals. Judea Pearl and Dana McKenzie called this the ladder of causation in the Book of Why. Seeing is the first rung, doing is the second rung, imagining is the third rung. The type of questions the system can address become increasingly complex as we climb this ladder. At the first rung, association, which is unfortunately about as far as traditional statistics can take us, we can ask, how are the variables related? What if I see X? What then? At the second rung, intervention, there is prediction about the world as it exists and feedback from actions taken in the world, with the possibility of the difference between the predictions and the outcomes driving a learning process. So doing enables learning. And here the questions become active. What if I do X? Does the action I take have the result I expect? At the third rung, counterfactuals, there is a prediction about the world as it might be or might have been. What could I do? What could I have done? So these second and third level systems don't just ask what is the answer. They ask what can we expect when we do or imagine doing things. This is the essence of having a causal world model. The theory behind these systems is presented in the book Active Inference by Thomas Parr, Giovanni Pizzullo, and Carl Friston. A learning system operating in the context of a world model can reason about hypothetical situations and potentially use that information to map out a sequence of actions which is optimal within the limits of the system's current knowledge. That means truth is subjective from the system's perspective, but empirically verified. Feedback from the actions taken can drive learning, expanding the knowledge available to the system, recursively improving future predictions and driving more optimal actions. Alternatively, the book Everything is Predictable by Tom Shivers presents the historical development of Bayesian logic. Shivers makes a number of very well-phrased observations. First, the great insight of probability theory is that we should look at the possible outcomes from a given situation, not what has gone before. The probability of an event is the number of ways we know of that that event can occur, divided by the total number of things we know of that could occur. Probability thus gives a quantitative measure of the things we don't know for certain. It may require a subtle shift in mindset, but think of certainty as a continuous rather than a discrete binary value. 1 can represent complete certainty, and 0 can represent complete impossibility, but the points in between can reflect levels of confidence and skepticism, with 0.5 representing an equal possibility of true or false, a state of complete uncertainty. The key insight of the Bayesian method is that you must add any new information that you get to the information you already have to make each subsequent prediction. Intuitively, think of learning by trial and error. When we learn from the errors, we don't make them again on the next trial. Sampling or statistical probability is different from inferential probability. What can we predict about a sample? given that what we know or think we know about the whole, that it's hypothesis testing. We don't really want to do that. With inferential probability, we're really asking what can we conclude about the whole given a sample or samples we've taken. Bayes showed how starting with an estimate of what is most likely to be true to your best knowledge, your model, you can make inferences and draw conclusions about what is likely to be true in the world. Consider, as a practical example, the doctor who looks at a patient's data, particularly their symptoms, and has to reason to the most likely conclusion, a diagnosis. Diagnosis guides a decision about treatment, and treatment may or may not result in a cure. Since the world is messy and often ambiguous, data is never perfect. Systems must deal with uncertainty, changing circumstances, and incomplete knowledge. This is where genius agents can help. They're designed for decision-making under uncertainty. The following comes directly from the Genius documentation. Genius agents tackle ambiguity through probabilistic modeling and Bayesian inference. This is very different from the approach of large language models, which are built on a foundation of neural networks. Genius agents use a probabilistic graphical model to represent the world, specifically a directed acyclic graph, which links the model variables, frequently from cause or prerequisite to effect. We'll focus on two related types of graph. The first, discrete Bayesian networks, are a great starting point for introducing the core logic and themes behind how these agents reason and make predictions. Here in the sprinkler example model, the cloudy variable has arrows to both rain and sprinkler, while the wet grass variable is the end point of the arrows coming from rain and sprinkler. The arrows make the graph directed, and the fact that there are no loops makes the graph acyclic. The next step is to add probabilities to each variable. Cloudy is shown as having a 50-50 split. Then rain on the left is shown as having an 80-20 split when it is cloudy, but a 20-80 split when it is not. Sprinkler on the right is shown as off 9 times out of 10 when it is cloudy, but split 50-50 when it is not. Finally, wet grass is shown with 8 different probabilities, depending on the 4 states possible for the 2 variables sprinkler and rain. For example, in the first column, when the sprinkler is on and there is no rain, there is a 0.9 chance of wet grass. The notation for expressing these conditional probabilities uses a vertical bar to denote given. When a probability has multiple dependencies, they are listed separated by commas. A factor graph replaces the arrows connecting variables with these probability tables, which are then referred to as factors. This sets up the system to make 2 types of inference. First, a forward inference, also called conditioning, where, for example, an observation of either the rain falling or the sprinkler running in green allows for the inference of wet grass in red. Or the inference can go in reverse, so observations of wet grass with a sprinkler running in green can be used to infer the chance of it being cloudy in red. The next lesson will cover how the variables, states, and factors come together in Genius.
All right, Pablo, how you doing?
Hello. Hi,
How you
Daniel.
doing?
Doing good. Are we live? Not yet,
Not
right?
yet. Not yet.
Okay. So
Okay, welcome back. Hello, Pablo. This will be a little different
hello.
session. I have put a link into the YouTube live chat, and it's available in the program as well. And Pablo is going to share this space, and then we're going to just run around in that space, and you will share whatever you have prepared.
Yes, awesome. Okay. I think I might be sharing my screen now.
Yep.
Okay. Awesome. Hi, I'm Pablo. I'm gonna be talking about what could be the future of internet. We think the next iteration of internet is going to be telling stories in 3D environments and with, of course, agents, hopefully agents with active inference systems. And we have prepared this environment for the community and for the symposium. Someone already, Paul. Don't worry, you will be back. You're okay. And the idea of this space is explore the space and collect the 4 different symbols that we are around. So we should be like exploring and sharing. It should be very educative. We have been involved with the community and the Active Inference Institute for, I think, already 3 or 4 years, and it's it's an honor to be doing this test. Take this as a first approach of 3D internet, and hopefully next symposium we will have more to share. So we should be exploring the different islands. This, as you can tell, is a kind of a brain and an interpretation of what could be a decentralized symposium. You can follow me. My name on the top of my avatar is Pablo FM. and we can go and start exploring a little bit. So here is the program of the symposium. So we can tell how it goes, the different days and the different persons that are gonna be talking. Yeah, this is not working. I'm gonna try it anyways. Oh. Ah.
So many levels there. We're screen sharing.
Yeah.
Your screen share of yourself.
Yeah. Cool. So the idea is that we can move around and go for the pop-ups and read here the adventure. Interesting.
Yeah, it's fun how you pulled out those quotes that are a little bit like a doorway between the technical content in the textbook and just these bigger adventure and mystery questions.
Yes. I'm not sure if it's behaving as I expected. Welcome to the adventure. Here is a cognitive map of the active inference, but it's incomplete. The 4 states of the system are missing. So find the 4 ellipses, gems, and send them here to the correct state. The books will give you clues about where the states of each gem. And yeah, so we should be like looking for. Oh, I'm gonna fall. I'm a little bit nervous because I think it's not behaving. Yes, it's working. No, it's working. Okay. So here, here we have some friends we can go all together to explore. Yes, you can join me and let's go first to this island of the drift, the island of the drift. So here is the book. So this state alters the environment, and with it, perception itself, it does not arise from impulse, but from the need of reduce uncertainty. Not only transform what exists, it transforms what the system believes. Key to move is just to this place. It is to test a hypothesis with the body and reshape a world to match your model. Okay. So
we're reading kind of a riddle, and then we're picking which of the 4 states of the particular partition it corresponds to?
Yes. So that's right. Which one would you say it is?
Let's go with active states.
Yeah. There we go. So for someone that knows active inference, it should be easy, but I think it could be a cool tool to explain newbies or people curious about the ecosystem, how this works. So let's go and let's find the next island, which is island of the Remota. Remote island. So one thing that we did here is that you can also infer which state it is without even reading, which is not the perfect, but for kids and people that don't really is getting this level of complexity, it's I think it's a good idea. So In this case, is not part of the system, nor it is under its control. Even so, it saves every signal that could be interpreted. Its existence must be inferred. So it can never be observed. Key. Some causes can't be touched, but without them, your perception would be noise. What what real is what persists, even when unseen. Okay, sorry for my English. So yeah, I think it's the external state. But okay, we got 2 out of 3 or 4. Whoops. You can see already there that we are completing the riddle or the treasure hunt. Let's go for that one on the. I think we need to teleport to the island of Vestiga. There we go. Yes, we use that teleport. And here is the 4th state. This state is not directly perceived, yet it guides every decision the system makes. It is a probabilistic representation of the world built on experience and expectations. It does not respond to the present, but to the model the system manifests of reality. Key. Predictions is not what you see, is what you believe in you are going to see. And that's already changes what you see, okay? So as we can infer is the blue. So we already know that this is going to be sent to the internal state. Okay, awesome. We need to go back to the main square. And it's only one more to go. It's out there, Island of Haze. So let's find, yes, this is the teleport. Whoop, here we are. And the last one is, this is the only state directly accessible. It is discontinuous changing, arriving like a burst. It can inform, but also deceive if taken as truth. It's the first thing that happens and also the easiest to break. It's only useful if you knew what you expect to feel. Okay? Sensory state. There we go. So now we have complete the adventure. We have some Easter eggs, and you can also download the Active Inference book from here. It opens the link straight to the download, and here is a 3D image of something that could be familiar for most. And then because we have discovered everything, we can get our seed of knowledge. So now we have managed to do this small adventure. And this is gonna lead us to another adventure that we did last year. I'm gonna enter into into this world. We have built 3 different spaces for the Active Inference Institute and having a blast during the building of them and trying to explain as easy as we could for new persons that would join the Active Inference Institute. We are not scientists. Our team is mostly storytellers and tech lovers. And this is the adventure of curiosity. And this is another riddle that tried to explain how the Active Inference system it works. So we have the internal states road, and here we have a small instructions, and here we have also an outside. So we have our brain, and this is a representation of what we already have been seeing as the main explanation of the complex maths. This is represents the Markov blanket, and this is the sensory states where some of the nodes are missing on each section. So we should take notes of what are the missing nodes, and with this information we can walk around and try to figure out how all this goes. Here is the basic music lesson, everything. Okay, so these are the missing notes that we were already inferring. We can talk with the teacher.
Is it intentional or possible that the missing notes are the matrices that we need for active inference?
Yes, that I mean, it's intentional that you need to infer to finish the adventure. I'm not sure if I understand properly, but the idea is that you have here like to walk through the different nodes, and let's say this one is the first that was missing. But if I fall, I have not taken notes of the second node, so I'm gonna fall. Yeah. Oops. Yes, here. So the idea is to fill the gaps and reconstruct the piece of that is missing, the parallelism. And yeah, we keep improving this proof of concept that or very early alpha. So here it starts. Okay.
Playing the song.
Yes, and second the last ones, do on the second, re. Do, re, mi. So we go back. I'm not gonna finish the adventure. I'm gonna let the the other part. So to go to Do, which is C, right? E. And here. Oh, I don't recall. I think it's La. No. So yes, we just need one more, and it should be done. And then you can get another piece of seed of knowledge. So I'm gonna go back to the symposium space and keep a little bit with the exploration, because it's another few things that are around here. So if you're new also and you want to show what's been how we build things on the Active Inference Institute, you can come here and probably through a more visual way get the links where the lessons and the courses and the different information that we are building would be available. The idea is that we already have 5 different years of the symposium, and it would be have like one island for each year or something similar. So you can go through the different information that is being shared. I have thought something like the Active Inference Institute ecosystem. So go to the ecosystem. This is part of the ecosystem that most that we have. So we have built, and the other space is inspired on this, and it should serve to explore on a 3D. Oh, this link is broken. No, it's working. The third space that it should help the community to join these 3D spaces. The idea is that on the near future we could speak, share screens here, have meetings, meetups, and pretty much interact on a 3D environment, which we believe is part of the future of the internet. So here it should be like the information to be a volunteer. If you're more about learning stuff, you would have there the different links. If you want to become an intern, or here would be like the teleport to the interns space, and it's just much funnier, gamified way of understanding the internet and the learning. And we're pretty much working on all this. So yeah, I don't know if we have any questions or someone has some curiosity. It's something that we are going to keep building. So, and it's evolving, and hopefully we do something very fun for the institute, and we believe that the education is way better with a gamified and a storytelling approach. So here it should be the space for the board of directors. And if you look this from the top, which I cannot fly yet, but on the future we will be able to fly. And what we will see is pretty much the same structure as we saw on the previous picture.
Yeah. Very cool. Yeah, it's a different mode of learning and playing. It's really fun to see it when and just it's as we kind of break into the digital and these kinds of spaces, we can have all of these linked spaces, different rooms and adventures. And right now, are those characters just procedural dialogues? Or they could have LLMs, or they could be other kinds of things, or what?
Yeah, they can have LLMs. We have already tried that in the past, and it's very cool because then you can speak to them in any language. They can be a very notable about one specific topic. And if we have one LLM that only is for onboarding, it would help people to get a better experience, and they can explore and be helped by these LLMs. And the idea is, yes, during this year, start having not whenever, because I think it's useful to have like a writing or previews NPC speaking and telling you what's going to happen, and at one point it can become an LLM, and it could be also very fun and cool to have them moving around these spaces and serving to the institute and to the ones that have curiosity about how everything works and all that. Anyone that want to participate on this project is an open source project. It's all about experimentation, learning, and having fun, and imagine a better digital future. We really believe that and have hope on building something that is not very dystopical. So we try to do our best and put our grain of arena to build a better future for the ones to come behind. So anyone that's curious or can add value or have any ideas or like or dislike anything, any feedback is welcome. And yeah, we are around the Discord channel mostly, and yeah, very passionate about education and what active inference is bringing to the world, and how we are on open science learning. And yeah, it's been a blast being around this. So yeah.
Thank you, Pablo, definitely. And I'll ask some questions from the live chat. So these will be some fun things to discuss. Okay. B. Solfum wrote, will the link work after the symposium?
Yes. The idea is the internet, 3D internet is going to be live, and we could be improving and using these spaces to share maybe the YouTube recordings or streams that we do.
We'll try to keep that link up, but then more generally, whether it's adventure.activeinference.institute or some other URL that we'll be developing over the coming years, we will have these spaces be very clear. Okay, next question. Is there a separate URL for whatever the Pi logo refers to? What does the Pi logo refer to?
I don't know, Daniel. You know, we have this logo on 3D. We will give these assets to. We will put them so anyone can use them. But yes, please let us know.
Oh yeah, definitely. A lot of things it could be, but that's the Institute logo. Where's the sign up? Well, for this, there's no sign up needed. This just runs in the browser. And for other Institute programs, we always try to communicate it clearly, do our best so that it's available without any barrier. And you can just email blanket at activeinference.institute with questions. And as you enter other kind of programs or courses or experience, then those are signaled clearly.
Yeah. The idea is that to keep it open and as low barrier as possible. And then, of course, on the future, it's going to be a sign up mode, but it's not going to be necessary for most of the content.
Yeah. It's fun. It really does feel like a new kind of journey and chapter in what even just technical education can look like, and also these broader work and professionalism questions. I mean, it wasn't so long ago I was in grad school, and the idea that science would be carried out in a 3D space with chatbots and all these kinds of things, I just didn't even have it on my radar. And now it is a delight. And it's just, we have all of these options for chat and text and code. We can kind of generate the personalized textbooks for broad fractions of material. Maybe at some cutting edge level, there's some poor performance, but for core background topics, where many of us will spend many years, the materials are there. And so I think it's really important and forward looking about what is the experience of those and how do we stay in this for the community and the long run and the marathon and the balance and health, not just propagating a sort of narrow view of what it looks like to learn in just kind of one style or just one type of material, when the real technical material are available in these fun formats too.
Yeah, and it's a layer very much easier to bring more people in, and then you can go deeper in different layers of the knowledge. And yeah, for us, it was like the main idea to make a top-down layer of learning, gamification, and exploring. And it's still a proof of concept, but yeah, we believe that it's going to be something on the future. Already we have like Minecraft and Roblox and a lot of experiences that are very cool.
Yeah, it's an interesting connection with the earlier talk of Robert Warden and the spatial consciousness, because in these digital spaces, it's often hard to have awareness of like how many other people are in this channel or in this live stream, or like what resources are there. And so we have folders of files and all of these infinite branching CODA documents. And then once you have that inner map, exploring them is very streamlined. But there can be a big learning curve with just getting the first situational awareness of what is even there. It's like a big library with kind of branching adventure chambers. And so having a browser-based top-level spatial navigation visual form helps put it all in front of you with what ways that you can move. And then that's the kind of learning by doing, and ultimately the active inference itself is like, what is off to the right? It's like, I do have to look. Oh, that's epistemic value, or this is not what I expected for that. And so just even in the gameplay and in the awareness, basically there's all of the touch points that we could want for going into these technical topics just from this gameplay. And we could talk about perception and cognition, action, all of that, just with what's happening here. So it's a great combo. Okay, one more question in the chat. Do you plan voice interaction with nearby neighbors in the 3D space?
Yes, it's we did actually test it on last week, and also sharing the screen. The idea it was for this year, at least during this day, sharing the screen on the main stage, and audio it would be available. So if you are watching together, all together, this movie, we could, stop and discuss and talk on real time on what's going on. It's sad that it didn't work for this year, but we are super close of doing that, and in other spaces it's already working. Also, it's an Easter egg. Anyone interested on POAPs or 3D objects, NFT objects or digital goods. It's this thing. I will share the link later, and if you write down this word, you can have a collectible, and that's also a fun part that I think next year we will share more about digital goods and the future of digital goods and how we could gamify better the learning experience through these objects that ensure that you at least have a degree of familiarity with the concepts that are being taught or told in the different areas. So this is very cool also.
Awesome. So thank you, Pablo, to you and to the rest of your team.
Thank you, Daniel.
Okay, till next time. See ya.
Ciao.
Bye.
Bye.
All right, thank you, Pablo. Farewell. Good luck with everything.
Thank you, man. Ciao. Ciao.
All right, next will be a 29-minute pre-recorded video by Ana Pereira. Here we go.
Great. So I'm going to go ahead and talk about making sense of uncertainty, designing experiences for adaptive interface. And I actually want to start by taking a moment to explain what this title is, because we're going to be bridging two historically sort of separate worlds. One of really sort of technical space of what's called active inference and free energy. And the other is we're going to be looking at, okay, well, what does that mean for those who might not know those exact same words? Or might not be intimately familiar with them, but are either practitioners or individuals looking to better understand themselves and how to make changes within themselves or create content or applications for others that are net positive. So I'm Ana Pereira. I'm a research fellow here at the Active Inference Institute. I also have a set of projects that you can see at actincycle.com. I'm a research scientist and also have a recent book, Navigating Uncertainty, Simple Scientific Insights for Everyday Life. So let's go ahead and jump into it. So by way of introduction, you can talk about, okay, why does this matter? So we have these things that are called active inference and free energy, and they tend to look like the image at the top of the slide here, but they're largely inaccessible. So if you haven't heard about it, that's pretty common. It's been around for 20-ish some years. It usually takes about 40 or to 100 for something like this to become common vernacular, but it eventually does, right? Like a lot of us didn't know what DNA was, but now we conceptually understand it. So that's some of the hope behind what's happening here. And why I think it's especially important is that this helps explain how humans can overcome uncertainty. And we have a high degree of that in society right now. And design thinking, so more than just colors or fonts, but the overall experience and understanding, offers a bridge between this abstract theory and our lived experience. And so that's what we're going to explore in our time together. Okay, so in this context, and we're going to slow down a little bit to make sure we're bringing everyone along. So if you're technically steeped in the space, perhaps thinking about it from a different perspective is of interest to you. If you don't yet know what active inference is, don't worry. We're going to talk about that as we go. So active inference is like the science, the very physics of us. So who we are, we're constantly inferring what's happening within us and around us. So you're doing that right now and listening to me, processing with the felt senses that are coming up. And what you're doing is you're working to reduce the uncertainty and the dissonance. So every thought, feeling, and action ties back to this fundamental process. So through understanding the science, we gain the insight to more effectively manifest our intentions, right? Because it's not my place to tell you what to do with your life. It's really up to you how you want to do that. But part of my design thinking might be to encourage you to remember that this is your single precious sort of remembered lived experience of life. And then to put this in a bit of context, so over the past year and a half, there's been a series of presentations from preliminary research to a book proposal around how this work could be done to accelerate active inference in the free energy principle in a way that was mutualistic for the larger community, leading to a preliminary book release. It ends up some formats like audio actually take a really long time, but hopefully by the time you're seeing this, it's actually available. And then finally, we have a deeper discussion around some of the science and principles that are in the book, which is happening here. So thank you to the Active Inference Institute in hosting this symposium so we can have these conversations. Okay, so for outline, we're going to talk about design strategy, and then we're going to go into active inference and free energy and conceptualize them, make them easy to understand. Then we're going to talk sometime about one small sort of activity around it, right? Active inference and free energy is a really large concept, but we're going to narrow in on a potential activity, strategy, and design, then have a discussion and finally close. So design strategy. Again, thinking about more than just fonts and colors, but thinking about translating complexity into clarity. So complex ideas like active inference and free energy, the downside of doing this is that they're going to lose some of the nuance when they're simplified. And what we emphasize or omit really depends on what we're trying to do. In this case, the cultural and contextual factors. But it really depends on what your design goals are. So the particular design goal for this was to distill into clear, relatable ideas that were meaningful to contemporary Western audiences. And so that means a lot of simplification, right? If you look at some of the stats, about 28% of American adults can understand the science section of the New York Times. So effective communication requires a very high degree of simplification. And one of my favorite places to draw inspiration from is Kriska's out. They do a really great job of this for a particular media and form. An additional goal is to think about breaking down our perceived reality, right? Sometimes I almost think of it like a neutral, omnipotent perspective of what we're thinking and experiencing as a way to help us kind of break down some of the biases that we might have. So as part of this work, we kicked off with a preliminary survey. It was a sample of representative U.S. population. We saw a substantial interest in the intersection of this larger wellness space and science. It was very interesting to note that people were especially interested when it was giftable or under $20 US. On the right, I have an image of what it looks like at the best case to get this sort of content out. So this would be a book with printed illustrations that you could have at home that you could refer to over time, you could mark up, you could come back to. So not something that's in a digital format, it's away from your devices. It's also not at the library, right? Because it's more personal and more accessible and marked up. In the best case scenario, you're more than double that. This is not funneling money my direction. This is simply the cost of printing, shipping, and the third parties involved in that. And I want to highlight this because it's a very interesting design constraint. And it has really, it's really interesting to reflect what does this mean from a societal perspective. We're not going to get into that now, but it has interesting implications. So, about the design strategy, people are frequently more receptive to information that is visually inviting and emotionally resonant. So, thus, attention is applied to aesthetics as a central construct because it helps build trust and engagement. So, it's a tool that we use in that regard. It's not something personally that I devote a lot of time to outside of a strategic sort of lens. Yeah, like a design lever to help do this work. So let's think about conceptualizing active inference. So historically, if you're familiar with it, it looks something like this. If you wanted to know what active inference was, you put it into Google right now, you'd probably land on the Wikipedia page, and this is the image you would see. It's complex, it's abstract, and it's technical. But then again, so is the math that's going to explain everything that's sort of behind us. So one way that we can break it down is to start to think about domains, right? And we're remembering our particular design objectives. So we considered what it unfolds across the historical representation of threes and normative cognitive capacities, right? You see a lot of threes in math, XYZ. You see it in social constructs like religion, like Trinity. And so the goal was to contextualize these key principles in a way that helped people see new possibilities. So we ended up landing in environment, mind, and body. And, I think after they're learned, they're great to start reminding people, well, these sort of like the Markov blanket, it exists, but it doesn't. It depends on how you're looking at it. And then the next thing you can do is start to play with color motifs and trying to think about, okay, well, what's distinguishable and what's memorable. So for environment, you end up with green, invoking the sort of nature. With body, you end up with red, orange, sort of balanced and inclusivity. And things like blood and internal warmth. And then with mind, you often, we found ourselves with blue, thinking about calm and thought and reflection. So the result is this visual language that is grounded in science, and it's structured to be accessible, designed to be repeated and elaborated. So here you see a description of the active inference, an early description we use in the book, kind of breaking down these processes. But because we're thinking about pedagogical methods and slowly introducing people to more complex methods, at this point, we only allude to the predictive brain. So you can see arrows moving in the opposite direction. For those who are less familiar with what the predictive brain is, it's the idea that what you're probably aware is that you can see the world, you can understand it, you can make actions. So that's potentially happening in this direction. But at the same time, your brain has already learned about the world and is making predictions about what it's going to see. So what we're experiencing is always these two things happening, and it has a lot of interesting implications for the human experience that we end up getting into in later chapters. So we think about conceptualizing free energy now. So we talked about active inference, which is the how, the ongoing cycle, the predicting, the sensing, the acting, the updating. We can start to think about the why, like why is this cycling happen in the first place, and how do we reduce this uncertainty? So we end up illustrating free energy by adding gray for the unknown, so building on our existing visual motif. So this is just one example pulled from one chapter where you see active inference start to be laid on some summaries from the social sciences, especially psychology. So with fragmented cycles or cycles with more free energy, you see things like rigid beliefs, resistance to new insights, sort of closed dialogue. You see the body having increased stress and disconnection, limited regulating practices. The environment, there's perhaps more conflict between science and religion, increased social division. And then in cohesive cycles, you see things like more like reflective beliefs, openness to new insights, open dialogue, increased coherence in the body, connection, regulating rituals, and an environment, we mean more than just, say, nature or pollution. We're talking about anything that isn't you. So this could be communities. For example, this moment I'm in my home in Switzerland. So my current environment is in my house. So in the larger environmental context, in a cohesive cycle with less free energy, you might see things like respect for science and personal beliefs, increased social sort of cohesion. So activity strategy. Yeah, so now that we understand the principles, you could imagine we've been sitting at a whiteboard sketching out what it means to ride a bike and how you ride a bike. We can start to think about, okay, well, what does it mean to actually learn to ride the bike? So we can start to think about some of that strategy. And so one of the things we were thinking of doing is how do we increase people's capacity? And again, it could be towards whatever intentions they have. It could be how to adapt to rapidly changing technology. It could be changing behavior patterns they've been stuck in. In more extreme cases, you might have people who are really entrenched in things like addiction, who might be looking to break free in assistance from others. And so some of the ways that we can start to think about this, and obviously these activities would change kind of depending on what your intentions were and where you were looking, were in much more of the larger like wellness space. So you can then think of things like prediction, action, and learning are all deeply interconnected, right? And so we have these suboptimal inference loops, like maybe some changed behavior patterns. I know in my past, I would find myself arriving at the same destination even after I made a series of changes, and it confused me as to why. And then how intentional practices, and again, this is a subset of the larger active inference space, but how intentional practices can support flexible updating, greater coherence, essentially breaking out of some of those worn in behavior paths that we might have, or the ability to learn a new skill set that we would like. And so this work, it is kind of the more in-depth exploration of what chapter 27 is in the book, Navigating Uncertainty. And what we're going to do is we're going to take a look at, okay, well, what does it mean to update ourselves through activities? And we're going to compare that to algorithm training. So we're going to borrow from machine algorithm training combined with active inference. What's interesting here is that humans train through embodied both mind and body experience. So you'll see how we kind of expand what we do for normal algorithm training to understand the science of humans and what that means for the human experience in updating ourselves. So, ground truth for human systems. Perhaps unsurprisingly, we landed in a space of mind, body, and environments. One possibility, and so for mind, really landing in the intention, is it like reflection, regulation, or focus? With the body, what are you doing with it? Are you walking? Are you sitting? And the environment, like what's the context? Is it social and the larger environmental conditions? And when aligned, it reduces free energy or creates a sort of ecological coherence, promoting adaptive clarity, effective learning, and potentially meaningful experiences. So we could take a running example, or you could almost put this to any sort of fitness activity. And so this again would depend on the larger context of what's happening. But in this case, we could consider it as an opportunity to think about increasing adaptive capacity through practicing reduced free energy. So increased free energy, more of this like lack of coherence, and it would be like a busy city landscape, songs with words, wandering thoughts. But if you were to use the same time and same activity to decrease free energy and increase adaptive capacity, you might run loops in nature with reflective soundscapes, borrowing from musical playlists used for psychedelics can be really great here. I know John Hopkins has a really great playlist that's just really great for introspective sort of reflection and awareness. And then the focus might be somatic awareness instead of wandering thoughts. But again, really pulling in that individualization really matters, right? And it needs to be flexible to meet the goals and realities of the individual. That might mean age. We've already talked about what economics might mean for some, cognitive capacity, live context. These are just a couple examples of things that might play a role. And really emphasizing supporting this sort of self-generated exploration with enough structure to reduce uncertainty. So this very delicate sort of balance. So essentially, the goal is to use the science to help humans today. And this kind of communication can help people begin to shift their experiences now. I also hope and think that the science can help others create for others through a lot of different means. And that's one of the reasons why I'm choosing to communicate in this way, because we're at a point in time where there is more work to be done than there are people to do it. So one of the hopes from this work is that this can spill out through different avenues. Okay, so let's think about actually designing the activity. So the additional details, especially those that are more technical and extend the sort of algorithm metaphors, are available at the paper on actandcycle.com/paper. Just in order to streamline and make this condensed. We went ahead and just focused a little bit more on the human side. And we landed in, again, for this particular example, in this particular chapter, a framework that looked at a 4-quadrant model defined by the 2 dimensions of body, low intensity, high intensity, and mind, quieted and highly stimulated. And this offers opportunity for increased psychological flexibility and adaptive learning. But I'm going to keep saying this over and over again, right? People have agency, and I just like to remind myself how important that is to remember. And people get to choose, where they want to focus. And some may choose to narrow their focus depending on their goals, their context, and their current capacity. We focus on broad spectrum updating because that is supported by active inference algorithm development in the broader psychological literature. I can't help but wonder, those who do choose to sit in one quadrant, how many might choose to change and kind of diversify a bit more if they understood what they perhaps had to gain by perhaps visiting some of the other quadrants and what that might mean for their main quadrant. So sometimes I just wonder if it's an aware decision or just one that has been made less consciously, and what people might decide if they have the opportunity to. Okay, so let's start with quiet mind and body. So mechanistically, this supports the sort of introspective awareness, parasympathetic regulation, can function as a form of denoising and detect subtle, persistent signals masked by everyday noise. So for this particular example, we have restorative yoga to nature sounds and meditation to no music. These are just 2 examples of many. Selected because they fit well in the presentation and they're well supported in the literature. But really, there's a lot to choose from. If we step into active mind, quiet body, you see things like cognitive stimulation without physical exertion. This is linked to improved memory consolidation and cognitive flexibility. So things like journaling and reading. Then you have things like active mind and body. So you have embodied practices that require both movement and mental strategy. So it supports sensor motor integration, social coordination, rapid prediction updates. The examples we have here are martial arts and team sports. And then finally, we have quiet mind and active body. So this supports downregulation of mental activity while maintaining somatic engagement. This is associated with things like reduced rumination, improved mood, and enhanced default mode network regulation. So we end up with this framework that a number of people could play with, either the individual or a practitioner who is perhaps working with somebody to explore, okay, well, how might a person use activities as one of the ways to create a more adaptive sort of set of capacities within themselves. And again, this would potentially be one tool among many, as the human system is complex with a lot of layers. So some additional considerations. Yeah, this one I find pretty interesting, that it might be beneficial to intentionally include activities with higher levels of unpredictability or informational load. So especially because we're living in a time of so much uncertainty, really training this part can help cultivate resilience by reinforcing strategies for self-regulations and adaptive inference as a sort of form of adaptive training. Since I know there's a lot of academics on this particular forum, I'll mention one of my favorites is actually to go to unconferences. So imagine instead of showing up in a sort of domain-specific conference, an unconference is across domains, and you show up and there's a large whiteboard, and essentially you're going to fill in your talk. And so you're going to attend talks across a lot of different domains. And then in the evening, spend time together as a community, say like by doing a massive cooking project with complex social dynamics and loud music. Yeah, I just wanted to leave that here as I imagine if some of you are looking for ways to sort of stretch those quadrants, given this is an academic community, I wanted to share that potential one with you all. Okay, and then it's also interesting to think about the balance of variation, which activities might want to stay consistent, but also, does it make sense to bring in some variation as a way to extend the sort of adaptive training and to explore more nuanced patterns of engagement and build resilience within particular cognitive or physical modes? Great. So let's step into the discussion. So this body of work is meant to be this initial step that really contributes to translating active inference and free energy into forms that are conceptually rigorous and accessible. The framework induced here is intentionally adaptive, designed to involve in dialogue, real world use, and ongoing research. Its value is also intended to lie in the conversations, applications, and refinements it inspires. If you have any feedback, you can leave that at actincycle.com/feedback, and I'd be delighted to receive it. So this work, it relies on multiple sources of rigor. Perhaps the biggest is the existing research and foundational literature. It's been truly remarkable to step into that body of work and really see just how robust it is across different domains and methods. Dialogue with leaders in active inference and the free energy communities, as well as collaboration with experts across other domains, pulling in other types of knowledge and wisdom, and feedback from users and peers. It's also interesting to really think about the fact that humans often update through discomfort, but many avoid this tension, right? Making it one of the greatest challenges for implementation. So helping people update more effectively with less suffering may be a really crucial lever. Conclusion. Okay, so this is essentially a starting point for bridging complex theory and practical application. Accessible visuals and experiential framework strategy based on robust science aim to foster learning, engagement, and adaptive action. How can we make these changes? We might be looking in ourselves, whether it's desire to learn a new skill set or break an existing pattern of behavior. increase capacity, be a better leader, develop a new tool for somebody else. Like these are all intertwined, the same science stance, and meant to evolve through feedback, continued dialogue, and interdisciplinary exploration. The references, they're listed in the paper at actincycle.com/paper. And I want to take a quick moment for the acknowledgements. I'm super grateful for the group that came together around this. Carl Frinston for being the academic advisor and taking the time to really engage with the community, even when seeped in the more technical world. Ludo, who just was such a great designer to work with and iterate on some of these illustrations and motifs to really make sure we got those things right. And the colors, and just really helped build such a beautiful design strategy for this. Zach, who was the editor, we of course used AI as a complementary tool. Everything originated with humans and was the final stamped by humans and created by humans in the middle. But Zach really helped make sure that communication was very human. And then Sylvia, which I imagine you'll hear from other times, was a much appreciated reviewer and also did the initial lift on the 500 references in the book. I personally had a chance to go through them, and again, we'll just, I know many of you watching this have probably contributed to that space. It's truly a remarkable body of work of which to get to intersect and work with. So thank you for that. And I hope it's not too much for me to sneak in this last thing, but we saw in the earlier slides that it's really hard to make the economics of this work. So please consider supporting the work either through reviews, recommendations, acquiring a book, or providing feedback. Any of the above are very much appreciated. So thank you so much for listening, and I look forward to continuing the dialogue.
Okay, we're back with Matt Brown, Adaptive Robotics for the Real World, A New Paradigm for Autonomy, and a repeat symposium guest. So thank you for joining again, Matt, and to you for presentation.
Thank you so much, Daniel, and glad to be back. I hope I'm not giving anybody whiplash. That was a great talk by Anna, and this is kind of a big shift in topic and probably a bit of a provocative title. So I'm Matt Brown. Great to be here. I'm with a company called ThoughtForge, and we're doing something a little unusual. ThoughtForge began as a research project back in 2007, exploring alternate biologically plausible approaches to machine learning, and we're applying it to adaptive real-time dexterous control for robotics. Just a little background on myself. I've been working in AI for almost 25 years now at this point, including time in the defense industry, video games on franchises like Halo, BioShock, Splinter Cell, stuff like that. And then about 10 years ago, was an early pioneer in deep reinforcement learning. at a company called Bonsai, which was acquired by Microsoft. And the last 5 years, I've been really kind of focused on taking this interesting research technology and applying it to real world applications. So just a brief agenda about what I'm going to talk about. Last year, I gave a talk around the low-level mechanisms about what we're doing and the kind of the approach from the bottom up. And this year, I'm starting from the top down. I'm talking more about the current motivations and goals for the technology, how it's being applied, and a little bit about the methods. And I'm trying to keep it to more interesting aspects, more of the philosophical stuff. So I'm going to starting out by talking about robots and dexterity, why it's hard, and why I think a new approach is needed. Then kind of contrasting current AI approaches with deep learning, and then kind of just talking briefly about the techniques that we're using and our implementation. And then I'll show off some videos and applications that we've been working on over the last couple of years. So why are people trying to apply AI to robotics? And then I'm apologize for anybody in the audience here who's very familiar with robotics, because a lot of this is going to be super obvious. Traditional robots operate in controlled environments, doing repeatable things over and over and over again. And that's kind of what they've been really being good at for the last half century, roughly. And they haven't really been applied outside of that because the real world is messy, unpredictable, variable. Everyone's aware of these challenges, I think. What AI is looking to solve, or what people are using AI to try to solve, are three main things. Perception, understanding the world, understanding when things are not in their controlled state. Adaptive manipulation. People really would like robots to be able to do a lot of the tedious manipulation work that's done by humans around the world on a daily basis. And then generalization, being able to learn and adapt without having to be explicitly reprogrammed for every situation that they're in. And at least right now, AI seems to be the only viable path to unlocking robotics in these kinds of challenges. So let me just make sure I didn't skip a slide. Okay, so these are the kind of cutting edge approaches in AI that are currently being explored, and where there's tons of money. You probably hear about bunches of companies getting funding to go after AI and robotics. These are generally the techniques that they're using. Visual language models basically use LLMs to kind of ground vision and actions in through language. And there's some examples here with RT2, RoboGen, OpenVLA. And none of these solutions have yet been proven to solve all the problems or gotten to the point where they can be used in factories reliably or in homes. I should probably start out by saying that. And so, each of these have their own challenges. With visual language action models, they have poor action fidelity, so they're very kind of poor quality motion. And also language is not necessarily the best way to understand the physical world, and they're also very non-deterministic, and so it's very hard to know with confidence that they're going to be able to accomplish a task reliably. Diffusion-based control and planning, this is basically using techniques from image generation or video generation, where they use kind of diffusion from noise to generate images. They're doing the same thing for robotic trajectories, for generating motion. And there's sometimes this is combined with visual language action models and with foundational models, so people try to mix and match. Right now, this is very, very ripe for a lot of experimentation. The problem with diffusion is that you need really, really high quality data, and that's really hard to get. The simulations usually are not good enough, so people are teleoperating the robots, so you'll see a lot of that to generate the data, but that's also a very tedious way of getting data. It's also very expensive to actually use in the real world. And it's brittle to distribution shift, so anything changes, anything about the task changes or the objects change, and then the policy stops functioning well. And the last one is kind of a broader goal, which is the foundation models for embodied intelligence. And this is generally people trying to create a ChatGPT moment for robotics, where if they get enough data about physical manipulation in the physical world, you'll get to some threshold, and these AI models will suddenly understand how the physical world works, and then you can kind of use that as a base model to go after individual tasks. And the problems here are somewhat obvious. The amount of data that you need is enormous. The amount of compute that you need is enormous. And I don't know if I talk about it in the next slide here. I was going to talk about how challenging the data problem is. Actually, I'll just move on to the next slide. These are the main problems with the traditional approaches in AI applying to robotics. And for the most part, data is the biggest problem. There's just not enough. There's not an internet of data, of robotics data that to train on the way that ChatGPT might have. And there's a lot of different embodiments, different numbers of actuators, different kinds of actuators, different kinds of sensory input, vision, tactile, force, proprioceptive, and every robot is different. And so getting enough data that can generalize across all different kinds of robots in the physical world, we just haven't gotten there yet. And the example I like to give is self-driving cars. Self-driving cars are finally getting to the point where they're usable and they're functional, but it's taken over a decade of data collection, billions of miles of road driven, and that's just to handle one use case, driving a car. As opposed to the expectations for robotics are that they're going to be able to do everything, clean your house, work in factories, and so the mismatch here between the data set sizes and the expectations are really quite large. And there's same problems that you have with self-driving with long tail variability. It's very hard to simulate reality accurately. There's just anything can happen. And similar to self-driving cars, in fact, when one of these models fails in the real world, it has very expensive and often dangerous consequences. The other problem is compute. The amount of compute to actually run one of these new age models is absolutely astronomical. And robotics have real-time constraints. They're latency sensitive. So if ChatGPT takes 5 seconds to give you an answer, that's not a problem. But if the robot's in the middle of manipulating something and it takes, more than a fraction of a second to make a decision, you probably have broken something or dropped something. And so the performance constraints are much more challenging than in language. And this is one of the reasons why AI in robotics is so challenging. This also means that your AI model can't live in the cloud. That means that your AI has to be small enough to be on a computer right next to the robot, because you just can't deal with the latency that you get from working in the cloud. So the biggest challenges here for AI and robotics still exist in that they don't really adapt to real world variability in the way that they need to. And so what we've been working here at ThoughtForge is a kind of a new way of looking at the AI problem in general, using cybernetics as kind of the original body of theory that we're working on. And obviously there's a lot of connections between cybernetics and active inference. And I'll go into that a little bit later in a couple of slides, a little bit more thoroughly explaining that relationship. But when I started kind of looking at these problems, and in fact the learning problem, I was very curious about how nature solves these problems, because obviously we exist in the world, animals exist in the world. How do animals kind of deal with these problems? And they don't do it with huge data sets and huge computers training on that data over a long period of time. And they don't just train once and then hope that they can generalize. And in particular, animals don't separate learning from acting. It's kind of concomitant and it happens at the same time. And so this is just kind of contrasting here. The kind of paradigms for what people are looking at with AI currently and what we should be looking at and what we're kind of at ThoughtForge are kind of attacking. Continuous feedback loops for perception and action simultaneously, adaptation at the point of contact, and learning shaped by physics and active inference and the free energy principle are kind of foundational principles and theories around that. And the idea here is to leverage learning in the moment versus learning in the past. So just to kind of dig into that a little bit deeper, most AI systems today are focused on prediction and are giant prediction systems. And so the approach we've taken is a huge shift over these old-fashioned deep learning approaches. I'm terrible at naming. So deep learning is, you can look at most deep learning networks as universal function approximation. So what you're doing is you're taking huge piles of data and then approximating that into a function, an input-output function. I've called what we're working on inactive synchronization. I'm terrible at naming. I guess there's a quote, there's two hard things in computer science: cache invalidation and naming things. And we may have mostly solved cache invalidation, but I haven't really quite figured out naming things. This is my current favorite name for our approach, inactive synchronization, because I think it's detailed enough and specific enough to be useful. Other things I've thought about calling it is, but are related, but maybe too generic and don't really give much insight, is generalized synchrony, cybernetic learning, metastable adaptation, things like that, homeostatic intelligence, or manifold synchronization learning. These are all accurate, but perhaps not as specific. And what I mean here by inactive synchronization is that it's a synchronization process with kind of an active tint to it. In that inactivism is views cognition as a dynamic interaction between environment and an organism. And the world model that's created through this process, through the synchronization process, is co-created through interaction. Model and control are kind of intertwined. And so the world model itself is constructed of sensory expectations and motor control percepts, essentially. And so these are kind of intertwined. And so this world model is created through interaction and created by the control dynamics themselves, or they emerge from the control dynamics themselves. So other ways to look at this is universal function approximation. Current deep learning systems are retrospective. They basically take past data and to approximate functions. And what we're doing is prospective equilibration, basically continuously adjusting to maintain predictive coherence. And maybe this will make more sense once we get a little bit more into the details. But traditional approaches are very data dependent, time agnostic, and feed forward, meaning they're input output functions. So once you have an input, it computes and generates an output, and that output is directly related to the input. And there are ways of making it with recurrent neural networks and things like that where it has some history. But for the most part, every time there's an output, it's a direct response to an input. This is very, very different. These are time aware, which means input signals are coming in, output signals are going out, but the output signals, the motor controls, are not directly a computation on the inputs. They are, you can think of the model both generating, predictions about their sensory experience and motor controls at the same time. And then where the sensory expectations are incorrect, they kind of filter through the network and modify future outputs of the network. So very different way of looking at the learning problem. And the goal with the inactive synchronization here is to build up this model of the world that can kind of predict how the world is going to react to your motor actions. And then the goal of the motor actions here are really to get change the world to become easier to predict or to put you into a preferred state. And a lot of this aligns very, very well with active inference, obviously. But this kind of gives kind of a high level philosophical view of what we're doing from the top down approach. So this is just a very, very quick slide to connect the kind of cybernetic approach with active inference. And obviously these are very closely tied together. The free energy principle is, I probably don't need to go into it too much, but it talks about how all living systems act to minimize their free energy, basically pulling from physics a lot of these really great ideas about how the natural world works. And then active inference is a framework within free energy principle explaining how organisms actively gather information to reduce uncertainty and maintain internal stability. This is kind of the kind of connective tissue into cybernetics, because cybernetics was a field that's kind of disappeared in recent history, but built upon the same ideas, where it provides kind of the theoretical foundation for how feedback and self-regulation leads to this minimization of predictive error and this kind of self-regulation, self-maintenance process. Digging a little deeper, our specific techniques are modeled around a cyberneticist known as Ross Ashby, and he had some really kind of foundational ideas. He's most known for the good regulator theorem and the law of requisite variety, which are both related to each other in some sense. And the good regulator theorem is, basically says that if one system wants to regulate or control another system, that system has to have or be a model of that other system. And the law of requisite variety is somewhat similar. If you want one system to kind of control another system, it has to be at least as expressive, or it has to have at least as much variety as the system it's trying to regulate or control. And he saw homeostasis as kind of the goal of stability, as kind of the universal mechanism for adaptation in the natural world. And so he built a device in the 1940s called the homeostat. It's very, very small, and I'll talk about it in the next slide a little bit more, where he kind of demonstrates demonstrated adaptation as stability, or stability as adaptation, and it uses feedback between the units to kind of generate a distributed homeostasis through a local property called ultrastability. So basically, he had these nodes that in a network. These were built out of World War II bomb parts. So this is pre-digital computer. He was using doing pure analog computing at this point, using recycled bomb parts. And each node is basically performing this property called ultrastability, and when networked together, generate distributed homeostasis amongst the group. And you can kind of look at the network as a self model, where each node in this network is trying to predict its neighbor's nodes. And if all the nodes in the network are doing this, you kind of reach this equilibrium, this homeostatic equilibrium over time through this ultrastability process. So just to talk a little bit more about the homeostat, because it is incredibly important to our techniques and what we're doing. It was the first device kind of capable of adapting itself to the environment. I guess, depending on how you want to look at it. It exhibited behaviors such as habituation, reinforcement, and learning through its ability to maintain homeostasis. He kind of viewed homeostasis as the fundamental mechanism for adaptation in complex systems, and he basically built this device to kind of show it off, kind of what he was thinking. And it was very kind of primitive at the time, but I think for the most part people didn't really really understand what's going on here. But at the low level, in terms of what he was trying to solve, there's a lot of what they're trying to solve with reinforcement learning right now was kind of exemplified in the system. And to contrast this with going back to kind of the 1940s, models of the mind and things like that, deep reinforcement learning now, and a lot of people don't know this, is loosely based on B.F. Skinner operant conditioning. And so really kind of old-fashioned ideas kind of put into computer science is what we're dealing with now. I would like to think this is a little bit more forward-looking in terms of concepts for how learning works. This was also described as an isomorphism generating machine, which is obviously useful when you're building a world model and you wanted to kind of abstract concepts in the world as groups and things like that. And I think I've already talked about how ultrastability generates homeostasis. Here's just a more in-depth look at what it was. You can see a picture of it right there. By the way, this is Ashby himself posing in front of his homeostat, in case anybody was curious who that person was. That's a picture of the homeostat there. These big clunky things made out of recycled bomb parts. On the upper right there, you can see just kind of a network diagram of what was going on. So basically each node in the homeostat was connected to all the other ones, and they also had a self-connection. And the diagram on the lower right there is meant to describe the mechanism of what's going on with ultrastability and how these nodes update. So in deep learning, the nodes in the network are perceptrons, kind of actually probably 5 or 6 years before the homeostat. It's kind of funny that all these chaotic attractor definitions came out of the same decade in human history. But so this was just half a decade later than the perceptron was this kind of model, and how they differ is that chaotic attractor definition. And so it's very similar to the perceptron in the sense that you have incoming signals or incoming connections from other nodes with weights. But how we actually update the network is very, very different. These obviously don't use backpropagation. Instead, they use this ultrastability. And so another way to contrast deep learning with this kind of homeostatic network is that in deep learning, this backpropagation process is a global update. You have to freeze the network, not use it, do a global update of all the nodes through backpropagation. With ultrastability, the update step is local. So you don't have to freeze the whole network. The nodes are continuously performing this ultrastability process in parallel. And so this works a lot better for large networks. Especially if you're trying to implement this on computing hardware, you can kind of distribute your network across computing resources, and you can kind of update them independently of each other. Because of the way that the connections are all recurrent, you can kind of think of this network as trying to predict itself. If each node is trying to predict its neighbors, the kind of group itself is building a kind of a self-prediction model. Ashby never actually connected this to external control systems or sensors, and so the base homeostat was really just trying to show how this equilibrium, this homeostatic equilibrium, could be reached in kind of a mechanistic way. So I just like to include this letter in here in my talks just because it's a fun little piece of history. At the time, Ashby and Turing were I wouldn't call them rivals, but Ashby was very much pushing for analog computing, this homeostasis way of building computers and computing machines, and Turing was very much about digital computation. And this is a letter from Turing to Ashby, basically saying that his universal computing machine is more general than the homeostat because you could simulate a homeostat on a universal computing machine. And while this is true, I think they're missing the point. This is kind of the original analog versus digital argument. And at the time, analog systems didn't really, complexity theory hadn't been developed, and so stabilizing analog systems hadn't really been figured out in terms of how you can use negative feedback to make them reliable and things like that. And so I think they're kind of conflating two things that I think are still being conflated here, where computation is not the same as, for lack of a better word, cognition, or universal adaptation is different than pure semantic computation. And we've kind of, I feel like this paradigm that we're seeing in AI with all these different approaches are really just pushing further down that semantic computation direction, as opposed to understanding what's actually going on in intelligent systems or complex systems. And so I feel like this is the beginning of this divergence in beliefs about how we should build a computing future. Obviously, Ashby lost this argument at the time. Turing, everybody knows who Alan Turing is, but it's a fun little tidbit I like to include. So how do you actually build one? There was one physical object built. I think it's still in existence somewhere. I think maybe the Ashby family has it. I'm not sure. But I basically took Turing's advice in the last letter here and simulating. So I'm using a modern Turing machine and simulating it and simulating the homeostat as an analog system in there. This is based on techniques. Before I got into all this stuff, I was an early pioneer in what's called software radio, which basically was I don't know if I would call it a science, but a field around how do you properly simulate analog systems in digital hardware in kind of accurate, in physically accurate ways. And so I use a lot of those techniques to build the first prototype. And one thing that's interesting here is because of the chaotic interactions between these nodes in these systems and the way that the homeostasis generates, is that you can't analytically calculate the network, and so you kind of have to simulate it step by step and let it evolve over time. That's what I mean here by you can't account for the interactions algebraically. The circularities and the recurrence really have to be kind of play out iteratively over time. And there's a great quote here about from Prigogine about complex systems. Don't forget their initial conditions. They carry their history on their backs here. And what I'm trying to say here is that the structure of how the system evolves itself stores within it a memory of the history of how it got there. It's a lot like how a snowflake itself is structurally a history of the temperatures and pressures that it went through during its formation. In the same way, these systems are also very complex and unique. Every time you run one of these, the way that it stabilizes is always unique, kind of like a snowflake. But the end result that you get there kind of contains the history in a way, in a very kind of compressed way, and that's kind of a property that we want in a world model, our dynamically generated world model through interaction. So I started with kind of Ashby's in terms of how to actually build this. I started with Ashby's kind of physical descriptions and analog hardware here. Some of this came from his technical journals, which were digitized almost 20 years ago. Some really great stuff. It's all handwritten, so be prepared to read his handwriting. He's got some amazing illustrations in there, but it's about 7,000 pages of technical journals, and so there's some gems in there if you're patient. So I started by pouring through his stuff and building kind of a very accurate simulation of the homeostat, and then over a long period of time, abstracted it down and simplified it down to something that looks a lot more like modern AI networks, where you can kind of build these into abstract shapes and topologies. And each node is doing the same thing. It's basically trying to predict its neighbors as the system as a whole reaches equilibrium. But you can think of this as kind of a loosely coupled set of dynamical systems. Each one of these is a homeostat, an abstract homeostat. Yeah, I'm trying to think how much I want to dig into the dirty details on this slide here. you can kind of imagine that this is still disconnected from an environment. So we haven't yet, in at least at this point in the slide, connect this to an environment with sensors and motors or anything like that. So really all it's doing is, when it's reaching equilibrium, is finding a set of positive and negative feedback loops. You can imagine these connections in the network here forming a large set of overlapping feedback loops. And depending on what the value of the weight, some of these are positive, some of these are negative. And what's going on through this local ultra-stability process is that they're searching a state space here of positive and negative feedback loops, such that they all are self-balanced. So all the, once you reaching equilibrium, it's not a quiet equilibrium in the sense that it's very much active. In that all of these feedback loops are very perfectly balanced, so that they're stable. And this, you can kind of think of this as a critical state. And this is really important because it means that the slightest change or the slightest new piece of data can completely destabilize one of these feedback loops and cause cascading changes throughout the network. And as long as you can kind of restabilize the network quickly, this is great. That means that one small piece of data can drastically change the dynamics of the model. And that's what you want in a system. That's the opposite to backpropagation-based systems, where you need a lot of data in order to change the behavior of a model. Instead, you want one surprising piece of data to drastically change how the model behaves. That's much more data efficient. You need a lot less data to get to a useful world model this way. Let's see if there's anything else that I want to talk about here. In terms of how this relates to active inference, when it's reaching equilibrium here, what it's trying to do is it's trying to minimize the prediction error of its prediction of its neighbors. And so once you're at equilibrium here, you're basically at zero prediction error, and all of the networks are successfully predicting each other. So just at a high level, I'm going to spend a couple of slides on these next few topics here. First is, how I actually connect these to an environment through sensory motor coupling. Sensors and motors kind of define that interface between the environment and the model. Then I'll talk a little bit about embodiment and why this is important. And in fact, I think, to me, the most important aspect of embodiment is the existence of time in the system, the time awareness of it. For me, I have a hard time looking at traditional deep learning AI models, even in robotics, where you have a body being embodied because or considering them to have embodiment because they're time agnostic. They have these input output functions, and they have no concept of being situated in not just in a place but in a time, where their last action that they took is relevant to the current one, for example. And there are ways to trick this by feeding, especially in reinforcement learning, this is often what you'll do, is you'll feed in your previous inference results as inputs to the function. But I think of that more as a hack. And then I'll talk about a little bit about synchronization as a learning process itself, in case that's not super obvious. So once you've built a homeostat, even a large one with a large topology, it's still kind of boring. All it's doing is kind of learning itself and learning to get to equilibrium. So one of the first things you have to do is, and so it's self-synchronizing. You can kind of imagine it as a self-synchronization process. So the next thing you have to do is, if you want this to do something useful, you have to connect it to an environment. And so sensors kind of define how the agent is embedded in the environment, and the topology itself defines what the adaptive capacity of the homeostatic agent is, what it can do and what it can learn. Obviously, the larger and more complex the network, the more expressive and more complex behaviors you'll get out of it. And then the sensor definitions, we've kind of, I call them sensors, but maybe they're inputs. I'm not great at semantics here. Naming things are hard. The sensors here are actually really important because they also act as teleodynamic priors in terms of getting this to do something useful. You basically can define what the homeostatic set points are in the sensors. So the sensors aren't just data. They're not just, pixels coming in, but they have they have goals implicit with them. And an example might be, instead of having a temperature sensor that's just saying 68 degrees or 70 degrees, instead it's saying, I am 2 degrees away from optimal, or I'm 5 degrees away from optimal. So the idea here is they have kind of implicit goals in them. And those can be seen as like input attracting sets, which you can kind of, from externally, you can modify those in real time to get more interesting behaviors and to kind of change what the model is doing at any point in time. The motor definitions here are basically just coupling points that go outward. So inside the network, there's a lot of recurrence, a lot of bidirectional connections. The sensors are almost by definition input only, so they're unidirectional, and the motors are also unidirectional outward. And they basically provide an affordances to the network for modifying the environment and it provides the basis for future sensory predictions. You can imagine the network here is basically trying to generate motor outputs that help satisfy the input goals, and so the preferred states of the sensors become the preferred outcomes of the motors. And so you kind of have this synchronization loop that goes outside of the network. So the network is doing self-synchronization. And then once you connect it to an environment with sensors and motors, that synchronization manifold basically extends outward, and it basically is performing a kind of homeostasis through the environment, outward through the motors and through the sensors. The model kind of imagines what it wants and what its preferred state is from the sensors, and then generates motor actions to kind of drive it towards that state over time. Like I was saying, I think embodiment is a critical feature of what we're building, and I think the missing piece here is time. So in these networks here, there's no forward or backwards propagation because there's so much recurrence. You can't really define a front or a back or a top or a bottom. Signals just propagate in all directions. The closest thing you can get to is distance to the environment. So how deep into the network you are and how far away you are from a sensor or a motor. This is not like the sandwich model, I guess is what people like to say, where you take input, you compute it, and you generate output. Instead, information is flowing into the network from the sensors, and actions are kind of flowing outward from the network through the motors. But once the information hits the network, it just starts bouncing around in all directions depending on the network topology. You update the network and information flows in all directions. And through this kind of, when you're reaching equilibrium and you're hitting this state, that's when you can consider that the network is successfully predicting the sensory inputs. And whether or not the motors are contributing to that depends on the specifics of the motors and the sensors themselves. But the expectations of the sensory information here becomes embedded with the motor actions themselves. So the idea here is the network, while it's generating sensory predictions towards the front of the network, it's also generating motor actions to the motors, and these are kind of happening in parallel. So as it's updating its model to better predict the sensory information, it's also updating the motor actions that are being generated. And so the kind of the motor actions and the sensory expectations kind of get intertwined in the network here. And this is why I like to call it the inactive synchronization process, because these are kind of being co-created as part of the model, the world model that's being direct. This is if those familiar with predictive processing or perceptual control theory, this will look very kind of familiar in terms of how this actually works. Finally, I figure I'll talk a little bit about synchronization and thinking about homeostasis and prediction and where the prediction errors are. If you kind of imagine the drive towards homeostasis as kind of a goal, the distance you are from that equilibrium could be seen as like a prediction error. And so you're basically trying to drive this prediction error down. And this becomes more obvious if you actually look at the chaotic attractor definition in terms of the way that you're taking a weighted multiply of your input signals, and you're trying to get that to be zero. You're trying to basically predict that what your neighbors are doing, and a successful prediction will result in a local prediction error that is near zero. And when the network when this happens, you can kind of think of it as a synchronization process. When you can successfully predict your neighbors, you're kind of synchronized with them. You know what they're going to do before they do it, and so that's how you can have the sensory expectations meet the sensory inputs through a synchronization process. And synchronization is kind of magical. Once you have two systems that have synchronized, or let's say you have multiple systems synchronized, and you can imagine each node in here is synchronized to its neighbors, and so you kind of have this synchronization over a distance. That's a way for two systems that are not in direct communication to coordinate their behaviors. And so you can kind of get very interesting collective behavior out of these networks, collective here of the nodes, through the synchronization process, where each individual node's behavior is going to be consistent with or coordinated with distant nodes in the network. And so this is a very important aspect of how these functions work, because if you had to, if two distant nodes that are representing different aspects of the environment had to be in direct communication all the time in order to maintain their correct modeling of the world, this whole system would become incredibly computationally expensive and impossible and intractable. So the synchronization process is very important. I think I talked about previously how this is maintained at a critical state. And so the smallest prediction error that's coming in through the sensor can have cascading effects through the network that cause very, very fast destabilization. And so the trick here is to synchronize faster than the environment can destabilize it. So if you're updating your network too slowly and the environment is changing very, very quickly, you're going to be constantly in a state of chaos. But if you can update your network much, much faster than the changes that are being experienced in the environment, you can imagine that this network is able to resynchronize and restabilize continuously over time faster than the environment can. And this goes back to kind of Ashby's law of requisite variety. And the idea here is that the variety that's being generated is very much time dependent and depends on the rate of change of the environment versus the rate of change of the network. But the trick to this is ultra stability is very, very efficient, and then we can run it really, really quickly. And in most of our robotic applications, for example, these networks are operating usually around the update state, the update rate of these individual nodes is for a robotic application, usually between 5 kilohertz and 50 kilohertz. So we do this very, very, very quickly. And depending on the application and what's being done, that's generally fast enough to maintain the synchronization manifold between the model and the environment. It's a prediction error minimizing synchronization manifold. But if you run the network that fast, you're able to basically maintain this synchronization manifold over time. And that's how we kind of get useful behavior. All right, I think I've talked enough about synchronization. Now I'll get to the fun stuff that I started up talking about the beginning here, where the killer application for this kind of learning approach, this adaptive approach, really is robotics. Early on, we kind of considered different applications of this technology for like anomaly detection or even analyzing model drift in AI or deep learning systems, for example. But the challenges in robotics that AI is facing right now are really insurmountable with the amount of data that they need. And at least in my opinion, I'm not sure they're going to get there in the next decade. And they call it a sim to real is the other problem. So if you train a robot in simulation, because the simulations are not entirely physically accurate, transferring it to the real world is a big problem. But doing the learning post deployment in the robot solves a lot of that. A lot of those challenges. It doesn't solve it, it more sidesteps it because you're doing the learning in the real world as opposed to in simulation. So this is just a quick look at some of the industrial applications we've been doing with this technique. These models are entirely using homeostats to do the robotic control. These are some of the more recent ones that we've been working on. On the left here is an insertion process for automotive manufacturing, where we're kind of inserting small rubber parts into in this case, a door latch assembly. We've also been looking at connector insertions for cables and cable manipulation. And on the right here is an older model that we built for turning valves and bolts. This was, I'll talk about each of these in the coming slides here. This is the one on the right here we take to conferences. It's a small little robot, and we let people kind of move it around and let the robot figure out how to turn the bolts as people are kind of playing around with it. So this is one of our first models. We built this several years ago, and this was originally designed for doing inspections on a moving vehicle. And so the vehicle could be bouncing around, and they needed to kind of point the robot at something that's being inspected as it's being bounced around in unpredictable ways. This was originally designed for solar farms. But can be used, and we use this as kind of a base model for all sorts of stuff if you just need a robot that points at something. Next, we started working on more manipulation use cases here. This was also originally done for the energy industry. They wanted to see if we could automate the turning of valves. You never know what size or shape a valve is going to be in a facility. And sometimes there are injuries. If these are high pressure gas valves, for example, they have, people get injured and killed very frequently. So, that's a great thing to do for a robot to do, is something that's dangerous. And so we would turn this into a demo that we bring around to conferences sometimes, and we would let people like move around these bolts while the robot tries to turn them. And it's kind of fun. People like to play around with the robot and torture it a little bit. And there are also not very many interactive robotic demos at conferences. This is another video of this conference demo, and I included it because it has this video here on the right. So that's our actual homeostatic network debugger, but you can actually see the network updating in real time here as people are jerking around with the robot here, torturing the poor robot while it's trying to turn a bolt. And people like to watch it's an internal debugger, and so we built it as a tool for us, but people like looking at it while they're actually playing with the robot. This is some more recent work, and I'll show what the final result of this ended up looking like. This was for a project in automotive manufacturing where they wanted to basically insert tight-fitting rubber parts. And the problem is you can't really do this with vision inputs alone because they're tight-fitting, and humans are really good at this. You can kind of feel your way through it and kind of wiggle it in really easily. And so that's essentially what we're doing. There's a force torque sensor in the wrist, and in these videos here, we're actually not using vision to guide the process at all. So we basically tell it, and we're actually telling it the wrong location. And we're telling it the wrong location, usually between 2 and 5 millimeters of error in like a random direction. And it's using the force sensor in the wrist to kind of feel its way through the insertion process. And the one in the bottom left there, you can see where it kind of has to, it catches an edge and then it figures out that they can insert it, and it kind of pushes it in. But we're basically using the same model for all these parts. So one of the big goals of this project was to show that we could build one model for insertion and have it work across a large variety of parts. With traditional AI, in a lot of cases, you'll have to build and train with separate data. Each of these would be a separate model for each part. And that's a problem in manufacturing because these parts change every year or two. And what they don't want to have to do is generate a huge data set every year or two when the parts change. And there's also about 500 of these parts. So they'd have to build a lot of part-specific models to do this. And this is just a video showing what this actually ended up looking like when we finished it out. And so you can see that in this case here, we've integrated the gripper. We are using vision to figure out where the insertion housing is, but it's using the force torque sensor in the wrist to kind of drive the rest of this process. And in case I hadn't mentioned it, so essentially we're using the homeostatic networks to kind of do the control here. So as it's doing this wiggling in, it's basically looking at the forces in the wrist, and we've basically given it the goal of trying to minimize the lateral forces and things like that, and maintain that the insertion, the force vector is perpendicular to the direction of insertion, for example. And it just kind of as it's trying to do the insertion, the network is constantly updating its understanding of what it's doing and modifying its insertion, modifying its behavior to perform the insertion task here. I'll give it one last second here. There's one more part. This is showing all 4 parts being inserted back to back using the same model. So we're not switching models here, like I said before. I'll just let this finish real quick. Hooray! All right, we inserted all the parts. And then this is some more work that we've done recently along similar lines. This time inserting, I'm not sure why. Wait, let me see. There we go. I just hit the button twice. Doing insertions of various cables. So we're using a single model here to insert cables. In this case here, like a 15-pin, parallel cable and then an Ethernet cable. And the idea here is this should generalize to different kinds of cable insertions. Again, this is using force to kind of drive the insertion process here. So even if the vision system is not entirely accurate and it's giving a location to insert that's incorrect, a couple millimeters off here and there, it's able to basically figure out how to actually insert the cable in the right spot. And we're continuing this work right now in more interesting cable manipulation cases here. So the insertion is one part of this. The next step is being able to manipulate the cable around, untangle a little bit. Cables are very, very challenging to work with. This is why we're working on it, is because this is very hard to automate with traditional robotics. Anything can happen with cables. They can get caught, they can get tangled, they can be in places you can't reach. So you might have to pull another part of it to get it into in a place you can reach because there are obstacles and things like that. So that's kind of where we are with applications of this stuff, and super excited about the next year and what we're going to be doing in the future. That's the end of my talk. Thanks. Thanks for having me. This has been great.
Thank you.
And feel free to reach out if anybody has questions or anything. Happy to hear from you.
Very cool. Okay, I'll just ask any of the questions that are written in the live chat. All right.
Oh yeah, I should have been paying attention to that. I'm sorry.
Oh, no worries. I'll read it. Okay, so Ready Player Sid wrote, "Are we headed into a decade of teleoperation telerobotics, What is the next decade of robotics going to look like with respect to embodied AI?
I mean, a great question. I think we are. I think just in the last year, I feel like I've seen at least 50 to 100 startups that are doing teleoperation or selling teleoperated data or selling systems to do better teleoperation. One of the reasons why we went after soft body insertions, for example, is because tactile data and force data is very, very hard to get. You can't really get accurate data in simulation, and it's if you need to train a deep reinforcement learning model, you really need accurate data for that. And there's obviously doesn't exist out there. That's why a lot of vision models don't, the visual language models don't have any kind of force data in there. And so, for example, I've seen just like 10 startups in the last year that are providing tactile data collection for teleoperating. So they're still using teleoperation, but they're not adding force sensors and tactile sensors to the robot so they can collect the data during teleoperation. But I think if the money keeps going in that direction, that's what you're going to see. And I think that's what you have been seeing in a lot of cases here. There are a lot of startups that are just hiring people to do a task over and over and over again, and then they'll train a model to do that task. And often what you'll see is you'll get a successful model that can fold a napkin or fold a towel, or I'm sure those are the ones that are coming to mind. But whether or not that model can then be translated to a different shaped towel or a shirt is questionable. Mostly because of the science, and so you'll have to teleoperate to collect data for a shirt instead. But there's so much money involved. That's the direction that people seem to be going. Like, people don't seem to have a problem with spending $100 million paying people to teleoperate robots day and night. I've even seen a startup where what they're not even selling AI. What they're doing is they're basically, you rent a robot for like $10 an hour to like operate your shop, or I don't know, let's say I have a corner store, have a robot operating, and then it's literally they're just paying somebody in another country, $2 an hour to operate the robot, and that's literally their business model. So I think you are going to see a lot of this, and there's going to be a lot of smoke and mirrors. I think I'm a little bit biased. I obviously think that there are better approaches, and I think eventually the hype will die down, and people will realize that we'll need more efficient and better world models, and that's what I like to think that we're building, even though it's kind of an active world model, and that the world model is comprised of sensory inputs and motor controls kind of intertwined with each other. So it's not the same kind of world model that most people kind of envision in their minds, but I do think it is one that is relevant to a robotic task load. Anyway, I kind of got off topic there, but I like to think that there are going to be better approaches, kind of like what we're doing here, that will take over at some point here when the economics pan out. I think with self-driving cars, for example, the value of having a self-driving car, the ROI there is high enough that it can justify spending a decade of collecting data. But for things like inserting rubber parts for automotive manufacturing, that ROI doesn't exist. Like, you can't spend a decade collecting insertion and teleoperated examples and have it be worthwhile in the end. So I think once you want robots to go after kind of lower value problems like that, and it's still highly valuable, but just not as much as a car that can drive itself, you're going to need different techniques. That's my opinion.
Cool. Okay. I'll read another question in the chat, and people can write if they have more. Question 2 from Sid. Why do DeepMind Robotics and other companies such as Figure take other approaches when it's so obvious adaptive models are better in so many ways?
That's a good question. I think it's because it's a clear straight line to something that they can imagine working, and it's an approach that they're familiar with. Backpropagation is, like, perceptrons have been around forever, but backpropagation has been around for 30, 40 years, which doesn't sound like, I mean, in the history of man, it's not very long, but like in the AI world, that's a long time. In which case, what I mean by that, I guess, is you have like multiple generations of people trained in that paradigm, and people understanding how to do that paradigm. So it's very comfortable, and people can just hand wave around. Oh, if we get enough data, we'll get there. I think the reasons why other like approaches with other implementations of active inference, for example, that are adaptive, don't have the scalability that they are looking for, and yet. And so I think it's easy to dismiss. I think the tide is turning, though. I think people are becoming much more aware of these other approaches. Our approach using homeostasis and Ashby's techniques is very unique. Like, as far as I'm aware, I don't think anybody else is doing this. And so, the reason why nobody else is doing it is because they don't know it exists and they don't know how to do it. And if I'm going to be honest, building getting that chaotic attractor, that homeostat, that ultra stability definition is very, very hard. Like I'm an engineer by background, and so I built my career around taking theory and turning it into real engineering. And it's challenging. It's hard. I want to say there's probably been about a half dozen attempts in the last 80 years to build a useful homeostat. And having looked at them, I disagree with the implementations. I think there are problems with each of them, but it's all subjective at this point. There's no definitive homeostat that you really just have to kind of look at the properties and argue that it has this property or it doesn't have that property. So I like to think we have something unique here and special, but and that would explain why nobody else has it.
Okay, and Sid with the hat trick. What kinds of adversarial cyber-physical attacks are possible on ThoughtForge robots, demonstrated in the video that use adaptive models?
I hadn't really thought about that. And I would like to think that, it's something I haven't really thought about too much. The models themselves are robust to like sensory noise, like, it's kind of inherent in how the algorithms work. And so if you have noisy sensors and things like that, but if you can like straight lie to the sensors and you tell it that the world exists, the world as it exists is different, that would, that would certainly work. And I guess, cyber attacks and cybersecurity, there's lots of different ways of looking at that, and if you get access to the code, it depends on what you want to do. But it would be pretty easy, for example, or not easy, it would be possible if, for example, like let's say we have an insertion model that goes and picks up a part and does an insertion. If you're somehow able to trick the perception system into thinking that a person was the part to be inserted, it will very happily go and try to grab that person and insert them. And obviously, this would be very dangerous for the person. So there's no if you can alter the perception of reality for any of these models, then you can get them to do whatever you want. And that's kind of how we're getting to do something useful in the first place. If I'm going to be honest, the way that we've defined the sensory inputs, where we're kind of implicitly putting teleodynamic priors, we're putting our goals in those sensory inputs, specifically so that we can control them to do something useful. Because otherwise, a homeostat will just kind of sit there. If you disconnect it from an environment, it will reach equilibrium and do nothing. And so the way that we're actually getting these things to do something interesting in environment is by manipulating its perceptual experience, which, I guess the moral and ethical consequences of that is probably for a larger talk.
Yeah. Very interesting and connects with this tension of the expectations for like a sensory prediction to be veridical but also actionable, because just veridically predicting is being a spectator, it's passive inference, but then that is the question of how much to have that kind of biased counterfactual homeostasis that takes you into the step that you need to go towards.
Yeah. And maybe there are ways to protect against that by having higher order teleodynamic priors, where the goal, instead of inserting a part, is to construct the part or construct the car. And so maybe then it can evaluate the effectiveness of its subtask of like, oh, is this thing I'm inserting actually going to get me closer to building a car? That might be one way out of it. We're not there yet with our technology, but I think from like a theoretical perspective, I think that's one way to approach it.
Cool. And then sort of in closing, any last thoughts, of course, and just what do you see for robotics or active inference? What are some of the constraints or limiting steps right now, and where do you see things updating or changing in 2026?
Oh man, that's a hard prediction. Robotics is super exciting right now. There's tons of stuff going on. I'm super focused on like practical applications, building the business, trying to make sure that this is an economically viable approach. And so that's where most of my energy tends to get spent. I'm super excited by all the traction that active inference as a field has kind of made in the last year, just in terms of public awareness. And I think if the AI bubble bursts, I don't know if it's ever going to burst or maybe just deflate a little bit. I definitely think there's a hunger out there for new approaches. I think right now people are starting to see that even LLMs with their huge capabilities and what they can do is super useful, super interesting. There are limits. At some point here, language will not get you everywhere, and is not what's going to get you to, truly, intelligent software, if you want to put it that way. I am much more lower. I'm not trying to create Rosie the robot for your home. I'm trying, if I have a lofty goal, I'd much rather make ants, because they're capable, they can build stuff, they are loyal to their queen, and like you don't have to worry about does the queen of an ant colony worry about the ethical consequences for its workers? Maybe not, but I feel like that's a much more lofty goal than trying to create sentient, AI and AGI, which is a lot of what you hear on from Silicon Valley these days. And to me, I don't think we need that. I think what we want is, machines that can take away the dangerous, dreary work that nobody wants to do. That's what I'm looking forward to.
Very nice. Thank you, Matt. So, thank you for joining the symposium again and for helping on the scientific advisory board as well.
Thanks. I'm looking forward to next year.
All right. Peace. Bye.
Cheers.
All right. Next is going to be a 33-minute recorded talk by Maria Luisa Janica. Here it goes.
Hello, everybody. Thanks for having me in this wonderful symposium. My name is Maria Luisa Ianaco, but you can call me Maria. I am a PhD candidate in philosophy at the University of São Paulo and the University of Porto. And well, my talk will be, I think, a bit different from the rest because I come from philosophy, and I will try to discuss the ambiguous status of attention in predictive models of cognition. So the content will be divided into like a brief description of precision modulation and salience, followed by a description of attention across disciplines, and then I will finish with this discussion that I've been labeling as having an ambiguous status. And, as I am a philosopher again, this is a philosophical analysis. And so my focus will not be on any specific models or any specific formalisms, but on the general framework of both hierarchical predictive coding or predictive processing and active inference, which I believe you all know very well. Okay, so attention in these two frameworks is usually related to two things: precision modulation and salience. Precision modulation, or precision weighting or precision optimization, is formally the expected inverse variance of prediction errors. In other words, in the predictive brain, the precision modulation happens within second-order predictions that control the confidence of the first-order predictions. So if the brain is highly confident in a prediction, the modulation will reduce the gain on error signals, choosing to trust its prior beliefs over the unreliable new data. However, if the context is uncertain or noisy, an error will be given significant weight, prompting a major update to its internal model. And it is believed to be implemented via lateral or self-inhibition in the error units, with the biological substrates being like inhibitory synapses, neuromodulatory adjustments, and also fast gamma synchrony. And attending here would be the modulation of the synaptic gain for these two top-down predictions and bottom-up prediction errors based on the precision they are estimated to have. And this is pretty much how the endogenous and exogenous attention would work. Salience, on the other hand, has to do with action selection. So salience has been characterized as intrinsic motivation and denotes actions promising maximal informational gain. That is highly unpredictable and yet interpretable observations, after which sampling is suppressed in a manner akin to inhibition of return. And in neurobiology, this would be tied to action planning, specifically in vision, we would say the action of basal ganglia, where the salience ranks potential saccadic targets and thus corresponds to competing saccade evaluations. So attention then comprises actions selected to elicit information that cannot be inferred passively, and salience indexes the epistemic value of such actions as quantified by expected free energy. And of course, the predictive attention has been around for a while across, various disciplines. And here's just an example of 3 tasks that were simulated using predictive models in visual neuroscience. But, there are tons of different other examples in the literature. So this first, on your left, is the famous Posner queuing task, which revolutionized the neuroscience of attention, and it was successfully simulated by Feldman and Friston in 2010. And this task basically makes participants fixate centrally while cues indicate where a target might appear. If the cues are valid, it will speed up the reaction times when the target appears at the cued location. If the cue is invalid, slowest responses will happen when the target appears as well. And it, people say that it reveals how attention can be covertly shifted without eye movements. And the example in the middle is an active inference model of selective attention developed by Mirza and colleagues in 2019. They focused on contextual epistemic foraging, that is how agents seek out task-relevant information while ignoring irrelevant stimuli. And for that, they simulated typical attentional behaviors like this one in Yabu's task, where you basically have a picture and you have to look to this picture, and then your saccades will be recorded. And so on the left side of the figure, there is the human saccades, and on the right side, there are the simulated ones. And they framed attention not just as the reactive process, but as a proactive part of planning that will be tightly linked to the saccadic eye movements and also belief updating. And the third example on the right is more focused on the movements of the eye itself and also the neuromodulation that happens. And this paper was done by Paul Friston, and they used an active inference model to simulate how different neuromodulators, specifically the cholinergic and the GABAergic modulators, affect oculomotor behavior during the late saccade task. And this task is about a cue that indicates a target location, followed by a delayed period requiring fixation, and then saccades to the remembered location. And so by manipulating precision parameters associated with each neuromodulator, they were able to model how pharmacological interventions could alter both the decision to initiate a saccade and the trajectory of the eye movements. Pretty cool. And so predictive models have also been used in computational psychiatry. That is a new and progressively important area that aims to, understand the psychiatric disorders using both real data and simulations and models. And the majority of these studies work with predictive coding schemes instead of active inference, so they kind of focus on the precision modulation parts instead of salience. And I'm not going in details about these papers that I put on my slide, but I left them here just for you in case you want to check later and read if you want. But the idea that I want to say here is this. Many, if not all, the psychiatric disorders in the predictive context happen because of the malfunctioning of precision modulation. And even though the malfunctioning is not the only or the main reason, as everything, about our psyche happens because of multiple things, it is a current and a core reason. And this means that if we understand attention as precision modulation, then all psychiatric disorders could be, in fact, attentional disorders, at least in principle. So can we, really say that attention is precision modulation? Well, attention, like any other phenomenon of the mind, has been studied since forever across cultures and fields. But one definition that was kind of foundational to the science of attention was the one made by William James. That is the taking possession by the mind in a clear and vivid form of one out of what seems several simultaneously possible objects or trains of thought. Focalization and concentration of consciousness are of its essence, and it implies withdrawal from some things in order to deal effectively with others, and is a condition which has a real opposite in the confused, dazed, and scatterbrained state. This is like the classical definition. But more recently, neuroscientists Sabine Kastner and Kia Nobre coined a more scientific or more operationalizable definition, that is the prioritization of processing information that is relevant to current task goals. And a couple of years ago, philosopher Wayne Wu made an even shorter description and operationalizable definition of attention. That is simply attention being the selection of a task to guide behavior. But of course, as the literature is huge, there are many different effects, mechanisms, and interpretations of what attention might be. So if you take a look in your right, you see this impressive taxonomy made by Caldas, and you can see that selection fraction is just one subkind of the many other subkinds and kinds of attention that coexists. Nevertheless, I'll stick with Wu's idea or these definitions of selection because they shaped the visual neuroscience and, of course, for the sake of time and scope of this analysis. Okay, so there are three main neural networks that people commonly attribute to attention. If you look at these pictures I borrowed from Ross, you can see in detail the activations. The first network is the alerting system, which keeps the person awake and not asleep. And this neural network is composed of the thalamus, locus coeruleus, frontal and parietal cortex, and has the noradrenaline as the modulator of the network. The second is the orienting network, which drives attention overtly and covertly, and it is composed of the pulvinar, superior colliculus, superior parietal lobe, and parieto-temporal junction, and also frontal eye fields, having acetylcholine as the modulator. The third is the conflict network, which monitors conflicts, problem solving, or basically decision making, and is composed of the ventral lateral prefrontal cortex, basal ganglia, and the anterior cingulate cortex, and it has dopamine as its modulator. And additionally, I included here a figure from Parham Friston that illustrates the network of eye movement, which is fundamental in attention studies in visual neuroscience. And this network is composed of the superior colliculus, basal ganglia, frontal cortex, cerebellum, and also the vestibular system. And it also has dopamine as the modulator. Very well. So from the 80s to the 90s, there was, a significant progress in understanding the effects of attention. And with that, many theories and models were developed. Here I brought 3 theories that are well consolidated in the science of attention, at least that I am aware of. And the first one is feature integration theory that was developed by Anne Treisman and Gary Galad in 1980. And this theory is about attention being a kind of glue that binds the perceptive features together in a single percept. And one core item in this theory is the cognitive maps, which have been extensively used in modeling neural networks. The second theory is the premotor theory of attention that were developed by Lila, Craig Hero, and Giacomo Ricciolati in 1987. And this theory is very important for spatial attention because it kind of proved that attention shares the same activations as eye movements and also action representations in the brain. So they basically described the dynamics of overt and covert attention. And the third theory is the bias competition theory, which was proposed by Robert Desimone and John Duncan in 1995. And this theory is highly influential because it basically describes the dynamics of top-down and bottom-up attention, specifically how visual contents would compete for cognitive resources. So, yeah, pretty important. And when it comes to personal level of attention or clinical attentional effects, there are mainly 3 disciplines that kind of investigated: psychology, psychiatry, and philosophy. Of course, that, before technology and tools, neuroscience was psychology, at least cognitive psychology. And you find attention literature before the 90s, mainly in psychology textbooks. So anyway, the personal level effects of attention are basically to focus, right? When you kind of pay attention to something and how well you perform it, this will depend in many things like mood, interests, environmental distractions, and so on. And we also have the internal agency, because not only do we pay attention, but we choose what we pay attention to. So even though our attention can be grabbed sometimes, like you're trying to pay attention in my presentation, then your phone rings. Even though it will distract you for a moment, you can choose between giving the attention to your phone and answering the person or whatever, or getting back to the presentation. So you choose, basically. You're in personal level, you choose. And when it comes to attentional disorders, when these things do not work well or properly, science and psychology, psychiatry worked a lot with lesions or developmental problems that make people kind of neglect one side of the visual field. And this was sometime later labeled as hemispatial neglect. And of course, we have the attentional disorders, ADHD, that is pretty common nowadays, and people are being diagnosed even when adults. So, it's important to highlight here that not only ADHD, but all psychiatric disorders have a common symptom that is the decrease in attentional task performance. And so, of course, when we talk about lesions and development, it's kind of a different thing. But when we talk about psychiatric disorders, this attention performance is a common and current symptom. And lastly, real quick, I would like to present to you some of the philosophical theories of attention. So the first here is Wayne-Wood's selection for action. He proposes that attention is best understood through the role in guiding behavior. So in his view, attention would be an active process of selecting information for that is relevant for action. So for instance, if an agent is preparing to grasp a cup, the visual and the motor systems will prioritize or select cup-related features. And this selection, according to him, is what constitutes attention. Sebastian Walt's priority structure depicts attention as the structuring of consciousness itself. So it would be a way of prioritizing mental content across perception, thought, and emotion. And for him, attention is not tied to a specific modality or task, but it reflects how the mind allocates its limited resources. And so this prioritization shapes what becomes salient, accessible, and integrated into our stream of experience. Christopher Moll's cognitive unison theory links attention to something related like something like an orchestra. So attention would not be a single process, but the harmonious functioning of multiple cognitive systems. And because of that, attention for him would be an adverbial phenomena that is not something that the brain does in one place, but how various processes operate together. Now, some theories of consciousness have attention at their core, as it happens with at least these two here. So Michael Graziano's attention schema theory will argue that the brain builds a simplified model of its own attention, that would be the attention schema, that is similar to how it tracks the body. And this internal model helps the brain monitor and control attention, and it's this model that gives rise to the feeling of awareness. So consciousness then would be the brain's interpretation of its attentional state. Lastly, Jesse Prince attended intermediate representation theory. That is to say that consciousness happens when attention targets intermediate level perceptual representations. Those reach enough to be meaningful but still tied to sensory input. So only attended representations at this level will become conscious, making then attention a gatekeeper of awareness. Okay, so now that I've talked a bit about attention, let's see why I think its status in predictive models of cognition is a bit ambiguous. So first of all, what are the differences in attention addressed in hierarchical predictive coding and active inference models? You know, I'm aware that this question may be more because I'm not entirely familiar with the formalities and, don't know how to reproduce these models. I don't model anything. But, by reading the papers, I could not spot real differences in the way attention is treated. And I would be happy to learn. I mean, if you know how to answer this question, please email me. I mean, formally, precision modulation and salience are different things in the models, of course, but the way attention is related to them is what is not clear to me. For instance, precision modulation happens every time in all scales, but does it mean that we are attentive at all the time in all scales? I don't know. I don't think so. Or even if we are, maybe it means that attention will be more like the foveal spot of our experience. I don't know. And even like if it is the case, then what's the difference between this and conscious perception? And I don't think that attention disorders mess with perception in this manner. Of course, there are some lesions in the brain that could be related with, holes in a vision or black shadows. I don't know, things that messes with visual perception. But I don't think that attention disorders would mess with perception in this specific manner. And what about salience? Is salience the same as the dynamics of overt and covert attention? It kind of makes sense to put it that way, but I don't see the relation of this dynamics and what salience means in the predictive models, specifically the action choosing thing. I don't know. But anyway, secondly, can these models address the various, if not all, types of attention beyond spatial attention? This idea of precision modulation and salience seem to work well if related to bias, competition, and the promoter theory of attention, but these two are about spatial visual attention. And so I don't know, I was just wondering if we could, if it will be ever possible to address the other kinds of attention. For instance, there is this work by Ransom and colleagues that argue that the affective biased attention cannot be simulated by predictive models. So I don't know, it could be just a matter of time until all the kinds of attention will be addressed, but I don't know. Anyway, my third question is also because of my naiveness towards the formalism, and again, I'll be happy to learn more. But what is the original contribution of these models to attention literature or to attentional neuroscience? The way I see it, there have been no new predictions made by these models, only reinterpretations or simulations of non-scientific schemes. And more, many of these schemes are also simulated by other computational models like reinforcement learning, normalization, and so on. So what's the novelty here? And lastly, where is the external world? Exogenous attention is famously known for its dependence on the external world, the external stimuli. But it looks like here it's all about top-down modulation, even to externally triggered attention. I know that prediction errors come externally, but whether they are going to be salient or not will depend on this modulation and not on, say, the intensity of the stimulus or something like that. And honestly, it kind of makes me feel a bit down because, I'm studying active inference precisely because of the narrative of the organism environment coupling and stuff. And as I understand it now, it looks like the external world is really a minor detail in the predictive biomachinery. So I don't know. I would be wrong. But okay, if we are to accept that attention is precision modulation, maybe it means that attention is something more fundamental than a simple cognitive feature, right? I mean, it can be what Moles described as an adverb in a cognition, meaning that it is a mode that things happen. But I think it still wouldn't explain the integral functioning of things, as sometimes we do not perform an attentive behavior at all. But it might be an interesting start. And also, if we understand attention as a more fundamental thing, maybe there won't be as many types of attention as we currently have, because once we reinterpret these types, they will kind of disappear into the model updating scheme, I guess. And another important implication of this take is specifically for psychiatry or computational psychiatry. So it is known that bad performance in attention tasks is common to psychiatric disorders, but what if they are at their core different expressions of attention disorders themselves. For instance, people say that too much gain in predictions leads to psychosis, whereas too much gain in errors leads to autistic behavior. So could that be the case? I mean, is everything attentional? This idea is not entirely new. Okay, there are some works in the literature suggesting that psychiatric disorders are attentional disorders, and so this might be a fruitful spot to investigate further. And of course, would we be closer to a unifying theory of attention if we continue these reinterpretations of models and theories of attention into the predictive account? I don't know. It looks like at least reinterpreting biased competition and premotor theory within active inference framework, I think it worked well. So we could keep doing this and see what happens. So yeah. Well, my last slide is what I think it kind of should be addressed by the community of active inference. First of all, what are the advantages of saying that attention is precision modulation and salience? Could we say that what I said a couple of slides ago is an advantage, or is it more confusing? Like, if we have a theory that explains everything, then this theory explains nothing, right? So I don't know. What are the advantages, the real advantages of saying that attention is precision modulation? And how to acknowledge that sometimes modulating weight has nothing to do with attention, because it may be the case, right? I mean, we don't need to, of course, if we say that attention is more fundamental than other cognitive features, then we could say that at least a primitive or a minimal attentional function is working all the time. But then I don't know. I mean, is it the case really? Well, and besides the kinds of attention that could be dissolved into the model updating scheme, can the predictive attention say anything about the personal level of attention, that is the act of paying attention, or the internal agency, or anything like that requires personal level interaction with the word? And lastly, this is more like a request or a suggestion than anything, but so I understand that active inference and predictive coding frameworks are still young in the literature, and people are applying them to everything, which is cool. But specifically for philosophers, it feels like that philosophers got away from the literature, well, scientists have always been skeptical and still are, but philosophers were once super attracted by the predictive idea, and then I think they are kind of getting away from this. If we see philosophers talking about it, they either have a very specific idea that may even not correspond to the formalisms at all of the frameworks, or they are critics of these frameworks, also usually having a very specific and maybe even unrealistic idea of the framework. So my request as a philosopher is to trying to deepen and learn the models and trying to work on their implications to real life is that the community should stop scaring philosophers away, and I don't know, we should try to make a second bridge for philosophers again to be interested in the active inference models and see what's new, and to continue working on the implications of these frameworks to real life, and so to help modelers to not be so abstract and lost in their maths. I don't know, it's just something that I feel like saying here. Anyway, that's it. Thank you for your attention. If you need to contact me, you can scan this QR code and see my website. Thank you.
Okay, we are back with Samuel Montanes et al., Agentic Finance. So, Samuel, looking forward to your presentation, and anyone in the live chat can write any questions. Thanks, go for it.
Thanks, Dan. Hi, everyone. My name is Samuel Montañez. I am an artificial intelligence PhD student based in Mexico City, and I'm here with my co-authors, John Clippinger and Matthew Moroney. We're basically a working group and a research group working mainly on the intersection of finance, economics, neuroscience, and in this case, bridging active inference for financial applications. So that's pretty much what we're going to share today with you. So what we have for today is agentic finance, active inference applied to dynamic portfolio management. So any questions, please put them in the chat. And also Matt here has some practical industry-oriented questions for that should be interesting that we're going to do in the end, as well as the public's questions. So let's start. First, I'd like to share with you the finding, a very important finding in economics that pretty much launched the behavioral finance revolution in economics, and it's called the excess volatility puzzle. So in standard finance and economics, we think about the prices of securities, of financial assets, pretty much depending on their fundamentals. When we say fundamentals, it's their economic fundamentals. So for example, for stocks or other type of securities, we usually value them as taking the present value of the expected dividends discounted by some risk rate. So that's pretty much the standard formulation that you will learn in any introductory finance course. But that's also the standard way that most people do valuation, both in industry, in corporations, and that's pretty much what you would be taught in an MBA. So what's behind that formulation in terms of the theory of what we are assuming about the economic agent is that we are assuming a theory that economists called rational expectations. We assume that economic agents are rational agents in the sense of having complete information, having transitive and static preferences, and a bunch of the other assumptions that makes the model easier, makes just the model easier to work for. And in general, most financial models have this assumption behind it. So in this case, if we assume that we have this rational expectations model, and we say that we expect that a certain security would be correctly valued depending on the expected value of their dividends discounted back to the present. We're going to check if that's true. We're going to use the Standard & Poor's 500, the market index that represents the 500 largest companies in the US. And if we assume a rational expectations models of the dividends I just shared with you, we would have from the 1980s to the 2025, pretty much the red line that we're seeing here. That would be the expected correct price under that rational expectations model. That would be what we should be looking at, or something very close to that. But what we are looking at really is the blue line. That's the actual real backtest on the S&P 500. And pretty much Robert Shiller, one of the founding fathers of behavioral finance at Yale, pretty much measured the difference in volatility between the rational expectations model and the real market price. And he found an astonishing finding, which was that real S&P or market returns were 25x higher than what would be predicted by a rational expectations model. And later on, subsequent studies tried to find the answer of these difference in volatility. And they pretty much analyze everything. Difference, for example, in costs of trading, differences in taxes, because of course the index is just like it's just an index, so it has no transaction costs, stuff like that. So they accounted for all of those things, and none of those things could explain a 20x difference in volatility. So basically, this led us this led the economics profession to start importing methodologies and knowledge from other fields, and in this case, psychology, to try to answer why is that markets are behaving this way, that prices are diverging of what would be expected under a rational model. And essentially what Shiller claimed, and what is like the tenet of behavioral finance, behavioral economics, is that markets are driven by belief dynamics and not only by their economic or cash flow fundamentals. So given that we're speaking now about beliefs, we need to import things or knowledge or techniques from psychology and later on from neuroscience. And pretty much what we're proposing here, our framing, is let's say the integration of different fields coming together. On the one hand, we have Robert Lucas as one of the, probably like the last mainstream economist who is a strong proponent of the rational expectations model, especially in macroeconomics. We can also mention others like Eugene Fama with the efficient market hypothesis. We can also mention Paul Samuelson at MIT, but all of those are the mainstream economists who have pretty much established that rational expectations is the way to do economics, and it's still the ruling school in economics. Now, later on with this work from Shiller here, famously Kahneman and Tversky, two psychologists who were exploring decision-making under uncertainty, published their famous prospect theory. You probably seen it or heard it or read it in their famous book, Thinking Fast and Slow. And they basically found that individuals consistently perform bad economic decisions and came to several decision errors, especially many errors concerning calculations, probabilities, and money in general. And later on, with this gentleman, Richard Thaler here, a recent Nobel laureate in economics into 2017, actually received a Nobel laureate in economics because he was able to integrate those findings in psychology and import them into economics. And that gave rise or formalized the field that we know today as behavioral economics. However, as with rational expectations, economists usually think about behavior. For example, we can remember from Paul Samuelson's revealed preferences, see behavior and we infer preferences from that observed behavior. And that standard lens to look at economics was pretty much prevalent also in the behavioral economics school. So it didn't change much the experimental methods or the techniques that they were trying to use or that they were using to try to understand economic behavior. So later on, especially from neuroscientists like Paul Gleismer at NYU and Colin Kammerer at Caltech, there was a neuroeconomics revolution, which was basically saying, why aren't we using the latest neuroscientific findings to try to inform our understanding of economic decision making? So basically, these two gentlemen are probably the leading academics or intellectuals following this trend. But interestingly, I mean, they have made waves in economics, but it is not nearly the most popular field in economics. But basically, what we are claiming here is that we can come together into a more general theory that accounts for a principle-based scientific theory, which is the active inference theory or framework, and integrate both of these schools of thought into a single school of thought, which we're going to call cognitive economics, where we're basically going to unify the behavioral finance, behavioral economics, and even some aspects of rational expectations as well, with neuroeconomics findings that come naturally in the active inference framing. And that's pretty much what we are proposing, using active inference as a general framework or a general umbrella to make these fields come together into what we call now cognitive economics. So essentially, we are taking, this is not limitative, but we are specifically focusing on bridging these aspects from each field. From neuroscience, bounded rationality, also the neural process theory in active inference, and also other aspects of decision theory in neuroscience. From economics, mainly behavioral economics, behavioral finance, but we can also reconcile some aspects of rational expectations as well, because it has been tremendously useful in economics. From finance, asset pricing theory, and from active inference, we're taking pretty much everything to integrate this into the framework. And actually, cognitive economics is not per se, let's say, our own creation. Other major economists or mainstream economists like Gabay at Harvard or Bordallo in Italy and Schleifer at Harvard have been actually pursuing this line of thought in the last 5 to 10 years, let's say. And for example, Gabay is studying the effects of attention and limited processing capacity that naturally for almost anybody in the active inference community, we are well acquainted with Landauer's principle, precisely having a thermodynamic constraints in decision making. So that comes obvious to people in the active inference community, but it's actually sort of novel in economics. Also, for example, Bordallo from Bocconi and Schleifer at Harvard have been pursuing what they call diagnostic expectations, which is basically integrating findings from cognitive psychology, some from neuroscience, and bridging it or importing them to economics. And they actually propose laws of motion for understanding belief dynamics. And naturally, that naturally resembles Bayesian mechanics in active inference. And finally, loss aversion, which is the famous finding from Kahneman Tversky in behavioral finance, can also be tracked like one of the, let's say, pioneering works on trying to understand decision making from a neural grounded theory. So basically, active inference would allow us to bridge all of these fields in one part from a normative standpoint, on the other part from a descriptive standpoint, because it gives us much richer tools to understand economic decision making, and the other is a mechanistic model to understand how those belief dynamics are forming and are being updated. And for this, we are proposing a change in paradigm in finance and in financial valuation. So we're proposing an agentic finance type of model. So instead of using static models as, for example, taking the present value of the expected dividends, which is basically a standard discounted cash flow type of model, and many other financial models, we're saying instead of doing that, let's use agents-based modeling. Let's assume that our economic agents are actual agents and that they perform inference as planning. Because in a sense, all type of economic decision making has a reference to goals for almost mandatorily has to do with economic financial goals, and it has to do with planning. So when we integrate those two key aspects, that makes the agentic framing very natural, very, very natural. And we are proposing that this agentic finance framework of financial evaluation would allow us, first, that the agents can infer distributions under uncertainty and actually update those inferences about the distributions that they are observing. Well, where we're speaking about distributions of asset prices, returns, etc. Because in traditional financial models, most of them assume, for example, a fixed distribution with known parameters, most often the normal distribution. But what if the distribution is not normal? What if we don't know the parameters? And that's what we often observe in financial markets, where we see changing distributions. We also see distributions with fatter tails than what would be predicted by a normal distribution. So that's very, very common. And finally, traditional financial models completely ignore the agent, completely ignore what the agent believes, pretty much always assumes a type of homogeneity in preferences. So all agents are the same. All individuals make the same type of economic decisions. They are fixed. Whereas in agentic finance, we can always tune our graphical model to the specific type of agent with a specific type of investment goals, of risk preferences, of prior distributions, financial knowledge, etc. So it allows us to really personalize valuations depending on the type of priors that you have. Whereas in traditional finance, that's fixed. So basically, we are proposing using active inference to frame financial valuation as planning through inference, essentially financial planning in this case. Now, the PMDP architecture that I just showed you in this graph, in this visual graph, is essentially the standard way to frame or to apply active inference. So the partially observable Markov decision process is partial. You might be acquainted with the Markov decision process in standard reinforcement learning, for example, but it's partial because the agent only partially knows the external states in this case. It has partial information, and it has to infer those external states. Now, a key aspect that we are framing here is that we can get into great detail in what financial aspects we want to take into our evaluation model. Here is just an example of how you could frame it, but it's really not limitative to public assets. It can also be used in private assets. It can be much more detailed in the actions that you can take or the many observation variables that you can define. This is just for visual clarity and that we can understand it. So first we have the state spaces, and we're going to define two state spaces or two factors. So one is going to be the market regimes. So when we speak about the market regime, is what we usually assume naturally. The market is going up, is going down, is flat, or we're in a crisis, like in a financial recession. So those are our four market regimes. And those are the ones that the agent, the trader, wants to infer. And then we have portfolio positions. So portfolio positions means what I'm going to do, or where do I stand in my portfolio in the sense of going long, going short, selling, or expecting a decrease in price, or just holding. I am holding my position flat. And when we observe and what the agent is observing from the external world to try to learn are two things in our model. One is the return observations for the asset that we are going to analyze. It can be a basket of assets, an ETF. It can be whatever we want. And second, we have the P&L observations. So when we say P&L, it's the profit and loss of our own portfolio, of the portfolio of the agent. And we're going to divide that portfolio into quartiles. And we're going to divide it into quartiles so the agent can analyze if I am on the top quartile or in the bottom quartile, so we can have some sort of ranking of order of preferences. And finally, we have the action space. So the agent is going to be able to act on its sensory inputs to try to change and trying to change their positions and get closer to its expected preferences. So those trading actions are going to be the 3 standard trading actions: hold, buy, sell, but we added a 4th one, which is reduce, because in some cases you might not want to sell your entire position, but you might want to decrease your exposure. So that's like a 4th like detail that we added. Now, if we want to think about how would this framework would evolve, how would it work while being active, basically we say that the state spaces are the hidden states. So we have 2 hidden states. One, again, the market regime, and naturally, as investors, we would want to learn if the market is going up, if it's going down, or if it's just like staying flat as it is. And the interesting thing is that we have no control over that. We have no control over market returns, and nobody really knows what the market is going to do. For example, economists all over the world, but especially in the United States, have been forecasting a financial recession or an economic recession in the US for almost since 2020. So we have been 5 years waiting for a recession that never comes in the US. And also, for example, Jamie Dimon, the CEO of JP Morgan, recently said that he expects that perhaps in 2026, we're going to get to the recession this time. So if not even the best economists, the world financial leaders, can guess in which market regime we are, that's pretty much the best example to see how they are completely unpredictable, uncontrollable. But what we can control is our portfolio position, because we can decide to go long, go short, just hold our position as it is. So we want to change that. And then we have the observations that the agent is going to learn from. And we divide the observations in this financial application into exogenous observation and endogenous observations. And why? Because again, the external, in the external states, we have the market, and there's the financial securities, and they generate returns. So we can observe those returns. We can observe them, especially for public securities like equities, public equities. Let's say, for example, for an Amazon stock, we can observe its price at all points in time, but we cannot have any influence on that price. And then we have the P&L of our own portfolio, and we can observe that. So that's endogenous to the agent. And that distinction is going to be very relevant to what's coming next. Also, a key difference between a standard financial model, and perhaps not that different from an econometric model, but much cleaner in its implementation, at least for an agentic implementation, is that we can factor these different types of information that the agent receives and clearly classify it. So that's key, at least for financial information, and return attribution, which is a key aspect of applying different artificial intelligence techniques for financial markets. And also, we can add action-dependent transitions, which is that we can act upon our portfolio to alter the P&L, but we cannot act on the market. So we can make that modality distinction, which we often cannot make in a standard model where we just put all of the variables into a black box. And finally, in the C matrix, which is the preference matrix, that would be a quasi version of a reward in reinforcement learning, for example. We can also embed into that risk aversion parameter, which is also standard in finance, and we are using the 2.25 standard risk aversion factor, which was pioneered by Kahneman and Tversky, which basically says that humans compute equal losses to gains in twice the magnitude. So that's what we are also putting into the model. So we can actually embed this type of neuroscientific or decision theory findings into the model to have theory-based parameters. So I just mentioned that that the C matrix basically is a matrix where we can put the traders, in this case the economic agents' preferences. Now, how it is done in the standard active inference is that we work with log preferences we work with with preferences of defined as log of prior probabilities, basically. So that's the standard way of framing it, as we can see in the upper box. Now, instead of using that type of implementation, we're changing it a little bit, and we're defining our C matrix as it is done in risk-sensitive control or KL control, where we just define preferences in terms of utilities. And one question would be, but why would you define the C matrix like this and not use the standard active inference implementation? And our reasoning to do this is mainly because of knowledge transfer and, let's say, industrial applications. So if we want to convince or persuade real investors, financial institutions to use this model, it's much easier to explain to them how preferences are encoded in just expected utility. So if the C matrix is defined as expected utility, we can say the model is maximizing expected utility subject to a specific risk preference. So we can actually frame it just like that. Whereas if we frame it as the log of prior distributions, we will have to say something like our market returns are expected or are modeled as a uniform distribution, let's say. And that's much muddier, let's say, than just saying it out loud as any economist would or financier would say it. And this is not new or anything new. This is the standard way to do, let's say, maximum entropy reinforcement learning or KL control, as mentioned. And actually, KL control has been used in financial management and portfolio management before. So that might be a method that also industry, general industry practitioners are acquainted with. So how are we defining this? Essentially, remember that we have market returns and the P&L. We just said that market returns are uncontrollable. I mean, the market is just there. We cannot control it. So we're going to define that C matrix as 0 so that means that we are neutral to market returns because we cannot influence them. Whereas the P&L is controllable because we can act upon selling, buying, etc. So it's position dependent. That's what we mean. So it's not going to be 0. And essentially, an additional benefit of framing the C matrix or the preferences as utilities is that scaling them by the risk aversion, scaling the losses by the 225 Kahneman and risk aversion is transparent. So it can be done in the active inference framing as well, but in this case, it's super transparent. As you can see, for example, from the utility vector, the risk scaling parameter is only applied to losses because we say that gains are just, factored by 1. So for the 0.6 and the 1.0 in losses, we can scale them, as you can see here, by 2.25, and then that would yield the reward preferences for the P&L, the updated reward preferences. So as you can see, is pretty much transparent. Now, how does this links to standard financial theory? So when we take an introductory corporate finance or investment management course, the first pricing model that we usually learn is called the CAPM, the capital asset pricing model. So the CAPM right here is essentially a regression model, a one-factor regression model that essentially says all expected returns on a security, let's say on an equity, on a stock, depend on just one factor, which is the market risk premium. So essentially, the model says you are strictly and only being compensated by the amount of market risk that you are taking. So we can decompose the CAPM into two types of essential risks in financial investments. One is called systematic risk. So that systematic risk is pretty much what I just told you, the market risk. How much market risk are you taking? And that's the only risk, according to this financial theory, that you get compensated for. Whereas the other term is the idiosyncratic risk. So that idiosyncratic risk, we can refer to it as the firm-specific risk. So for example, if I'm investing in a restaurant, I am exposed to specific risk that the restaurant has, like having a fire, or then employees don't show up, or a flood, or whatever. But that's not systematic risk. When we speak about systematic risk, we refer to as general market risks like inflation risks, like interest rate risk, so COVID as well. Those are systematic risks that we cannot control in any way. So we cannot diversify away in any way in standard portfolio management theory. Now, what are the disadvantages of this model? Number one, it's static, meaning that the betas in the model, which is often called the market beta, is not dynamic. So in the standard framing is not dynamic. Now, there are more recent proposals where you have a dynamic beta, but interestingly, for I think that most of the viewers, if you go today to Harvard Business School and pursue an MBA and you get taught a corporate finance course, you're gonna get taught this model, not a dynamic beta model. This is the model that you're gonna be taught. And most investment banks and consultants still use this standard model and not more sophisticated models that do exist in the literature. So that's very important because perhaps there's updated models, but those are not the models that most people use in industry. And additionally, it's a passive model in the sense that there's no agency because, again, economic agents are just static in a sense. So it's just, it's in a sense just saying you can buy an index fund and just stay there for, as long as you can. It's in a sense, it's saying that because you cannot really add up much more return unless you're willing to take firm-specific risk, idiosyncratic risk. But that's up to you. And in theory, this theory says you shouldn't because you're not being compensated for that. So it's not even logical. Now, in our active inference framing, I just explained that we cannot control market returns. We can learn from them, but we cannot control them. So those are neutral preferences in the sense that we cannot act upon them. But we can act upon our P&L. And our P&L is a function of two things: of the weight that we want to have exposure to in a specific asset times the market return on that asset. So that's what we can act upon. That's the controllable modality that we can act upon in our model. So how's different from the CAPM? It pretty much changes the whole framing because, number one, the W, the weight, is adaptive. It's not fixed. It's not static. So that's one main difference. Second, it learns because even though we cannot act directly upon markets, we can learn from that market information to change our weights in the position. So we can learn from that information and we can act upon our portfolio position to modify our P&L. So as you can see, it completely changes the way to see finance as just measuring temperature to an agentic vision of financial markets. So how does this links to standard framing in economics? So as I was saying, even though the rational expectations model comes across sometimes as like very antiquated, let's say, for many people, because they say, how do economists actually believe, or it's not that they believe, but how do they take those axioms which are very extreme into their models and they just think that the models are going to be very successful as those axioms are extremely radical, let's say. But Robert Lucas is probably one of the most famous living economists. He won the Nobel laureate because of his famous Lucas critique. And basically what he claimed was the following: in econometric models, those econometric models, again, implied a certain stability of financial agents. So policymakers just assume that, again, individuals in their societies were fully rational, respond to information, and the most important aspect is that preferences were stable, that people don't change on their preferences. So preferences are stable. And essentially what Robert Lucas says is that parameters of econometric models are not structured. So what that means is that they are agent dependent. So agents, humans, we respond to information. So we respond to actions that the government takes. So when the government implements a certain policy, they should not expect that people are just going to be fixed and acting as they always did. People are going to react and probably, or in some cases, likely are going to modify their behavior. And as surprising as that may look, that wasn't accounted for in standard macroeconomic models in the 80s, 90s. And again, you can see that here's another place where we start thinking about beliefs in economics. Now, how does this critique is relevant for our model? Because if we frame our active inference agent as a standard active inference implementation where we say we have different modalities where one observation is going to be, let's say, the different senses. One is going to be visual information, the other is going to be auditory information. Naturally, that information is coming into the agent. We can weight its importance, but it's all coming into the agent. And you can put on glasses, you can put on headphones or whatever, so you can act upon those observations. But in this case, if we were to conflate that you can act upon the P&L and to the markets as well, that would cause a problem into the model because we just explained why they are not different. They are actually different. So what's our approach? We want to break the potential issue in this type of implementation of policy endogeneity. So we are proposing an application where we have selective Bayesian learning instead of full Bayesian learning as it would be done in standard active inference. So for example, we have in the standard active inference model, we just mentioned that we have two modalities. So we would have two learning equations as they are posed here. And in that case of standard application, we would be just using the two modalities entirely to update our beliefs. But as I just mentioned, we don't want to use the two modalities fully. We want to learn from the market, but we don't want to learn from our portfolio. And why we don't want to learn from our portfolio? That's like a weird question. But imagine this. I am looking at my portfolio, and my portfolio performed well during the last 6 months. And given that it performed well, I am going to update my internal model to act and start trading with that information from my portfolio. So my portfolio, if I am not Vanguard or BlackRock, is not going to be nearly representative at all of the general financial market. So if I am learning from that information, I'm going to contaminate my internal model to actually try to predict what's going to be the next market regime. Because again, if Samuel owns 0.00001% of Tesla, my position has literally no effect upon Tesla or the robotics market or the electric cars market at all. So what we are doing here is frozening that part of the learning equations in our model. So that's what we call it selective Bayesian learning. And we are only updating our internal model based on external market information, which is what we can learn from and which actually can provide relevant information. Additionally, we have adaptive confidence gating. So we're implementing ad hoc confidence gates where we are saying that when there's a certain level of policy entropy, the agent is not going to act. So in standard portfolio management, we have different types of risk management tools, but some standard ways to frame a trading strategy is to standardize, is to implement some systematic trading rules. So for example, some of the rules can be, you can never invest more than 5% in a specific asset, or you can never invest less than 1% in a specific asset, or you cannot have an overconcentration to a specific sector of 20%. So those are standard risk management trading rules. And in the same sense, we're imposing, let's say, an active inference flavor trading rule, which is having a confidence gate where if the policy entropy goes beyond a certain threshold, even if the agent wants to act, it's not going to act. And that could be naturally adjusted depending on how conservative we want our trading agent to be. Additionally, we are also using an exponential forgetting factor as well. And also that can be adapted depending on the type of agent that we want. But it is also recognizing that people don't remember market history perfectly. Not nearly. So it also recognizes that economic agents naturally forget. Now, if you want to frame this financial agent or this financial market in terms of the Markov blanket, like the standard framing in active inference, we could say that we have an external world, an external market, and in this case, we're specifically going to focus on trying to predict the market regimes. So that's going to be the external state, the market regime that we want to predict. Again, if the market is going to go up, it's going to go down, what's going to happen with the market. But we cannot have direct access into that market, and those are uncontrollable dynamics. On the other hand, we have in the right-hand side the internal model of the agent. So that internal model of the agent is going to be the internal model about what's going to be the market regime. I'm going to try to predict as a trader what's going to be the next market regime. And how this model actually works is between the sensory and active states. So the external market is going to yield sensory states. And again, we just mentioned that two sensory states are going to be, or the two observations are going to be market returns from the assets and the P&L from my portfolio. We just explained I want to learn only from the returns of the assets in the market, and I'm going to froze the information on my P&L because I don't want to contaminate or I don't want to have an endogeneity issue in my learning. And finally, I can act upon that information. And in this case, I'm going to act in two ways. One is going to be performing trading, and the other is going to be looking for information, the epistemic component into the active inference framework. So as you can see, this type of framing, I think, more naturally accounts for standard trading and economic decision-making in financial markets than, for example, the model we showed. So essentially, how we can look at it now, when it's actually updating in the action perception cycle in active inference, is depending on the expected free energy that can be decomposed on a epistemic value, the intrinsic value, and the extrinsic value, which is going to be the pragmatic component, the expected value in economic terms. Essentially, one of the key advantages, well known to everyone in the active inference community from the active inference framing, at least in this case against economic type of approaches, is that it allows us to embed in a single functional in the optimization process both the risk or the epistemic component or the intrinsic value and the expected value or the extrinsic value or the expected utility into a single optimization process. So is balancing these two components, or another way of framing it is balancing the exploration-exploitation dilemma automatically into the model. So how is this different from standard models in economics, in finance? Well, in economics and finance, we almost never ever use epistemic value whatsoever or intrinsic value. We only care about expected utility, extrinsic value. Now, in other type of approaches, for example, in reinforcement learning, you can add an ad hoc parameter to add an exploratory term, for example, in e-greedy methods, but that's an ad hoc addition to the model. In this case, an advantage is that it's embedded into the optimization model of the model, in the optimization model itself. Now, just to provide an example, we're going to use the ARK Innovation ETF. So for those who don't know it, ARK is an investment management firm, one of the most popular today in the US. It's owned by a famous investor called Katie Wood. And she became very popular, at least in financial markets and, let's say, investment community, because she has been a strong proponent of thematic investment and especially focus on what we could define as transformative technology, highly growth stocks, and like transformative technologies, like ranging from to digital health, clean technology, many of those mega trends. And her asset management firm issues and manages several exchange traded funds. And we are portraying here the last 10 years of performance of her most popular fund, the ARK Innovation ETF. That pretty much is an investment fund that gives exposure to investors to the major trends, again, in innovation. Now, as you can see, the fund performed extraordinarily well since 2015 up to 2021. So it went up 700% in 5 to 6 years, 700%. So at that time, Katie Wood was appearing in TV all of the time. She was claimed to be the next Warren Buffett. And her fund draws investments for more than $20 billion. So it became extremely popular. Now, as of now, after that peak, it went down 80% in its lowest point. And even after almost 6 years, people who were most of the investors who entered into the peak have not recovered even their initial capital. Now, why we like it is because this type of popular, trendy, momentum chasing type of investment is precisely the type of asset that allows us to measure regime shift. Because almost visually we can see that would be a bear regime shift, and then more or less a flat regime shift. So we are using ARK as an example, and how we can train we're going to train our active inference agent taking almost like a standard machine learning type of training methodology where we're using 70% of the historical information, and we're performing a back test on the last 3 years from 2022 to 2025 to see how would our agent would perform. Now, what's the advantage? Because one may say, why not use just deep learning and LLM? And the advantage is that we don't require retraining to just keep following the performance of the ETF, because by definition, this type of active inference implementation is adaptive. It's adaptive learning. It's full online Bayesian learning. So that's a completely different way to do machine learning, and I would claim it's a much more efficient way. And also, I think for financial applications, this adaptivity makes you much more prepared to adapt to changing market circumstances, especially with this type of volatile assets, which are one of many in the financial markets. Now, just a brief theoretical bridge as well with standard financial and economic theory. Using the Helmholtz decomposition, which is a standard part of the active inference and free energy principle, we know from Helmholtz that we can decompose any vector field into two components or two parameters. One is the gradient, we can say almost a deterministic component, and the other is the solenoidal flow, which is the cycle that is never changing into the model. Now, how can we build a link between this theory behind active inference and financial economics? One model, which is one of the most important models in valuation, is the Black-Scholes-Merton option pricing formula. So this model was created in the 70s and very quickly became the standard to price financial insurance, financial options in markets in general. But originally, the model was created to value corporate liabilities, actually. So another extension of the Black-Scholes model is what we call the real options Black-Scholes-Merton model, which can be actually applied to value private projects, private equity projects, and mostly innovative projects where there's a contingent aspect into that type of investment where there's like huge changes. For example, like all of the innovation trends embedded in a fund like ARK. Now, the Black-Scholes-Merton option pricing formula defines that stock prices move as a geometric Brownian motion, where you have a drift, the first term here, defined by mu, and a stochastic component where you have the volatility here and the Wiener process, which does the stochastic part. But what is the probability evolution of this model? And the probability evolution pretty much will yield this equation here, which basically just left you with the gradient, meaning that by equilibrium economics, that dissipative aspect, comes to an equilibrium. So there's no solenoidal flow. Put into economic terms or into physical terms in this case, because again, the model is an equilibrium model. So it will always reach equilibrium. So if it always reaches equilibrium, there will be no exploration, no epistemic value into the model. So what we're claiming here is that this agentic active inference framing is a non-equilibrium dynamics applied to financial markets, and it can be applied to other type of markets where we know that even though at a certain very quick points in time, the financial market or one specific market might reach a certain equilibrium, that equilibrium would rapidly dissipate and start moving towards another equilibrium. And the reason why, again, is because standard equilibrium economics assume that agents were sort of statics, sort of robots. But when you have changing belief dynamics, it's always going to be non-equilibrium dynamics. And in this sense, we say that the synergetics theory also behind a lot of the active inference can naturally be applied in the self-organization and market regimes. And interestingly, in the econophysics literature, which is like what we could say like a niche group within the economics field, has basically been studying this, applying synergetics and applying other type of phase transition physics literature to try to understand market regime transition and also the emergence of prices and different market phenomena from the microscopic, and we define microscopic as, for example, the acting of an individual like Samuel in his own portfolio, and how that accumulates between millions of investors, and that gives rise to the broad macroeconomic behavior that we see in markets and eventually even in world financial markets. So we can see this emergence of economic phenomena coming from essentially microeconomic foundations. And naturally, that framing as well can be embedded into trying to understand the theory of market regimes from an active inference perspective as well. So what we're just saying here is that this framing of gradient flows, solenoidal flows, synergetics gives you a very natural technology to see these type of macroeconomic phenomena and macroeconomic questions and address them with this type of technology and in an agentic fashion with the applied active inference agent. So what are the advantages? I have discussed some against both, for example, LLMs, and in this case, a closer application would be deep reinforcement learning, and also against traditional finance. So against deep reinforcement learning, number one is the sample efficiency. Instead of requiring zillions of data points to train the LLM, in active inference, you have an adaptive agent that is training from real data or coming data, so it's much more efficient. Now, in deep reinforcement learning, we can have ad hoc exploration parameters, whereas in active inference, it's inbuilt within the optimization function. DeepRL, or in general deep learning, the most important aspect is the explainability and transparency aspect, because by definition, it's a black box. And in investment management, and also from coming regulation in future years, is going to be extremely important when applying AI methods to financial decision making, that you can actually explain how the agent got to a certain recommendation. It's going to be key for regulation purposes. And the active inference framework with a graphical model allows you to clearly understand how and why the agent recommended a certain decision or why not. Very clearly, very transparently. And finally, you have implicit uncertainty in deep reinforcement learning, whereas, again, in active inference, the entropic term is explicit into the model, and you can also add confidence gates regulated by entropy, policy entropy, like we did in our implementation. Now, against traditional finance, not to joke, but it's sort of a low-hanging fruit, because again, most of standard finance has stayed in models that were built in the 60s and 70s, and they haven't been updated much. Now, naturally, academics have updated them, but in industry practice, I mean, besides some small quant shops in very few places, most financial departments in most corporations are just using models that were built literally in the 70s and 80s, which are static, which have no way to adapt themselves to changing circumstances, have no account for information gathering or epistemic affordance, none of that, pretty much. So, as I mentioned, epistemic value is completely ignored in traditional finance. Most standard applied finance doesn't use findings from behavioral economics. I mean, more often is now included in some aspects in marketing, but not that much in trading. And in terms of bridging adaptation, at least in the applied sense, is almost completely ignored in applications of real investments. And we can see that, again, standard discounted cash flow models, the Black-Scholes models, which are real models that most people learn and most people use, is completely ignored all of these points. And we're about to conclude, but just before, the standard metric to measure the performance of portfolios in finance is what we call the Sharpe ratio. So the Sharpe ratio is essentially this: measuring the expected excess return of my portfolio against the risk-free rate. So that's what we call the excess return, because the risk-free rate would be like the baseline of money or investments, divided by the standard deviation, which in finance we call the volatility of that portfolio. So in plain English, it's basically measuring a ratio for risk-adjusted returns. So what we care in investments is not the absolute return, is the risk-adjusted return. Because if I have a very large return but taking huge amounts of risk, that's not interesting, because probably if I follow on that strategy, I'm going to lose money eventually. So what I want is a high return with low risk or controlled risk, let's say. That's what I care for. Now, what we're proposing here is that given that our agent is adaptively learning, has online learning, we actually want to measure that information gathering efficiency. So we're proposing including an additional metric to investments called the entropic Sharpe ratio. So we're doing the same thing that we do in the Sharpe ratio, taking the excess return of our portfolio against a risk-free rate, but we are dividing it not by the portfolio volatility, but by the policy entropy. So that's what we are dividing it for, and is essentially measuring the excess return per bit of informational work performed. So is measuring the ratio of how information gathering efficient, or how efficient the exploration component is happening within our active inference agent. So for example, how could we read it? If we have an expected Sharpe ratio above 50%, we can say that the model is well calibrated, is being very efficient on using the information it is gathering to trade and to generate profits. If it's low, we can say that that information seeking aspect is not being efficient. Now, why this is important is because increasingly investment management firms are implementing LLMs, natural language processing strategies to gather lots and millions of bits of data of market information to trade. And it would be useful to measure how efficient, energy efficient and cost efficient that information gathering is being for generating profits into the portfolio. And if you can actually show that your model is much more efficient into that, that can be also accounted for in the economic, let's say, valuation of how effective the agent is. And almost last slide, the explainability. As I just mentioned, a key aspect that is coming in very few years is going to be AI regulation, and especially in fields like finance, in fields like healthcare. Given, just having recommendation agents that you cannot actually see how they are coming into that recommendations, its output, that's probably not going to be acceptable for regulators. Because if people lose money, if people get bad medical recommendations, somebody needs to be accountable for it. And if deep learning or LLMs cannot be actually interpreted in that sense, in how they came into the output, then this type of machine learning, we believe, is going to be the standard way to do financial machine learning, because first and foremost, you can decompose the entire model to see exactly what caused the model to come to a specific decision, to a specific recommendation. So we believe that that's a key advantage against other standard deep learning methods. So to conclude, what we reviewed today was essentially that active inference is not per se a different theory. It's a much more general theory that can actually account for most of what has been done in economics as of now, but done right, let's say, or done much more robustly. It also integrates other aspects that have been missing into economics, for example, adaptive learning or online learning, and it's framing, again, valuation or asset pricing as planning plus control. And also we can show that standard financial models like discounted cash flows emerge as special cases where you only focus on the pragmatic aspect of expected free energy, whereas this model is much more robust. It's also including the epistemic value component, which again, we just mentioned, is becoming increasingly relevant in the world where AI agents are going to be all over the place trying to gathering data and to distinguish from fake data as well. That's also going to be a key value that we want to have in agents performing any sort of task. And finally, more specifically to the market regime theory, this is a type of agent that will allow you to understand more macroscopic market phenomena or more microfinance type of phenomena, but at the same time being embedded into a single individual agent. So it allows you to, let's say, reconcile some like pending phenomena in macroeconomic theory with microeconomics and finance in this case. So we believe that our core contribution is that active inference provides a principal framework for portfolio management under uncertainty. And as we just showed, with demonstrated risk management advantages, because if you define that the agent is risk averse, as naturally people are risk averse, it will usually engage in much better risk management than standard traditional methods, or also reinforcement learning methods where it's very much focused on the reward. So thank you very much. So we're going to go with some prepared questions from Matt, and then we're going to address some questions from the audience as well. Or we're running out of time. Oh. Awesome. Awesome.
Thanks, Daniel and Sam. Excellent stuff. I want to take the perspective of someone who would be a practitioner in the industry. And there's a lot about risk reward management. There's a lot to be said about portfolio construction and the separation of trading and compliance in most firms. But I really want to focus in on this contribution of the entropic Sharpe ratio, because to me, this fundamentally reframes how we think about data economics. An asset manager might spend tens of millions of dollars on Bloomberg terminals and satellite imagery without any idea of whether each new data source actually improves their returns.
Right.
This actually suggests that we can measure the value of each information source by its policy entropy. So I wanted just to make it super practical. Could you outline how you would do real-time scoring of different information signals like tweets or data releases or earnings reports that could help readjust a portfolio based on the quality of those different information feeds over time?
Yeah, sure. Basically, we would say that, I mean, pretty much the higher the ratio is, that means that whatever information you're feeding into the model is being much more efficient in terms of the signal to noise ratio. So it's being much more efficient on signaling the correct information or the valuable information to maximize its model evidence or minimize its surprise, let's say. Whereas if you're feeding whatever information, other information, if the policy entropy is low, that means that is doing the opposite effect. Is not helping the agent much on maximizing its model evidence or minimizing its surprise. So that would be like the clear implementation. And what's valuable, as you just said, is that later on firms could literally quantify it in monetary terms on weighting how much money they're spending on feeding data into a specific strategy and how much that data is providing returns. So that also gives market opportunities for people willing to create methodologies, data sets, etc., to make that process much more energy efficient and data efficient as well.
That's really important. I have a quick question, sort of a big picture question. If you really look at what you're saying, you're providing a really new paradigm for identifying value, and it fuses economics and finance, and it actually combines monetary policy and fiscal policy in some form. And when you look at the current economic system, where it is using an arbitrage of different opportunities and risks and bid and ask risk spreads, this actually is a replacement mechanism, viewing the market as a Markov blanket that aligns different agents around specific outcomes. So this becomes is far bigger than sort of me being a simple technical trades. It's a very different way of envisioning the market, and yes, and I think that is going to have really significant implications at multiple scales. Would you agree with that, or is that an overreach?
No, totally. As you just mentioned, we are literally reframing how we would conceptualize macroeconomic structures or market structures within Markov blankets, and how the agents as active agents, not as passive, like just static agents in standard economics, are actually are accounted for into that theory. So as I mentioned in the beginning, it's a way of framing, in general, finance, and in this case, asset pricing, but in general, framing economics into an agent-based theory.
Yes.
Which I think is the right way, because it's how people behave in their economic decisions. So I think it's the natural way to frame the theory.
Okay.
Well,
yeah, just as we're out of time, I'll just for completeness and just for your all's future work, Active Lumology wrote, I hope they discuss how they propose integrating this model into underwriting. Bert wrote, what is epistemic value when actions do not influence the market? And then also Active Lumology wrote about the parameters of defined efficiency and financial modeling. So just a few notes for possibly a future symposium. But thank you all for the awesome work.
Thank you.
Thanks a lot. And for those who send questions, you can send them to me through this email, and we'll get back to you. Thanks a lot for your time.
Farewell. Bye.
Thank you. Bye-bye.
Hello, welcome back. We are with Denise Holt for From Coordination to Cognition, Rethinking Agent Communication Protocols for Active Inference in the Spatial Web. So Denise, thank you for joining again. Anyone in the live chat can ask any questions, and thank you for the presentation.
Thank you so much, Daniel. Thank you for having me. Okay, I'll just jump right in. So today I'm going to be talking about current agent communication protocols that we're using with current AI versus what's coming with the spatial web and active inference. So with the rise of intelligent agents, agentic AI, comes essential need for multi-agent coordination. So as a step beyond reactive chatbots or standalone systems, LLM agents are now being designed to collaborate across tasks, domains, and organizations. But how do we get these agents, these LLMs, to talk to each other, share context, access tools, perform tasks, and make decisions in a way that is secure, scalable, and interoperable? The response has been a new class of communication protocols. You have MCP, which is Model Context Protocol. It's from Anthropic, and this gives agents access to essential data sources. ACP, Agent Communication Protocol from IBM and Cisco, enables structured collaboration between agents. A2A, Agent-to-Agent Protocol from Google, standardizes agent tasks across vendor systems. And then there's ANP, which is an agent networking protocol. And this is open source, and it supports decentralized agent discovery and secure identity management over the web. Now, why do agent communication protocols matter? Each of these approaches has unique strengths and limitations. They're all new, and they're beginning to be implemented, piloted, and standardized today. They just came on scene this last spring. And they help developers solve urgent problems, enabling the first wave of autonomous systems. So they're not just valuable, they're an essential part at this moment in time. And it's agent communication for the World Wide Web. But a larger shift is underway. Parallel to these efforts, the spatial web is rising. We have HSTP, Hyperspace Transaction Protocol, and HSML, Hyperspace Modeling Language. And this forms a radically unified infrastructure to contextualize and connect everything from people and places to devices and data. It enables a globally consistent framework for describing, discovering, and interacting with entities across physical and digital realms. And this framework was ratified by the IEEE, one of the largest core standards bodies in the world, on May 29th of this year as the third official foundational internet protocol, layering on top of HTTP and HTML. And this protocol doesn't just accommodate agents, it redefines the terrain that they operate in. So this raises a pressing question. As the spatial web's universal domain graph begins to take shape, will today's agent communication protocols evolve to align with it, or will they eventually become redundant? These new agent communication protocols reflect a legacy of centralized computing and static data models. Active inference, on the other hand, requires something more: real-time action perception loops, causal modeling, and dynamic adaptation to unfolding environments. The current agent protocols are solving today's problems, but they may not be structurally suited for the agents of tomorrow. So, agent protocols at a glance, bridging the gaps in today's intelligent systems. So let's go one by one just so we can understand what these protocols are doing currently. MCP by Anthropic, the purpose, it provides a standardized way for LLMs or agent frameworks to retrieve structured context like files, APIs, databases, system tools. And it acts as a content feed that simplifies how a model pulls in relevant data. The strengths:
It's simple, standardized integration of tools and knowledge for LLMs like GPT or Claude. It enables straightforward integration, reducing development time and cost. And it enables developers to plug in live information to otherwise static models. But the limitations, MCP agents, they don't reason about the world. They pull in data, they process it, and output a result based on prior training and prompted instructions. You're still dealing with LLMs. The agent's understanding is contextually injected. It's not self-modeled. Active inference doesn't just fetch context, it continuously infers it, updates it, and acts upon it in real time. The MCP model isn't designed to support that cycle. Now, ACP, Agent Communication Protocol by IBM and Cisco, this enables structured multi-agent collaboration between agents in enterprise environments. Its strengths, it supports stateful threads of communication and allows agents to negotiate and reason together across tasks, facilitates task coordination and collaborative workflows, uses standard APIs and JSON schemas, helps AI-driven enterprise applications coordinate complex tasks like order fulfillment, and it establishes clear workflows and roles for agents. But the limitations are it requires a centralized directory for discovery and coordination. And context is carried in messages. It's not modeled internally in the agents. In an active inference architecture, agents don't just cooperate, they co-regulate. ACP enables interagent chat. Active inference agents exchange beliefs, align internal models, and adapt as they act. Now, A2A by Google, its purpose is cross-vendor interoperability for agent tasks between tools like CRMs, HR systems, etc., from various vendors like Salesforce, SAP, Oracle, and others. The strengths, it solves real interoperability pain between tools like CRMs or HR systems or productivity agents by reducing operational silos within your tech infrastructure. It's well supported by major enterprise vendors, and it's built on familiar standards like HTTP, JSON, and OAuth. Now, the limitations, it's optimized for task exchange, but not cognitive computing. So there's no real-world grounding or embodied understanding. Agents operate like modular services in a cloud-native workflow. Active inference agents perform perception, planning, and action within a unified framework. A2A enables interoperability, but it doesn't enable inference. And then you have ANP, and this one is open source. It enables decentralized discovery and semantic identity for agents, and it comes closest to aligning with what's needed for active inference in the spatial web. And the strengths are that it utilizes decentralized identifiers and linked data, potential foundation for semantic interoperability, discovery via open registries and search indexed agent descriptions, and it empowers secure agent interaction without a single point of failure. But the limitations are that it lacks shared global context and transactional knowledge graph that the spatial web provides. Challenges in scalability and real-time context synchronization. It connects agents, but it doesn't connect them to their environments. And it's difficult to scale enterprise-wide without global context management. So to sum it up, you've got MCP, which is easy context access, but there's no internal inference, and it's static and non-adaptive. ACP is for task coordination, but it's centralized and limited semantics, and it's not flexible. A2A is cross-vendor integration, but there's no adaptive context modeling, and it's not context aware. And then ANP is decentralized security, but it has limited global synchronization and it's complex to scale. So, introduction to active inference AI, and this is a complete paradigm shift. The principles of active inference: agents continuously update internal models to reduce uncertainty. It's based on the free energy principle. It employs generative models for decision making and predictions, and it moves beyond reactive machine learning towards adaptive predictive behavior. And you minimize uncertainty. These agents adapt in real time. So why does active inference matter to a business? Advanced AI approach, it's an advanced AI approach that helps agents predict and adapt dynamically, enables proactive responses to emerging business challenges, and it significantly reduces uncertainty and improves operational resilience. Now, generative world models and causal reasoning. Active inference agents proactively model environments. They are continually creating generative models of understanding about these environments. They're simulating multiple business scenarios and outcomes. And this allows agents to understand why something happened, not just what happened. And it improves strategic decision-making and risk management. Now, one type of active inference model is renormalizing generative models, and these are an advanced form of active inference modeling. They're hierarchical and scale-free, and they efficiently manage complexity. They enable real-time modeling and adaptive predictions across domains, efficiently handle complex operational scenarios, and significantly reduce data requirements and computational overhead. So while generative models like RGMs reveal how agents learn and predict, the next evolution, including multi-agent systems, brings physics itself into the inference process, where belief and behavior evolve inside a shared field for multi-agent coherence and belief propagation. So when you're talking about this field of belief for multi-agent belief propagation, there is an architecture called Field of Belief Hamiltonian Monte Carlo. And this takes us from models to fields. It moves beyond hierarchical layers to a unified field of beliefs shared across agents. It has Hamiltonian dynamics. It applies energy-based equilibrium for efficient inference and real-time adaptation. It includes isohedral symmetry. Each agent is seeded from the same geometric program, enabling instantaneous alignment and a silent consensus among the agents. And decentralized coherence. Agents act locally, yet remain globally synchronized through the shared field. And this establishes a physics-grounded architecture for scalable, self-organizing intelligent systems. So given all of that, what kind of communication protocols are needed for active inference? Active inference requires continuous dynamic updating of context. It needs protocols supporting real-time semantic synchronization. And it pushes beyond task-oriented protocols towards holistic environmental modeling. So why businesses need active inference compatible protocols? They need them because traditional protocols lack the dynamic adaptability that businesses require. Active inference demands protocols capable of managing real-time changing conditions. And this is crucial for responsive operations, for customer experiences, and for innovation. So the spatial web, building the world agents can think inside of. So when we look at the spatial web infrastructure and we consider the space between the physical and digital worlds, right? You have connectivity, and then you have this spatial management area that includes things like identity and activity and location. And it's in this space where trust and privacy and security and interoperability lie. So this is a new internet infrastructure layer that unifies physical and digital worlds. and it provides unified context, semantic, shared meaning, spatial and temporal interoperability. And it's a foundational layer that enables complex adaptive agent interactions. So it's the next generation internet that it integrates digital and physical business operations with intelligence layering over all complex systems. And it allows for the coordination of processes, people, entities, and places seamlessly. So what is hyperspace modeling language, HSML? It's an ontology-based semantic modeling that provides universal, consistent meaning and definitions. It describes entities, relationships, permissions, locations, and states. And it ensures clear, consistent communication and interoperability across domains. So when you think of a spatial domain and a web of spaces, you need to know who or what is authorized to access the domains, what content or data is available to view, who can publish or modify content, who can transact or interact within it. So this standardizes business semantics. It provides a universal business language for digital and physical entities, ensuring consistent meaning across all business units and partnerships. So Hyperspace Transaction Protocol. This protocol it provides secure context-aware queries and transactions. It supports decentralized multi-dimensional data exchanges. It enables real-time consistency and context coherence across the spatial web. So it offers secure and context-rich transactions, a secure, trusted method to coordinate complex multi-party interactions. It enables enterprises to respond immediately and precisely in complex environments. And it enables decentralized multi-dimensional interactions across the enterprise. And what it results in is this universal domain graph, or UDG. A decentralized, permissioned, and constantly evolving model of everything. Not just information, but real-time, spatially anchored representations of the physical world. With global decentralized knowledge graph of all entities and states, it stores spatial, semantic, and temporal data. It's a common source of context for agents and systems, and it enables real-time queries and context updates and synchronization across domains. So context is not fetched, it's embedded. Entities don't just reference data, they're part of the global graph. Every agent, location, object, and event can be described, queried, and updated in a universally consistent way. So agents can locate themselves, interpret relationships, and respond to unfolding changes without relying on private databases or hard-coded integrations. So the UDG creates this shared business reality, a common real-time operational view for your entire enterprise ecosystem, and it dramatically improves visibility, responsiveness, and decision-making accuracy. So for active inference, the spatial web offers something profound. Active inference agents operate on the principle of minimizing uncertainty about the world by continuously updating internal generative models of understanding based on incoming data. They don't merely perform tasks. They infer the hidden causes of their observations and act in the world to fulfill expectations while adjusting their beliefs. And this requires a deeply contextual understanding of space, time, causality, and intent. The spatial web delivers what active inference needs. It delivers spatio-temporal grounding. Every entity is located in time and space, enabling agents to align their models with real-world dynamics. It offers semantic consistency. HSML ensures that room, temperature, or flight path mean the same thing across domains. It offers contextual granularity. Agents can navigate the universal domain graph to retrieve just the data they need at the right level of abstraction and scale. and it offers permissioned access and trusted frameworks. And this is crucial for real-world applications. Agents can access content securely and act within regulated boundaries. So the spatial web provides the shared external memory, sensory input, and environmental structure that active inference agents need to operate effectively at scale. So contrasting current agent protocols with the spatial web. Excuse me. So this takes us from API calls to adaptive worlds. The spatial web is not just a medium of interaction, it's a model of the world itself, accessible in real time. It isn't static, it evolves as agents act. The feedback loop between agent and environment is central to active inference, and it's what makes the spatial web a uniquely compatible architecture for the next era of intelligent systems. Where legacy agents process tasks in isolation, active inference agents embedded in the spatial web can act as contextual participants, constantly sensing, reasoning, and responding to a dynamic multi-scale world model. There are architectural differences. With current agent protocols, they're point-to-point versus shared context. Agent protocols like MCP, ACP, etc., they're point-to-point, isolated context, task-driven, and centralized. Spatial web is graph-based, unified global context, inference-driven, integrated, decentralized, and globally synchronized context. So you have centralized versus integrated. Current protocols are narrow task-based communication, and the spatial web offers unified real-time operational visibility and context. So the spatial web supports active inference agents by maintaining a persistent, structured reality that they can pull from, update, and adapt to. Discovery and identity management, isolated registries versus global semantics. Current agent protocols, they're localized states, centralized registries, or basic decentralized discovery. Spatial web is real-time global context management, semantic global entity identification, and universal discovery via spatial web identifiers, which are kind of like URLs, but within the universal domain graph. So in the spatial web, entities are discoverable by meaning, location, time, function, or any combination. And if you look at this graphic that I inserted in here, it's one of my slides that I used often when explaining this, because HSTP and domains in this universal domain graph, these new spatial web domains, they're very different than what we know as a World Wide Web domain. And if you look at current AI, it's built for the World Wide Web. So a World Wide Web domain includes websites and apps. And these serve up content and generate data. And they enable you to do things with that content and data, right? So current AI is built for this system. Now, a spatial web domain is an entity with a persistent identity through time with rights and credentials, defining people, places, things, and rules in machine-readable context and spatial grounding. So active inference AI is built for this new framework. So for high-level causal reasoning of active inference, agents need more than just who to talk to. They need to know what exists, where, when, and why it matters. State management, local versus global. Agent protocols, these current agent protocols, they're local state, tasks, messages, context. And ACP and A2A allow for message threads or long-lived tasks between agents, but the state is local to the conversation. And MCP supports context injection, but not persistent world state synchronization. Whereas the spatial web, the universal domain graph, becomes the single source of truth for all agents. Every entity, event, and state change is part of the global context, accessible and queryable by permissioned agents at any time. To minimize free energy and make accurate predictions, active inference agents must align their internal models with an externally observable state. A common source of synchronized reality, like the universal domain graph, allows agents to coordinate without needing custom logic to reconcile individual perspectives. And semantic interoperability. Current agent protocols, they're message-based formats without shared meaning, whereas the spatial web is ontology-driven, semantic interoperability via HSML. So clear semantic standards ensure consistent meaning so that a term like location or battery status refers to the same concept across systems. And then there's causal reasoning and adaptation, and you have fixed workflows versus embodied understanding. So today's agent protocols treat agents as isolated services, reacting to tasks and triggering responses. Active inference, by contrast, enables agents to simulate multiple futures, plan under uncertainty, and infer hidden variables based on context and change. The spatial web enhances this by providing real-time structured context that agents can reason about causally, bridging the gap between perception and action across a shared world model. This enables enterprise-wide responsive, intelligent decision-making. So active inference agents within the spatial web, this ushers in a new era of autonomous intelligence. Agents don't just cooperate, they co-regulate. They learn, infer, and adapt in concert with their environments. In FOBHNC terms, each agent is a localized excitation within a shared belief field, acting independently yet maintaining global coherence. Agents don't just follow commands, they understand situations, simulate consequences, and act accordingly. And most critically, active inference agents don't need to be tethered to a centralized database or cloud tools. They can operate on the edge, inferring, adapting, and acting autonomously. But to thrive, they need an environment where context is available as structure, not just as data. And that's where the spatial web becomes indispensable. The future of agent protocols in the spatial web era. So navigating the road ahead. The agent protocols emerging today, MCP, ACP, A2A, ANP, they seem to be solving different problems than the spatial web. They manage task execution, data retrieval, peer messaging, and the spatial web aims to model the entire digital and physical universe. But when we examine how these systems interact and where technology is heading, a pattern begins to emerge. These protocols are not competitors to the spatial web. They're early bridges, temporary scaffolding across a digital landscape that's still taking form. They're a necessary layer for now. There's no doubt that today's agent protocols are doing important work. These protocols are gaining traction, not just because they're useful, but because there's no shared substrate yet. Each protocol is a patch for a fractured internet, stitching together siloed APIs, services, and data under a common interface. They're vital in a world where agents are still grounded in machine learning architectures that lack self-modeling, physical grounding, or native contextual awareness. The spatial web, from protocol stack to contextual substrate. The spatial web is not simply a next generation protocol stack. It's a paradigm shift in how agents interact, not just with each other, but with their entire environment. Active inference provides the internal generative model. The spatial web provides the external semantic and spatial context. Together, they enable real-time, scale-free, causally grounded intelligence across distributed networks. In this convergence, the universal domain graph becomes the ambient knowledge base for all agents, no matter who built them. HSML becomes the language agents use to interpret their world. HSTP becomes the protocol they use to act upon it. So what happens to these current agent protocols? Well, in the short term, there's collaboration. Today's agent protocols continue to address urgent interoperability needs. They form essential bridges toward broader spatial web adoption. Midterm, we're looking at convergence. Protocols will begin to integrate or evolve to align with the spatial web standards. Integration pathways, HSML for agent descriptions, HSTP for transactions. Businesses should start aligning protocol strategies with the spatial web principles, and early adaptation will ensure competitive advantage and future readiness. Now, in the long term, there's a risk of protocol inaction. Many protocol functions like discovery, negotiation, task management, they're likely to be natively supported in the spatial web. Interoperability challenges will disappear, and failure to adapt may lead to technological redundancy. And if you look at, the evolution of the internet historically, universal and open standards inevitably replace fragmented systems. Early web protocols were displaced by HTTP and HTML. So with my company, with AIX Global Innovations, we're working on an ecosystem of adoption that includes education and guided activation and tools and solutions, a continuous path from learning to deployment. And if you'd like to learn more, feel free to scan this QR code. It'll take you to Learning Lab Central. It is a global education hub that we have built that is hyper-focused on active inference AI and spatial web technologies. I host monthly learning labs, and we have courses and certifications available there. And it's just a great place to come together as a community and find other people who are interested in building in this field of technology as well. So I will stop sharing now.
Thank you, Denise. Awesome.
Thank you, Daniel.
Okay. Some fun questions in the live chat. So I'm just going to read them off and we'll go with it. Okay. Bert Berkers wrote, when and how can people get started building on the spatial web?
Yeah, that's a great question. And I don't have an exact date. I know that the standard was approved and ratified by the IEEE in May. And I know that the consensus is that towards the end of this year, I'm assuming end of this year, beginning of next year, we'll start to see some tools that will make it really easy to start building, registering domains in the Universal Domain Graph. I know the spatialwebfoundation.org is the authority that will be handling the Universal Domain Graph. And so I'm assuming there's going to be tools that can instantly start to register. And I've seen tools where you can put in documents, you can put in information, it'll register the domains, it'll spit out the HSML for you. And I know those tools are on their way. I just don't have a date for those yet. So I feel like as soon as those things land, then it'll be really easy for people to just start, kind of going to town on this and exploring and figuring out how this looks in the wild.
Awesome. Okay. Scott David wrote, I'll put it in the chat just in case you want to see it. He wrote, what are the steps through which the spatial web and context-rich AI interactions can be onboarded to existing organizations, companies, governments, etc., cost savings, risk reducing?
Yeah, and that's similar to the answer you're going to get that I just gave you. I don't have all those details right now. I know that they're coming. Yeah, I mean, I would keep an eye on the Spatial Web Foundation, because they will be the entity that starts to onboard people and give information on how to onboard and how to start building out in this space.
Yeah, I think it was a great framing and very helpful to get that review of these protocols. And I just got the sense of all these different pairwise or hub and spoke type interaction architectures, but they're still very generic and they're not necessarily about any real physical or embodied space. So some
Right.
domain ontology is still required to have the kind of content of that agent to agent channel be meaningful beyond just being like a handshake.
Right, right. I mean, we're really good at message passing and injecting, data. But you're still dealing with the LLMs, and they have hard limitations, right? And when we talk about active inference and we talk about the capabilities of active inference, we really want to enable all of those within a framework that enables this embodied AI, right? That can tie these agents to the physical world, and this kind of digital twinning of everything.
All right, I'm gonna read a question in the chat, and then I'll just read a few more things that were followed from there. So Alex Sabine wrote, "There are some quite profound ontological implications for humans who share this field of belief with agents. How are we managing the ethical discussions around this?" And then Scott David added to that, +1, ethics is about human ideas about human behavior, so maybe we need new approaches to ethics, more akin to an ethics of treatment of other species, ethics of environment interactions with non-humans. So I know that's a few different pieces, but how do you engage with this at that level?
So what's really interesting to me about that is, when you try to think of, what the approach we've tried to take with, ethical use of AI and, bias mitigation and different things like that, it doesn't really work because you can't. There's no amalgamation of that globally. If you look at our world, you have all kinds of belief systems, all kinds of different cultural differences, all kinds of different governing styles. So you have to have a way that preserves all of that. And so this enables that. The spatial web enables people to be able to build agents from wherever they are in the world, and they can imbue them with their their own beliefs, their own, they can be customized to the various differences and preserve those differences throughout societies, throughout the world, right? So I think that this is the system that will actually enable us to, solve these, create ethical AI localized, right? And then because these agents can share beliefs, there can be a global consensus, of certain things, the same way we've done with human knowledge, right? I mean, the way human knowledge grows is it depends on the diversity in thought and ideas, but we also come together as a species to have a consensus over, larger overarching governing ideas, right? And so I think we're going to see that play out with these agents within this next evolution of the internet as well.
Yes. Okay. You have traveled around and given many educational talks and hosted a lot of learning labs and experiences. So over this last year, what would you say has been surprising or interesting in those experiences? Like, how over this journey have you seen the kinds of questions or interests that people are showing up with in education settings evolving?
Well, it's interesting because I see that people are starting to understand the implications of this. And, it's also really funny because, everybody's been really focused on these LLMs and, current AI because they're amazing. They're powerful tools, right? But I've been out here talking about what's coming with spatial web and with active inference. And a lot of people don't really know what to, or, I for a while I was a lone voice in the wilderness, right? People would be like, I don't really know what to make of it, but this is really interesting because it's right here and it's right in front of me. But that, I think, has helped with this kind of adoption cycle and this understanding, because people have been able to develop expectations for what they really want from these tools. And then they've also had firsthand experience with what we have currently to understand that they have hard limitations and they're not really going to get some of those things from these tools. So I feel like over this last year, there's been a lot more people waking up to the fact of really understanding what active inference offers, the potential of this adaptive, self-evolving, super efficient intelligence and distributed intelligence, getting away from the being tethered to, the mothership of the giant databases and being able to operate at the edge and everything else. So I would say that's probably the biggest thing I've noticed over this last year, is that people are starting to really, develop more of an understanding, expectations, and having the ability to recognize why active inference would be ideal compared to what they're experiencing currently.
Yes, interesting. And then also just sort of on the education wavelength, how do you hold the space and make it relevant when a lot of the models are very technical, or people might not be building Bayesian statistical models in their basement, as some do, but not many. So how do you convey that, or what have you just found interesting or useful about how to bring technical ideas and try to make it relevant?
So most of the people who are attending, like my learning labs and, Learning Lab Central, a lot of them are not technical people. They're business leaders. They're wanting to understand why they need to choose this versus something else, and how it's going to affect their industry, how it's going to affect their business. And, they need this deep understanding about it so that they can make proper choices, moving forward with their business. And so you have to be able to take these complex ideas and make them understandable for anybody. And so that's what I really try to do. And it starts with meeting people where they are. You don't stand over here and talk about something and expect that someone is going to come and just start understanding it eventually. You have to start talking to people where they are, with a common ground of understanding with what they understand. And then you bring them to you. Then you start to guide them, towards you as far as what you're trying to explain to them. So that's really the approach that I take. And so that means, getting rid of a lot of the jargon and just, talking in plain terms, but I think a lot of it too, there's a lot of moving parts to all of this. So repetition is important, people being exposed to the ideas over and over, and maybe exposed from different angles, and that helps to kind of bring this cohesive understanding together.
Yes, all makes sense. What are you going to be most looking forward to? Like, what will reduce our uncertainty the most in the coming months or in the year ahead?
There's a lot to look forward to. One of the things that I'm doing with my company is really focusing on establishing this ecosystem of adoption. And, I know that as these tools become more and more available, the ecosystem of adoption has to be able to scale with the demand. And I mean, if you look at the reality of what active inference does, what the spatial web does, and we're talking about the internet, right? And we're talking about this layer of intelligence that will be operating throughout this new expansion of the internet. This is going to affect every industry across the globe, every business, and anybody with a website or an app is going to need to evolve their presence to take advantage of these new capabilities. So the demand is going to be high. And so with my company, what I've been trying to really wrap my head around is how do you scale for that demand? How do you scale the adoption for that demand? So those are the problems that I'm attempting to solve. And so it's exciting for me because I really see the framework starting to be established within my company for that. And so I'm really excited for that. I'm excited for what's coming in the next 6 months, 12 months.
Very cool. Any last comments or anything else you want to bring up or ask for people to consider?
You know, Daniel, I just want to give you a big shout out and thank you. You do so much for the active inference community. And, you know, I think a lot of it's done behind the scenes. And I, for one, am really grateful for you. You know, and I'm always here to help support the Active Inference Institute in any way that I can. I think that what you guys do is a phenomenal job at putting education out there for active inference. And, you know, I have a whole section for you on Learning Lab Central too. So in the resource locker, and I'm just very grateful for you and all the hard work that you do.
Thank you, Denise. It's a team/ecosystem effort, and it's really exciting times. So, thank you.
Absolutely.
Till next time.
All right. Thanks so much. Thanks everyone for tuning in.
Bye. All right, we're back for our final live presenter of the day. Viet Dung Nguyen will be presenting on active neurorobotics, deep prior preference learning guided by learnable goals. So thank you, Viet, for joining again, and for the NAC Lab for sending their students to present. Take it away.
So yeah, thanks Daniel for having me today. I'm Viet. I'm a PhD candidate at Rochester Institute of Technology. I'm currently working with Dr. Rabia in the Neuroadaptive Computing Lab. And yeah, today I will be discussing our work, active neurorobotics, deep prior preference learning guided by learnable goals. So first of all, I want to talk a little bit about introductions and motivations. Yeah, so we can see nowadays there's a lot of applications of robotics in several different fields, right? So for example, robotics can be applied in industrial manufacturing. For example, speeding up assembly processes in factories, can be applied in healthcare, can be applied in farming, agriculture, and constructions, right? It can also be further applied in locomotion, for example, self-driving car and space exploration. But there's several problems in this, where most robots cannot operate and learn autonomously. And then they actually cannot adapt to new environments as well. Right? And generally, training a robot learning algorithms actually costs a lot of amount of resource for data collections. Costs a lot of money, right? And then the safety measures of robots are often not learned, so it cannot be flexible enough to work safely around humans. So to overcome these barriers, right? Research has actually investigates different ways to tackle this. For example, one ways to tackle this is to investigate neurorobotics, which is a subfield of robot learning. Basically, it's model the robot's learning process, very similar to that of a human. So a biologically inspired autonomous learning system often investigates human perception, memory, attention, sensory motor control, and so on. And so this neurorobotics field also features robot learning from real-world interactions or online learning. Right? So with online learning, robot can adapt to new environments with less data collection cost, and then can be learned to be safe around human. So first of all, we need to, in order to do like neurorobotics, we need to investigate cognitive architecture. So the cognitive architecture is very much studied in the active inference process theory. Basically, it investigates different modules inside the brain that can be used to learn a perception system, right? So first of all, there's like the generative model, which is basically the perception system itself, right? So it's basically trying to, through the sensors, making observations in the environment, and then learn the actual interactions between the environment and the agent. The second one is the motor, which is the action controller. Its actual the action will be taken by the agent and then executed inside the environment to return a new observation. And then there's like the memory module, which stores the interactions between the agent and the environment, right? So that memories will be stored in here in order for future use of like training or just maybe remembering of knowledge and knowledge purifications, for example, or distillations. And then there's prior preference. So basically, the prior preference distribution is trying to predict the desired representation or the desired goal that the agents want to achieve in the future. So generally in active inference, a prior preference distribution is provided in advance. But in our work, we are trying to have like a separate neural network to predict the prior preference in the future dynamically. And so the last one is sensors, right? Like for example, the robot has like eyes and arms and so on. So before going to the main topic, I want to touch on a little bit about deep active inference and the background around it. So basically, the interactions between the agent and the environments can be described as the interactions between the generative process and the generative model. So first of all, is the generative mode process. Basically, it's the real-world environment itself, right? And inside the real-world environment, there's like a hidden state. So this is like the true probability distributions of the environment, and we cannot actually see it. And in here, we can see that there's an arrow between the true state and the observations, which means that the generative process actually generates the observation that can be observable. Right, so the agents can actually see these observations, and this, when compared to like, it is very similar to a partially observable Markov-decision process that is often formulated in the reinforcement learning literature. So now when we have the generative process, we have the generative model, which is the actual agent itself. Right? So the agents also have a state distributions here. Right? So it is actually the agent's best approximations of this generative process basically it's we can call it like a dynamic state or a agent's belief state, right? Or a world model state, however you want to call it. So this state distribution will be best estimates of the hidden states inside the environments. So the hidden states here can be like the world dynamics, for example, or the physics, or the logic of the world, for example, something like that. And in active inference process theory, the agent's basically continuously trying to make the observation through time, and also continuously modify its belief after making the observation. So, how do we further formulate this? First of all, we have the agent states here, right? It is like the initial belief or representation or the world dynamic states. Right? It's gonna be called the prior over state, which is P of S. And then we also have P of O, which is the model evidence, which is the observation distribution. And then in active inference, we're trying to have the agents both observing and predicting, right? So first of all, we predict the observations, which is basically the likelihood observations. It is the agent's best estimate of the observation distribution given like the prior or the posterior information that it have. And then finally, the P of S given O is posterior function. Basically, it's the agent's best estimate of the state after making the observation. So it's gonna be after making observations, it's the agent's actually making or changing the posterior belief, right? So now we have like all these definitions of all these functions. How do we learn this generative model? So we have to learn first of all the likelihood functions, and then the posterior approximation, right? And then we have to best estimate the model evidence distribution here as well, right? And then we estimate the posterior and then the prior, right? So how do we learn this? So active inference process theory is proposed that we trying to minimize the variational free energy or the marginal free energy amount. So in order to do that, we first have to predict the likelihood of the observation, right, or the model evidence. So in deep active inference, generally, this is actually called the decoder, and it is often parameterized by a neural network. Next is the posterior functions, right? So at the same time, when we're trying to predict the observation, we also have to make an observation, right? And then we produce the approximate posterior at the current time step. Right? So in deep learning literature, this is often called an encoder, and it is also often parameterized by a neural network as well. So in here, active inference says that we have to trying to continuously correcting the belief after making new observations, right? So we are trying to minimize the KL divergence between the belief states after we have made observations and the belief states prior to making the observation, right? So we're trying to minimize the surprise between those two kind of distribution. That also means that we're trying to minimize the KL divergence between the posterior Q of S and the prior P of S. So this is also means that we are trying to correct the belief after making new observations. And then next is in parallel to minimizing the uncertainty between the posterior and the prior, or the surprise between the posterior and the prior. We also have to maximize the prediction accuracy of the observation as well, right? So in this case, we are trying to maximizing the similarity between the true observations and the predicted observations. This is also called maximizing model evidence. or maximizing observation prediction accuracy. And we do this by minimizing negative log likelihood of the predictions. So that is for like one step, right? And now we want to extend it to multiple steps, and then we have to integrate actions here as well, right? So at the time step T, there is several different there's hidden states, right, that produce the O of T, which is the observation that the agent can see, and then the S of T is like the actual initial it can be prior or posterior of the agent, and then there's the actions of the agent that the agents like plan to take, right? So when the agents take the actions in the environments, it is executed and it's produced a new state, a new hidden state that we cannot see, and it produce a new observations, right? At the same time, the agents can estimate the next state given the previous state ST and the action ST. It can estimate the next state ST plus 1 here. And then we do the same process, right? So ST plus 1 here is actually the prior of the next state. And we can do the same process by predicting the observations of the next state. And at the same time, we observe the observation of the next state and then encode it to an approximate posterior. And then we minimize the variational free energy by minimizing the KO divergence between the posterior and the prior, and then maximizing the prediction accuracy by minimizing negative log likelihood of the prediction OT hat plus 1. So here's the formula for the variational or marginal free energy. You can see that in here, there's like a complexity term where it's minimizing the KO divergence between the Q of S given O and P of S given ST plus 1 minus AT plus 1 and AT plus 1. It's basically the previous state and previous actions that's caused the current state, right? Leads to the current states in the current prior. And then this complexity term is like measuring the amount of surprise that we want to minimize. And then finally, we have like the accuracy term where we are trying to maximize the prediction accuracy of the observation. And so we're trying to minimize the negative log likelihood of the prediction observation distribution. So now when we have done the learning for the world model or the generative model, we have to learn the policy as well, right? So we have to know a way to like decide like what kind of actions should be executed in order to optimize or solving the task. So there's so many action that can be taken in one single time step, and each of those actions can lead to like different possibilities, right? So the agents can like estimate like each possibilities based on like previous actions and the current belief, right? And so on, right? So there's like as the time steps or the horizons spans out, the number of possibilities of the belief states actually goes up a lot, right? So how do we choose the optimal trajectories of actions that we want to take? That brings us to the expected free energy, right? So we are trying to say that whatever kind of trajectories in the future that yields the lowest expected free energy, then we choose that as a optimal trajectories of actions that we want to choose, and then we learn the policy from that. That's exactly like this. The expected free energy is eventually decomposed into an epistemic term and an instrumental terms. So in this topic, I only focus on the instrumental signals. So the theta here is the neural networks actually parameterized by theta, right? The pi is planned action, right? So the instrumental signal is decomposed in here. It is, we can look at like all these three terms. First of all is the estimation of future observations here. And then Q of S given pi is basically the approximate posterior in the future like given the policy in the future, right? And then there's log of P of O given log of P OT. It's basically the prior preference distribution at time t. Generally, in active inference, right, we provide the agent with the prior preference distribution in advance. But I've mentioned before, in our work, we will predict this kind of distributions so dynamically, right? So that the agents can follow its own wanted or preferred trajectories and learn the policies that can follow the preferred trajectories. So yeah, that brings us to the main parts, active neural robotics and goal-guided preference learning. So before going to the main topic, it's basically I want to reiterate a lot of problems in current model-based robot learning nowadays. So popular robot or model-based robot learning algorithms often deploys the offline policy onto a real-time robot. What does it mean? So it's basically it's learn an offline policy, and then it's evaluated in the real time. Right? So there's little to no online learning capabilities. Second of all is they do not leverage the concept of prior preference learning, so no goal predictions. So the agents might not know what it wants, right? Most of the algorithms actually only maps from the vision or the language or both directly to the actions. That means it is only learning, it's only treating all these experience as identically distributed, independent and identically distributed. Right? And then next is it depends largely on expert demonstrations. So if there's little to no expert demonstrations, then the policy will suffer from suboptimal policy. Right. Another problem here is nowadays we can see that a lot of big or large organizations doing like all these vision language action models. Like there's foundation models and fancy and so on, right? So all of this is just come down to training a very large model that have a very large language model and large vision model, and then encode that with transformers and then map it directly to the action tokens. Right. So this is basically a schematic of model behavior cloning and imitation learning. Right. So in this case, expert demonstrations are treated as identically and independent distributed. Right. And every single interaction is put into like a single data set, and then it's trained, right? And then it's gonna be evaluated in the real world or in simulations. So this is more like a supervised learning setting where they could yield a lot of problems. The classic problems here is mentioned by also Sergey Levin and a lot of other popular people. Is cascading problem, right? So cascading errors actually accumulates over time in actual trajectories because of like the domain data, the domains that's the expert demonstrations is trained on, is used to train on the robots. It's different from the actual real world domain, right? So it's kind of similar to a data set distribution shift or domain shift. And therefore the robots actually deviates from the demonstrated examples, and then this leads to policy collapse in real-time or online executions. So, right. So in here, we are trying to develop a very intuitive way of overcoming all these problems. Right. So behavior cloning and imitation learning, they actually can learn to match the expert performance at best, right? and the expert policy is potentially suboptimal. As you can see in the figure on the right, we can see that like behavior cloning in red, for example, it's gonna be solving all these. It has like the reward trend. It's very low. For example, this is like the suboptimal policy. It's learned through expert demonstrations. For prior preference learning, right? The agent first learns to predict the expert trajectories as its prior preference, and then throughout several interactions or further interactions between the agents and the environment, the prior preference learning model can try to dynamically produce more optimized goal trajectories or more optimized prior preference trajectories. And so the predicted prior preference trajectories will actually eventually be better than the expert demonstrations. And then we can see that the dynamic prior preference is independent of potentially suboptimal expert demonstrations. So that is the intuition of the method. So in our work, we also have a generative world model. It is also very similar to what I've talked about in the deep active inference background section. But in here, there's a little bit difference. We have another model. So in this case, the similar thing is we still build our generative models on the concept of a world model, which is basically dates back to David Ha. And yeah, so we still have like observation. We have like encoder posterior that encodes the current observations, and then we have like the transition model that predicts the next state prior given the previous state and the previous action. So this prior will be reserved as the prior informations prior to making the observations of the next state of the next time step. And at the same time, we also have like the observation at OT, right? And then we encode it to an approximate posterior. So at the same time, we have like two kind of states. One is prior to making the observation, and one is after making the observation. And then we also have the decoder reconstruction as well, where we have the posterior and then we reconstruct it in order to predict the observation. And then we also have the complexity loss, which is the chaos divergence between the posterior and the prior. We also have the accuracy loss, which is the negative log likelihood of the predicted observation. There's a difference here, right? We have the RSSM, which is basically called recurrent states, recurrent state space model, right? So this actually is very simple, and this is introduced in the Dreamer series from Danijar Hafner. So the RSSM is here's the inside of the RSSM. Right? So we still have like the encoder posterior in orange here, and then we have an additional recurrent neural network. Normally, it's a gated recurrent unit. It takes in the recurrent state, and then it takes in the distributions of states posterior, and then it's predicting the prior of the next state itself, and then it's also predicting the recurrent state HT or the deterministic state. The next prior over state is often be called stochastic state. Right, and this HT is also serve as an input into predicting the next state posterior, in addition to the next observation OT. Right, so now we have trained our generative world model, that is RSSM, right, we can now learn the prior preference model, right? So learning the prior preference model requires, I'd say, requires the state of the world model itself. So in this case, we are trying to propose a dynamic contrastive learning system where CRSPP is contrastive recurrent state prior preference model. Basically, we're trying to keep the RSSM the same or fixed when we are trying to learn the CRSPP or the prior preference model. So the point or the goal of learning the prior preference model is trying to have that model predicting the optimal trajectories, right? The optimal trajectories of the state in the future, such that those state trajectories represent the goal or the preferred state, or however you want to call it. So in order to do that, we have to collapse the states of the prior preference model to the states of the RSSM whenever the trajectory is successful. And in contrast, we have to pull away or push away from the RSSM state when the trajectory is not successful. Right? So in order to do that, we have to introduce a term called rho, or prior preference rate. So we're literally saying whenever the trajectory is successful, the rho is positive, right? This positive term will collapse all these two states together, right? And then whenever the rho or prior preference rate is negative, then these two states are pushed away from each other, right? So when we keep the state of the RSM fixed or stop the gradients at the RSSM, then only the state that get pushed and pulled is the state of the prior preference model down here, right? So in the end, right, the CRSPP or the prior preference model will learn to only predicting the optimal state of the RSSM without predicting the failing states, right? So you can see that in here, there's a little bit difference, right? So the RSSM is not conditioned, or the RSSM is conditioned on the actions, right? But the CRSPP or the prior preference model is not conditioned on the actions, right? This basically trying to say that give me an observation, I will predict future trajectories that is needed, or future goal trajectories that is needed to be in, or future optimal state that is needed to be, that the agent needed to be in. So eventually, we will use these goal trajectories to guide the policy learning, right? So now there's here's an example of how we calculate the prior preference rate rho. It's basically we are trying to say whatever the immediate step that leads to successfulness of the trajectories, then that one will have the most strength of collapsing two states to each other. That the two states of the RSSM and the states of the prior preference model. Right, so we can say that whenever the trajectory is successful, for example, the car is in the flag right here is successful, then that's prior preference rate at that point is 1, and then we decay backward. Similar here, the push button, we also decay backward. On the other hand, when the agent is in an unsuccessful state or trajectories, for example, then the prior preference rate will be -1 near the unsuccessfulness state, right? And then we also decay it backward. So here's an example of positive rho that is used in the successful trajectories. So in here, when the positive rho is used, these two RSSM states and the CRSPP states is collapsed to each other, right? And the CRSPP has been able to predict all the state of the RSSM that is successful, right? So here's an example or example representation of the CRSPP state, which is trying to predict the successful trajectories. And for example, in here, there's negative rho. When the rho is negative or prior preference rate is negative, these two states from the RSSM and the CRSPP is pushed away from each other, so that the CRSPP will not predict any failing goal or failing states from the SSM. Right, so there's no complexity objectives here, no chiral divergence between the posterior of the CRSPP and the prior of the CRSPP. So throughout time steps or future horizon, which is in the x-axis, right? So we can see we have like two environments in benchmark here. First of all is the observation, which is the first line, first row. Second row is the prior preference rollout. So we plot it in order for visualization. So we can see that throughout all these observations, the car has to go to the left in order to build enough momentum to go toward the right hill in order to reach the flag. Otherwise, it cannot. Right. So we can see for every single observation in the mountain car environment in the top row, we can see that the prior preference rollout is trying to predict the goal that the car needs to be in. Right. For example, in here, the first observation, the car is in the middle or the bottom of the hill. Then the prior preference trying to predict the car is trying to going to the left in order to build momentum. And then until like the frame number 5 and 6 and 7, the prior preference model is trying to predict the goal of the car is fully moving toward the right. And in the next benchmark environments, it is also happening the same case, even though there's a little bit of noise here. But we can see that the prior preference rollout wants the agents to push the button, right? So it's trying to predict the preference rollout. So we are halfway there. Now we need to integrate the language part, right? So when we want to compete with like all these vision language action models, very popular, for example, like RT1, RT2, right? We also need to have like some form of like multimodal encoder, right? So it is because language instruction or dynamically provided goal can be considered as a form of observation, right? So in this case, we can use like pre-trained large language models as frozen feature extractors, for example, GPT, Llama, T5, and so on, right? And then there's vision encoders. Basically, it's trying to extract real-time observation, and we can just train it as normal. So generally, I often saw people do trainable text encoder as well. But generally, it should not keep the same embeddings and integrity of the language encoder. So there's a lot to be experimented. So what I'm trying to say. And then finally, right, we have like the language embedding and the image embedding, right? And then potentially we can have like several other modalities as well. But here's like I demonstrate the two case, most common case, right, with the language and the vision, right? Then we concatenate them together as embedding, like a 1D vector. Right? And then it's going to be further also known as modality fusion techniques, meat fusion. And then this can serve as the observation embedding that can be fed into the posterior network. So in here, right, you can see that the multimodal encoder is producing all these, for example, embeddings, right? This embedding is fed into the posterior network as normal in our system that we have described, right? This is the RSSM. And then we can see that the posterior trying to feed in the recurrent neural network, and then it's producing the deterministic state. At the same time, the recurrent network also predicting the next state prior distribution, or the stochastic states, right? And then the deterministic states also affect the predictions of the next posterior distribution as well. So we can see that this is kind of like a multimodal world model system where it can execute actions guided by the language instruction. So now that we learned the world model, right? We also need to learn the prior preference model as well, right? So notice that here is the CRSPP without the language input. Right now we need to expand the CRSPP modules with so that it can be guided by the language as well. So that's the prior preference model can predict the optimal trajectories that is conditioned on the language, right? So in here is the actual way that we did it. The CRSPP is now can be conditioned on the language model. The language here is basically can be encoded using all those models, large language models, for example, GPT, Llama, right? And then we do the same process as well as I described in the previous slides. So now we need to learn the policy as well, right? So after we have like the generative world model, we have the prior preference model. Now we need to find a way to like determine the robot's actions, right? So when we are trying to, there's a lot of popular actions determinations models, right? So when we're trying to do that, we have to be very mindful of like what kind of policy learning that yields the best performance as well as efficiency. So there's two competing methods. So first of all is cross entropy methods, where trying to say for every single step, we sampled n Gaussian distributions of actions. Right? So usually n is 1,000, and then we're trying to prune all these distributions using like the world model and the preference model to estimate the scores of all these possible trajectories that is yielded by all these 1,000 Gaussian distribution of actions, right? And then after that, we tried to take the top k, maybe k is 30 to 50, normally 30 to 50, and we choose the best k performance trajectories, right? And then we take all those actions to make a new mean and the standard deviations of the action distributions, and then we initialize. We sampled n Gaussian distributions again, right? So we trying to iterate those like 5 times, for example. Normally it's 2 to 5 times, and optimize the actions populations. So generally, this process is very slow. We have to do it for every single time step. That will yield the computational time complexity of like O of n by k. Basically, n is like the populations and k is the iteration numbers, right? So imagine we have to forward the world model 5,000 times for every single step that we want to take the actions, right? So it's very slow. So other methods here can be actor critic. It is very classic in a reinforcement learning literature, and it is faster because we only need to make one single forward pass in the world model, and then make one single forward pass in the policy model. So in order to learn this model, right, we trying to have this state dynamics model here, and then it's produced a representation and the preference states throughout all these trajectories rollout, right? And then we can use the representation and the preference to compute the instrumental signal and the epistemic signal. For example, the representation and the preference can be used in here is basically, for example, instrumental signal can be computed by the difference or the divergence between the representations, actual representations, and the preferred states that the agents want to be in, right? So if it's far away from each other, then the instrumental signal is low. Basically, it's the score of like rewards is low. And on the other hand, right? So if the actions that use the representation that match our preference or goal or predicted goal, right? Then the score, internal score should be like higher, right? So it's, and then for epistemic signal here, basically we're trying to boost the explorations of the agents, right? We are trying to say that the agents want to take actions that potentially reduce the uncertainty in the futures, right? So uncertainty can be in several different ways we can understand it, right? So uncertainty in the agent's knowledge, right? Or uncertainty in the agent's, or uncertainty in the environment itself, right? So to reduce the uncertainty, we have to take action, like appropriate actions that explores the agent, explores the environment enough, right? And there's also other epistemic signal that is investigated in by Carl Friston as well. So it is a beautiful literature. So yeah, we use all those compute all those scores, and then finally we accumulate them to compute the advantage value and return value. This will serve as the label for the value models to predict the return, right? And then finally, we learn the policy learning by backprop through the value model or value network, right? This is also called policy gradient. So yeah, after like learning the world model, the prior preference model, and then the policy model, right? Now we are able to actually perform online learning in simulations and real world. There's several different benchmarks to it. So there's first of all the front car kitchen, which employs front car kitchen robot arm. There's a lot of tasks, 8 tasks. For example, the robot has to open the microwave or turn the switch or move the kettle and so on, right? And then there's also Meta World, where the cellular robot arm is featured with over 30 manipulation tasks. And then there's RoboSuit, which is a very classic and popular benchmark for testing robots algorithms. So it features so many robots, but in here we actually use Panda robot arm with a total of 20 plus manipulation tasks. And in the future, we also may want to integrate real-world robot learning as well. So here's our preliminary results. We have compared our agents on the top left here. We have compared our agents with a lot of other state-of-the-art benchmarks or baselines on different benchmarks, right? So we have like Dreamer v3 and deep active inference variational policy gradients, right? And then some other active inference baselines as well as model-based reinforcement learning baselines. In general, we have our agents actually has the best performance in most tasks, and it usually converge faster and learn to solve the task faster, as well as can solve complex tasks where other agents cannot. For more complex tasks, for example, where the tasks requires completing multiple subtasks, for example, and then it's gonna have the language instruction here as well. For example, open the microwave and then move the kettle and then finally open the slider. you can see that the robots actually do according to the language instruction. Yeah. And then after that, we also test on the robot suite as well. For example, in this case, open the drawer, pick the cup, place the cup into the drawer, and close the drawer. We can see that the robots actually have a little bit of struggles to put the cup into the drawer, but eventually it did it.
Yeah, just while you're on this slide, how does the model come to understand the semantics of what a cup is? Is that the vision model connecting it to the embedding, or how does that?
Yeah,
how does it know what a cup is?
So it doesn't know by a concept per se, but I'd say like all these actions is encoded based on the visual information that is received. So it's basically the robot has received the information of both views, like from this view and from this view, and it's kind of encode, like use the convolution neural networks to like encode the perception informations into some form of a state, and then use the states to decide on actions using the policy network. Did I answer your question?
Yes. So it doesn't necessarily have a like a knowledge graph world model, but
Yeah.
it uses the embedding. So then if the model could represent a chair, that would go from the visual input to the embedding space of chair. That gets hooked up with the. But then how does it know how to? If you said put it to the left of there, how would it know that?
Right. So in this case, when we have like expert demonstration data, right, it kind of have like the initial understanding of like each pixels is on which pixel, right? So there's like different set of pixels inside the visual image that's kind of activates the representation that can yield the policy activations, and it's trying to solve, trying to like actually do solving the task. But if you actually move the cup to the left a little bit, it will still struggle, right? Because the distribution of pixels now is different, right? So I think it's gonna be totally dependent on like the distribution of pixels. It's very susceptible to like the image quality and stuff. If it is like different from the image quality of the expert demonstration, then it will struggle. So to answer your question, there is no knowledge graph or I'd say causal model that's the robot learn. So there is no causal model and no concept models. It's just the representation or like the embedding that is learned from the distribution of pixels throughout the encoder or CNN. And by that we called all those representation the approximate posterior and the prior itself. Yeah.
Yeah, that's very interesting how even without the formal causal model, you could still in language say something like, move the cup to a place that will look better. But then that implicitly entails a causal model of how actions would lead to something looking better or looking different. So there is a sort of way in which the causality is at least actionable, even if it's not represented in that declarative way.
Yeah. And then, yeah, I'd say there's also failure case as well, right? So this is because like there's like the pixel distributions kind of different from trajectories to trajectories. Right? So, for example, with the same prompts right here, and the distributions of like action of the robots is different as well, then the robot will struggle to interact with the environment and use the optimal trajectories. So yeah, it's because, for example, the robot like moved the kettle, but now the kettle is in different position as the learned one, right? So it's gonna be struggle to like having all those informations encoded into the policy, and the policy making appropriate actions to solve the task. So yeah, that is one challenge. There's also other challenges as well. For example, you can see that's like the in the figure on the right here, right? We can see like this is an example of like the inability to predict different blocks in the language table benchmark. So this the figure on the left is the true actual observation that the agent saw. But in here, like the agent actually predicts the observations, like has no blocks at all, right? So you can see that like the subtle changes in pixels cause the agents to struggle to predict, especially in the environments that have like so many different blocks that is like in subtle pixel, right? There's small pixels inside the environments, and then there's like all the trained interactions and observations as the subtle pixels varies, right? Have all these blocks like varies in positions, in size, and in colors, right? So this actually caused the agents to predict all these frames with disappeared block. And then there's also other several problems as well. For example, like decoder learning is computationally expensive, and then research work has investigates encoder-only active inference model. For example, in the very popular paper from NeurIPS, it's contrastive active inference is also that paper that investigates the encoder-free active inference. Right? And then experimental design. Finally, yeah, right. It's also challenging, right? Because experimental design for real-world online robot learning is something that's not usually possible, because we have to design the reward function, right? We have to design the reset functions, for example, for every single episode, right? We want to reset the state of the environment. We cannot like use the human to like manually like reset the state per se, because the real world is kind of like a single live process where it's like one episode, one trajectory is like long forever. It doesn't reset, right? And for example, in here, for example, pick and place the block. The robots can play around with the block inside one episode, but when it push the blocks away, then technically the environment needs to be reset. But there is kind of to build a system that's trying to pick and place the block and put it back to the initial position so that the robot can learn. It's either chicken and egg problem, or maybe we need like a larger system to be, and it's very tedious to set up, for example. And if we can use like human to like manually pick and place the block, it would cost a lot of effort and time and money for data collections and stuff. So that is also very challenging to design a real-world online robot learning experiment. So that concludes my presentation about our topic. Thank you very much for having me. If you have any question, feel free to mention. Thank you.
Awesome. Very comprehensive presentation. I'll just see if anyone in the live chat wrote a question. Meanwhile, though, what stage are you at in your PhD, and what are you looking to kind of get towards with this phase?
Yeah, so I'm currently a fourth year PhD now. and I am very active in developing different robotic learning algorithms using biologically inspired algorithms and active inference. Right? So I focus on building all these generative world model and making use of all these concepts that active inference literature propose. And all these mathematical concepts as well in active inference. So I think it's very interesting to further extend this to like real world robotics, humanoid. It's very interesting to like say a humanoid can automatically or autonomously explore the environment in order to do save and rescue operations and stuff, for example, right? Or it can do like autonomous explorations of like deep sea mission, for example. Or we can send like humanoid robots on like Mars, for example. It's gonna be a long way, but it's inspiring me so much about that. Yeah.
Cool. Okay, from the live chat, Jason Fox wrote, what number of expert demonstrations did each task require to train a good prior preference model?
So in previous research of R, we used 5 trajectories. Generally in RT1, RT2, they use like several thousands in order to do like a single task. But in our task, we use 5 trajectories. Yeah.
Yeah, that was an interesting part with the behavior cloning, but then there was a second plateau of performance with the secondary prior shaping. So what is the lift or the improvement from the expert trajectory? What is that secondary improvement? And then do you think that that could be replayed back to a human expert to kind of update their improvement? Or is it learning a technique that doesn't really, for some reason, it's more optimal, but not for a human or something?
So yeah, when we say it's gonna be learning the suboptimal policies and then be better than the suboptimal policies, we're trying to prove that our algorithms kind of use less expert demonstrations than like normal behavior cloning, and eventually, right, the prior preference model predicts the expert demonstrations accurately, right, and then eventually through the process of self-imitation learning, right. So when we're trying to collect all these interactions from between the agents and the environment, eventually the agents also explores the environment, right? When the agent is currently having like suboptimal policies equal to the expert demonstrations, it also explores the environment using the epistemic terms, right? And then it can try to explore the more optimal policy. And then now when we have like further interactions between the agents and the environments that is more optimal than the suboptimal policy, we save that into the memories, right? And then the prior preference model will look at those memories and then see that, oh, this one is a better interactions. This one is a more optimal than the suboptimal trajectories from the experts. Then the prior preference model will try to learn that and try to predict the more optimal one instead of now predicting the suboptimal expert trajectories, right? So with that, when the prior preference model predicting the more optimal trajectories, now it can guide and influence the policy learning, right? So that is the reason why the agents can outperform the experts in case of in case here we leverage like self-imitation learning and prior preference learning. In case, to answer your question about can we go back and improve the expert, I would say yes. There's several different ways to achieve this, right? So we can treat the prior preference model as another expert, for example. And then we have the expert model, right? We have the expert model, and then now the role is changed, right? The main agent, the active inference agents now is an expert, and then it's trying to interact inside the environment, and then produce all these sort of interactions between the agent and the environments, and then all these interactions saved into the memories, and then the memories used to train the experts using normal supervised learning. So that would increase the amount of increase the optimality of the expert itself. So yeah, so did I answer the questions?
Yes, cool. Anything else you want to mention or point towards?
I think for now it's good. Yeah.
Yeah, that was an awesome presentation. Really cool to see how going from that basic state estimation, this project is really taking it all the way through the vision, language, action models, and cool to see. So thank you again, Viet, for joining. See you next time.
Thank you.
Bye. Okay. Next, I will play a few pre-recorded videos. We're over with the live presentations for day 2, and those will return tomorrow. I'm going to play several pre-recorded videos, and we'll see how far we get on this stream. First video is going to be a 57-minute by J.F. Kotcher, research fellow at the Institute. So here it goes.
My name is Jean-François Cloutier, and I'm a research fellow at the Active Inference Institute, where I carry out a research project in artificial agency. The title of my talk is The Phenomenal-Logical Robot. So my research project asks the question, what does it take at a minimum for an autonomous robot to learn to survive in a world it knows initially nothing about? So in the hope of finding answers, I'm programming a mortal robot to have felt experiences, to make sense of them, and to grow the agency it needs to survive. The robot in question is a rover made of Lego EV3 parts that is equipped with a variety of sensors and motors. So what this project is not, first of all. Well, this is not an input-output simulation of human-level cognition, which is what LLMs do. It is also not meant to be a general model of cognition. It is, at best, an attempt at implementing one form of basal cognition for a simple robot. This is not a robot solving free energy principle equations in the same way that bacteria do not do math. And this is not a robot as an extension of its programmer. Very importantly, the robot's experiences are not going to be grounded by its observer. It has to make its own sense of its own reality. So what is this? What is this project? Well, I want to achieve basal cognition, not simulate the more complex human cognition. I am building an artificial agent, not proposing a general model of cognition, though this project is principled. Free energy principle is applied here as an analytical framework, not in implementation. It will be used, but a posteriori. And finally, experiences are to be intrinsically meaningful to the robot, and not necessarily to me, its programmer. So this project is a learning by building exploration, which is at the intersection of phenomenology, active inference, and agency. Phenomenology seeks to determine the essential properties and structures of experience itself, and to provide an objective account of subjective experience. So what is experience? And not, is this experience correct in terms of some objective reality? Active inference. Well, according to active inference, an enduring self actively infers the causes of its sensory input and shapes its niche to minimize prediction errors. And agency? Well, agency is the ability of a self to act purposefully, to achieve its own goals in an uncertain world it experiences. So my project is to program a robot so it learns to survive by experiencing, engaging, and making sense of its world. And the robot is to do so all on its own, unassisted by its programmer or some observer. Okay, so first let's look at the principles guiding this project. Well, to have agency, a self must be mortal. We take that position. I take that position. Agency implies a self that is distinct from its environment. I think that's pretty straightforward, though the self is not disconnected from its environment. So distinct but connected. The self is not a thing, but processes that are organized to endure. In other words, a self is a dynamic organization of processes that constrain and sustain one another. The organization is not fixed, but can adapt to avoid dissipation. What matters is the lack of discontinuity. The self's overarching goal is to survive, and survive in a dissipative environment it depends on. The processes that produce the self must adapt their organization to preserve continuity of being. The self strives to remain a self, but not necessarily to stay the same. Mortality is critical because it introduces value. What helps the self persist is good for it. What threatens to terminate it is bad for it. Value is subjective. Here we see a small bacterium that's breaching a larger one to feed on its insides. Or clearly, what's good for one is bad for the other. So for our purposes, let's define an agent as a mortal self choosing how it survives. So to survive, an agent must make enough sense of itself in its environment to predict well enough the consequences of its actions or inaction. To endure, a self must have felt experiences. That's very important. So what are experiences and where do they come from? First of all, well, the agent's environment impinges on its senses, and so do the agent's own actions. The agent must constantly process streams of multimodal sensations. the agent integrates these sensory streams in space-time in order to create its experiences, actively create its experiences. So, for example, when I bite into an apple, I experience its taste, crunchiness, color, weight at once in unified moments of experiences. It's worth noting that an agent need not be aware it is having experiences in order to have them. But that's the more it's a different topic. I think if we go deeper into this, we start entering the domain of consciousness. Let's not do that. Not yet. So the agent keeps track of risks to its survival by constantly measuring its well-being. It is mortal, and measures of well-being indicate how its survival is at risk. Let's posit that the well-being of an agent is a function of three things: its fullness, how energetic it is, its integrity, how healthy it is, and its engagement, how involved it is. And let's assume that the functions calculating well-being are predefined and unchanging. They are given to the agent at birth, so to speak. So the agent will correlate its experiences with fluctuations in its well-being, detected fluctuations in its well-being. And this is how it will have felt experiences. An agent can thus have good and bad experiences. So, sense making. An agent must make sense of its world if it is to survive in it. It cannot just act blindly. An agent makes sense of its experiences by modeling what causes its sensation. It builds a causal theory. The causal theory explains what causes the sensations. The causal theory is used to make predictions. It is a generative model. It predicts incoming sensations. Now, actual sensations that contradict the predicted sensations become prediction errors. This happens when the causal theory is inaccurate or incomplete, or when the world has changed since the causal theory was formulated. So this is basic predictive coding, predictive processing principles. So what an agent senses will be the uncontested predictions it makes, plus the prediction errors it receives. So the perceived sensations are a combination of predictions and prediction errors. What the agent experiences then is limited to what it can predict, but what it can predict changes over time. Let's not forget that the causal theory that generates these predictions is going to be changing and evolving over time. So we remember that an experience is the integration of streams of sensation. And so an experience will be surprising when it incorporates sensations that are prediction errors. So the more prediction errors are integrated into an experience, the more surprising the experience will be. So at first, an agent will hold a trivial theory of causal theory, one that simply predicts that nothing changes. So it predicts unchanging sensations. But clearly, expecting a world that never changes leads quickly to many prediction errors. The agent updates its causal theory when too many experiences are surprising. As we've discussed, the agent uses its causal theory to predict incoming sensations, but also to predict what actions favor good experiences over bad ones. So the causal theory is involved in planning. So not all experiences are worthy of being acted on. So we need to look at the concepts of attention and goals. The agent pays attention to the experiences that matter most to its survival, those it feels most intensely. That will be primarily the ones that feel worse, but also the ones that feel best. The agent will assign itself the goals of impacting experiences that it pays attention to. Experiences it doesn't pay attention to will be neglected. The confidence an agent has in individual experiences will modulate how it responds to them. So an agent seeks to gain confidence in its experiences before it attempts to persist good ones or attempts to terminate bad ones. An agent has confidence in experiences that are not surprising, which is experiences that are not made up of many prediction errors, or if they are surprising, it will have confidence in experiences that are enduring. So even if it is surprising, the longer an experience persists, the more confident the agent will be about it. An agent will prioritize existential goals. It will prioritize its goals so that they maximize, so it maximizes its well-being. But when survival is not at stake, the agent can choose to act just for the sake of new experiences. It will pursue exploration goals. We say that it babbles. Okay, so having reviewed at a very, very, very top level the principles guiding this project, let's now look at its implementation. Implementing a robot that has agency does present significant challenges. Well, first, somehow the robot must be made mortal. So it has good versus bad experiences. Somehow, well, the robot must experience its world. It must make sense of its experiences and act to promote good one, and do that entirely on its own. Which means that the robot's experiences, its sense-making and its goals must be entirely its own, not the programmer's. Now, what role does active inference play in the implementation of this project? Well, we have to recognize that active inference does not tell us how to program a mortal agent, especially one, as we'll see, that has an expanded cognition. That's fine, because that's not its purpose or intent. What active inference does is formalize what is required informationally for a self to persist in a dissipative world. So active inference provides us the requirements on the implementation of our autonomous agent. If I'm to be successful, the observable states of the robot will conform a posteriori to the requirements set forth by the free energy principle. Now let's talk about building a robot's mind. So how am I programming a mortal, experiential, and agentic robot? Well, my implementation draws inspiration mainly from cognitive biology, biosemiotics, and philosophy. I find inspiration in concepts from cognitive biology, such as the organism being mutually sustaining constraining processes, concept of multi-scale competency, stress as cognitive glue, problem solving in morphospace, and cognitive light cones. Those of you who follow the work of Michael Levin will recognize these as some of the key concepts underlying his work and the work of his lab. I also take inspiration quite a lot from biosemiotics, with concepts such as Umwelt, aboutness, signal processes, and sense making. And my two principal sources of inspiration are Dr. Terence Deacon and Dr. Jesper Hoffmeyer. I also lean pretty heavily on ideas that are coming out from philosophy. The application of Kant's metaphysics, its synthetic unity of our perception, plays a central role in my implementation, and we'll go into a little bit more details. And more specifically, I take very, very keen inspiration from the work of Richard Evans and his team in the development of the apperception engine. Again, we'll talk about this a little bit later. For you programmers watching this, the software is built using the Elixir and Prolog programming languages and an extension to Prolog called Constraint Handling Rules, CHR. So Elixir is a process-oriented and functional programming language. Prolog is a logic programming language, and CHR is a constraint-solving extension to Prolog. These are my programming tools. The hardware used in this project is a combination of the robot's devices plus a high-end server. On the robot, we find a set of Lego AV3 sensors and motors, a Raspberry Pi 3 for computing aspects, and a Dexter Industries BrickPi board that interfaces the EV3 sensors and motors with the Raspberry Pi, so they can be controlled through the Raspberry Pi. And the Raspberry Pi, of course, is connected through Wi-Fi to the network, making all of these devices remotely accessible. On the back end, I have a 128-core server that I actually do need to do the compute-intensive processing of various cognitive functions. Well, that's a necessary piece of hardware, because the computing power of the Raspberry Pi is far insufficient for what I'm trying to do. Okay, let's talk about mortal code. Can mortality be programmed? Can a robot be made mortal? Well, obviously the robot's physical structure is immortal. However, the processes that animate it can come in and out of existence. And if these processes implement, let's call it the mind of the robot, well, the robot's mind can be made mortal. So as it operates, as it explores its world, the robot will grow a mortal mind. This mortal mind is what animates its immortal body so that it can survivably explore and exploit the world it's in. And the goal is for the robot to learn to maintain sufficient well-being, or else its mind will die. I built a virtual grid world to provide a virtual robot with an environment that can both nourish, provide food, and damage the robot through obstacles and poison patches. The reason why I need a virtual world and virtual robots is just to accelerate development. If I were to do all the testing, debugging with physical hardware and in a physical world, this would be largely unfeasible. But however, at some point, a physical environment will be built that recreates the conditions of this virtual world, but add all the unpredictability, messiness, and chaos of an analog world, which we can't do without to really fully test this implementation. All right, so we said that the robot will grow its mind as it exploit its world in order to capture what it learns. So let's talk about growing the robot's mind. More specifically, so what are the architecture and dynamics of this robot's mind? Well, first of all, I truly believe that all intelligence is collective intelligence, which means that the robot is not a monolithic agent. its mind contains multitudes. So the robot's mind is implemented as a dynamic collective of cognition actors. So you should think of a cognition actor as a process that's part of a community of mind processes. It is the rich interaction between cognition actors that instantiates the agent's society of mind, its collective intelligence. Each cognition actor is implemented as a process that makes observations, which is a combination of predictions and prediction errors, unifies these observations into experiences, makes sense of these experiences, assigns value to them, are they good or bad experiences, and then acts to have better experiences. Each cognition actor in a collective of cognition actors has its own Umwelt. Umwelt, you can think of it as the self-centered world of a cognitive process, in this case, the cognition actors. So each cognition actor has its own Umwelt that it observes, makes sense of, and acts on. A cognition actor's Umwelt is made up of other cognition actors, except for the more low-level cognition actors who connect directly to sensors and effectors. So this collective of cognition actors that grows during the life of the robot is organized by their Umwelts and organized into abstraction layers. The bottom layer is populated a priori, so before the robot is turned on, by static cognition actors. These static cognition actors interface directly with the robot's sensors. I call them sensor cognition actors, and with motors. I call them effector cognition actors. Their own Umwelt is the robot's immediate external world. It's the distances perceived, it's the distance perceived, the ambient light perceived, it's the contact perceived. So, but the static cognition actors connect the robot's mind with its body's sensors and motors. So that's the bottom layer. All other layers come in and out of existence during the lifetime of the robot's mind. They capture, as I said, what the robot learns from striving to survive. So if the robot's mind is a collective, how does the collective learn to survive? Well, clearly the a priori bottom layer composed of the static cognition actors is not enough by itself for the robot to find nourishment and avoid hazards. Additional layers providing abstractions are needed to create the big picture experiences and affordances that are needed for competency in survival. Pure low-level perception and action are simply not enough. So, as we said, the first row is pre-populated by the static cognition actors, but all of the layers are populated by what I call dynamic cognition actors as the robot experiences its world and learns how to survive in it. We have to imagine that the society of mind grows, shrinks, reshapes itself by adding and removing dynamic CA as cognition actors. And for example, a dynamic cognition actors with insufficient well-being can trigger the birth, with sufficient well-being, can trigger the birth of another to fill a gap in Umwelt coverage. So obviously we have a bunch of static cognition actors that are not in the Umwelt of a higher level one, so coverage is incomplete. And so we fill in this layer, and the layer must fill up before a higher level is started. There's a logic to the growth of this hierarchy of cognition actors. So as dynamic cognition actors are added into new layers, while clearly they form an abstraction hierarchy. But it's not only growth. A dynamic cognition actor will remove itself if it persistently serves no purpose. If a dynamic cognition actor does not participate in another's Umwelt, or if it's never called upon to share its experiences or to execute its affordances, if it's useless, it will eventually remove itself. And this will allow maybe new and different cognition actors to take its place and maybe be more successful. So this adding and removing of cognition actors and layers of cognition actors, in fact, explores the space of possible organizations of the mind. So let's say that this particular collective illustrated here is struggling to maintain the robot's overall well-being. Well-being is going down. This is not working. Death is impending. So we are searching for a competent collective, and this is not it. So the top cognition actor might remove itself, and it can because no other cognition actor depends on it. This allows for other underperforming cognition actors to also remove themselves. And so on, reducing the energy costs of the entire collective, and thus the loss of fullness by the collective. So we've essentially stopped the bleeding of fullness, of well-being, and we're now in a position to grow again. So the collective now having a lower energy draw can afford to regrow itself, and this time differently. There's a lot of randomness in how things grow. So the odds are that as it regrows itself, it will be different from the collective that existed before and was found to be insufficient. So the robot's mind searches for an organization of cognition actors that keeps it nourished and safe. The robot's mind is doing problem solving in morphospace. So what about experiencing? How's that implemented? Well, a cognition actor assembles unified experiences from its observations. Sensor cognition actors, so that these would be the static cognition actors in the bottom layer, have very simple experiences from observing distance, color, luminance, touch, etc. Their observations of sensor readings are their experiences. So while a static cognition actor observes and experiences the readings of its associated sensor, a dynamic cognition actor observes the experiences of its Umwelt cognition actor. So when a dynamic cognition actor is born, it is born with an Umwelt, a subset of the cognition actors from the layer below, and that's a static Umwelt. And this is what the cognition actor will be observing. It will be observing the experiences of its Umwelt. But in order to observe it, it needs to predict. So the cognition actor in an Umwelt will communicate its experiential domain to the parent's cognition actors so that these can make meaningful predictions. An experiential domain describes the kinds of experiences a cognition actor has. So if I'm a cognition actor, I'm part of an Umwelt, my first task is to communicate to my parent. These are the kinds of experiences I have, so you can make predictions about the specific experiences I'm having. And that's what the parent cognition actor will do. It will observe its Umwelt, the cognition actors in its Umwelt, by predicting their experiences and then receiving or not prediction errors. And the observations of the parent cognition actor are the summation of predictions and prediction errors, but predictions of experiences of its Umwelt cognition actor. So there's a sense where the experiences of your children become your observation. But the parent cognition actor then unifies its observations into its own experiences. So multiple observations of its child cognition actor experiences will be combined into single experiences. So multiple observations of child experiences become a parent's experience. So for example, having observed in its Umwelt that distance keeps shrinking, a dynamic cognition actor would experience the more abstract concept of approaching. So the experience of a cognition actor becomes the raw material that are unified into the experiences of more abstract cognition actors, and so forth, all the way up from static cognition actors. So clearly, higher up dynamic cognition actors have more abstract experiences than the lower down cognition actors. For example, the experience of I stopped approaching is more abstract than the experience of approaching, which is more abstract than the experience of distance. It's worth noting that experiences are constructed and named by the dynamic cognition actors, and they're not constructed nor named by the programmer. In fact, they need not make sense to me as an external observer. So we talked about felt experiences. Where does the robot get its feelings from? The feelings it attaches to experiences so that the experiences are either good or bad or indifferent. Well, everything a cognition actor does increases or decreases its feeling of well-being. So well-being is determined, as we saw, by fullness, integrity, and engagement measures. Any internal or external work by a cognition actor reduces fullness in predefined ways. So for example, spending time over a fruit patch will be captured by a cognition actor as increasing fullness, or hitting an obstacle will be perceived by a cognition actor and it will reduce integrity. Cognition actor participating in an Umwelt will increase its engagement. So throughout its life, each cognition actor comprising the collective that makes up the mind of the robot will have fluctuations in its own well-being. And this fluctuating well-being determines whether a cognition actor's concurrent experiences feel good or bad. It might be good to note that well-being measures are not entirely separate. For example, activating motors is work that causes loss of fullness. It's an energy cost, but also a loss of integrity. We're going to be simulating wear and tear, while also increasing engagement. We are moving into our environment, so we are engaging. Lost integrity is regained over time. Think of healing, for example, but that drains fullness, and on and on. Now, if a cognition actor senses touch, when it senses a collision, it will have a loss of its integrity well-being measure. It will experience a loss. But it's important to note that the loss or gain in well-being of an individual cognition actor will diffuse throughout the collective. We can think of losing well-being as stress. So losing well-being causes stress. And stress is contagious. Stress experienced by a cognition actor in another's Umwelt will diffuse to the parent cognition actor, which will then diffuse downward to the children and upward, and eventually through the connections, the Umwelt connections of cognition actors, stress experienced by one will diffuse and be experienced by everyone. And because a cognition actor cannot distinguish between a self-induced change to its well-being and a change caused by the diffusion of well-being from other cognition actors, well, one cognition actor's problem eventually, through diffusion, becomes every cognition actor's problem. Now, when a cognition actor feels a reduction in well-being, it feels stress, and stress alters its behavior. A stressed cognition actor is more likely to try something different from what has worked in the past. Obviously, something different needs to be tried. But a comfortable cognition actor, one that does not feel stressed, is more likely to settle into habits. Why change what has worked before? Now, let's take a little bit of a dive into acting. So a dynamic cognition actor, again, it's part of a collective of dynamic cognition actors, acts for different reasons. One is to confirm its experiences, and then to terminate its worst one, or persist the better ones. So to confirm, persist, or terminate an experience, a dynamic cognition actor must first identify the observed Umwelt experiences that it unified into its own experience that it now seeks to impact. So the experience of a cognition actor is a unification of observed experiences by cognition actors in its Umwelt. So if I want to change, as a parent cognition actor, if I want to change an experience I have to understand its composition in terms of the observed experiences of my Umwelt cognition actors. Now, the cognition actor will plan how to alter these Umwelt experiences so as to impact its own experiences as intended. The dynamic cognition actor, each one has a causal theory, and we'll see more in details how it acquires it, that explains the observations it makes in its Umwelt. And then it will use this causal theory to anticipate what would happen if experiences in its Umwelt were to change this way or that way. Would this achieve its goal of persisting or terminating one of its best or worst experience? So knowing how its own experiences are made up of Umwelt experiences, having a causal theory that explains how the observed Umwelt experiences change over time, then it can formulate a plan to change these Umwelt experiences in order to alter its own experiences. So question number one, as we said, which observed Umwelt experiences need to change to impact my experience, says a cognition actor. And then the cognition actor would say, okay, these are the changes that need to happen to the experiences in my Umwelt that I've observed and unified into my own experiences that I want to change. And it will then formulate a plan as a set of directives. And what's a directive? It's simply a desire to modify, impact an experience in its Umwelt. So it's basically a goal. A plan is a set of goals that are sent to the Umwelt for the Umwelt to accomplish. So the parent dynamic cognition actor sends goals to its Umwelt, goals to persist or terminate experiences that are being had in the Umwelt. But it doesn't tell its Umwelt exactly how to change these experiences. The Umwelt cognition actors will interpret these directives they receive and then make their own plans, because their experiences are also made of observations of their own Umwelts. So this way of, at a high level, saying, I want you to accomplish this, and then at the lower level say, okay, fine, and I'm going to decide on my own how to accomplish it, and then ask the lower level to do the same. This implements a multi-scale competency. Again, for each goal it takes on, a cognition actor interprets it as directives, planned directives that it then sends to its own Umwelt for them to interpret, and so on. So action goes all the way down, from the top to the bottom, all the way down to effector cognition actors, where a directive might be simply to spin a wheel. Now, a dynamic cognition actor keeps track of directives as sent and the goal they are meant to achieve. Directives that appear to have achieved their goal are remembered as affordances for later reuse. Effector cognition actors, at the very bottom, have atomic preset affordances such as spin or reverse spin. Whereas the cognition actors higher up, the dynamic cognition actors, discover abstract affordances such as go forward or even go up the luminosity gradient. So as you go up the abstraction layer, the affordances become more abstract, more high level. Affordances are discovered and named by the dynamic cognition actors, not by the programmer. That's important. And in fact, then they don't even need to make sense to an external observer such as myself, the programmer. Now, let's look at how cognition actors build the causal theories they use to predict incoming observations and plan their actions. So, a cognition actor observes its Umwelt one time frame after another. And a time frame is a thick now. And the more abstract the cognition actor, the longer its time frame. So we could say that a more abstract cognition actor has a bigger cognitive light cone, if you wish. And observations made within a time frame are considered synchronous. So even though they may be made sequentially, so within a time frame of, say, let's say half a second, 2 seconds, 5 seconds, they are considered to be concurrent, to be happening at once in the real world. So a dynamic cognition actor constructs its causal theory to make sense of what it observes within each individual time frame. And this causal theory, this construction of a causal theory, is a form of induction, that is the production of general rules from specific examples. Examples being the observations. A causal theory here is a set of if-then rules in the program. It's a set of if-then rules that are constructed and live about three kinds of things. What observations ought to occur at the same time, in the same time frame? What observations cannot coexist in the same time frame? They're mutually exclusive. And what observations would follow from previous observations? For example, we might have this causal theory that says if the distance is getting shorter, then nothing is being touched. So if you are observing that the distance is getting shorter, you should also be observing that nothing is being touched. And if you don't, you can infer that nothing is being touched. Another constraint, another rule, which is a constraint here, that says the distance cannot be getting both smaller and larger at once. So you cannot have these two observations coexisting. And a third rule, which is more of a causality rule proper, is if both wheels spin forward, then the distance will get smaller. So this rule predicts what happens in the next time frame. So these are examples of, this is an example of a causal theory. An interesting side note is a causal theory can posit hidden, that is latent facts, that are needed to make sense of actual observations. So a causal theory can be partly an act of imagination. And this positing of hidden facts is a form of abduction, that is the inference of likely causes from effects given general rules, for those who enjoy logic. So the discovered rules that make up the causal theory are expressed in the implementation as a logic program. The logic program embodies a causal theory, and it is constructed without human intervention. Learning is achieved entirely from experiencing. There's no prior instructions or feeding of examples before the robot is turned on. And this type of learning happens repeatedly over the lifetime of a cognition actor, and it happens for all cognition actors making up the collective, the mind. So the logic program serves as a generative model. You can feed it the current observations, and it will produce the predictions of the next observations. Each dynamic cognition actor constructs and runs its own logic program, though at first they run the same trivial program. So the whole thing bootstrapped with every cognition actor have a simple program that says it is as it is and nothing ever changes. And so the dynamic cognition actor will run its logic program to predict the next observations, but also to do what-if reasoning before acting. Okay, so when predictions made from a causal theory result in too many prediction errors, that's because the causal theory is inadequate, then the dynamic cognition actor will replace it with a better one if one can be found. So how are these logic programs that embody causal theories generated? Well, by an apperception engine. The apperception engine is a computer process that inputs a cognition actor's observations and outputs a causal theory that explains them. So you feed in a history of observations, turn the crank, out comes a little program, logic program, that if you feed it the latest observations will produce the likely next set of observation in the next time frame, the predicted observation. So when they need a causal theory, and they will need pretty quickly, especially in the beginning, dynamic cognition actors call upon the apperception engine as a service when they need to replace their current causal theories. Again, they do so because they experience too many surprises when using their current causal theories, or they fail consistently to predict the consequences of acting upon their umwelt. Now, finding a logic program from remembered observations, one that makes accurate predictions about future observations, is a difficult search problem. It's a hard nut to crack. Because the space of all candidate logic programs, where the haystack, if you wish, is ridiculously large. So to find a good enough program in what I call useful time, while it's still useful to have that logic program, the search needs to not look over the entire haystack. It needs to be biased so it productively ignores much of the search space. That's where the work of Immanuel Kant comes in, is synthetic unity of apperception. It's part of its metaphysics, focuses the search on causal theories that are coherent and possess explanatory power. So Kant's theory says these are the properties of causal theories that are worthy. They are coherent, they have explanatory power, and you can ignore any causal theory that does not have these properties. So the apperception engine is a program that applies Kant's synthetic unity of apperception to find logic programs that encode coherent and useful causal theory. So the original apperception engine was built by Richard Evans et al. At Google DeepMind. And I simply, quote unquote, re-implemented and optimized it. And it was the subject of my presentation last year. And there's a paper on that you can read to find more of the details. Okay, so all in all, this project aims to express and connect all of these concepts into working code. And this code will animate a mortal and adaptive robot that is capable of agency. That is the task. So where's that code? Well, it's the open source project that I'm working on that contains this code and design notes is called the Karma system. In all the code, all the notes are completely open sourced, and here you have the URL of the GitHub repo, which you can go see and peruse. There are a number of sub-repos under the Karma system. There's one with a Prolog actor framework. The actor framework is kind of the runtime platform for the cognition actors. There's a implementation of a practical apperception engine. There's code that implements agency, so code that implements the actual cognition actors, a bunch of utilities. There's code to implement the logic on the body of the robot itself, so the access to the sensors and motors. There's an implementation of a virtual simulation environment, Karma World, and there are other repos to come that will provide an experimental platform so I can run experiments, collect information, collect data, and submit this data to analysis. So these are the main subsystems of the Karma system, and they communicate over a network. So that's how the sensors and motors can be accessed on the robot and by the cognition actors running on the backend servers, so that it forms a unified system. Bit of a progress report here. Well, a lot of things have been accomplished, done. I have a detailed conceptual and implementation design that's documented in the Karma system repo. The interface of the robot's sensor and effectors is implemented and working. I have a virtual grid world that's also functional. The apperception engine is running and seems to be doing well. I have a runtime platform for cognition actors. And I have implemented the static cognition actors for that interface with sensors and effectors. So that's code that works, tested. What's in progress right now is the implementation of the dynamic cognition actors, and that's in the Karma agency repo. What's hasn't started yet and still to do is a physical recreation of the grid world, implementing the observer and analyst subsystems. So observer to collect the data from running the robot, analyst to subject them to analysis, more specifically to validate that the requirements from the free energy principle are realized in the data that we captured from running the robots. Then and of course doing the experimental runs and collecting the data and doing the free energy principle data analysis. That's to do. Now, a parting thought. Now, should I succeed at programming a robot that has felt experiences makes sense of its world, and strives to survive, could there be something it is like to be this robot? I, for one, don't know. But if you answer, definitely not, then I do have follow-up questions. All right. So here's how I can be reached. Email, and I'm on the SimCog Robotics channel in the Active Inference Institute's Discord. And you have here the URL to the top of the GitHub repo. So I'd like to conclude by thanking the Active Inference Institute for giving this project a supportive home. Thank you.
All right. Next up is going to be Harshal Shah and Satyaki Maitra, who will be presenting on their drone work. This is a 40-minute pre-recorded video. Okay, here we go.
Hi everyone, and thank you for joining us. My name is Harshal Shah. My name is Satyaki Maitra, and today we'll be presenting our project on combining hierarchical active inference with affordance theory for scalable policy selection and autonomous drone navigation. We recently presented at the International Workshop in Active Inference, and a lot of people were interested in how we got started as we're sophomores in high school. We're from California and attend Mission San Jose High School, and we've been working in active inference for around a year now as they combine your interests. After learning the fundamentals, we went into autonomous drone navigation around April, and we found that it had a lot of potential with active inference for many of the issues and challenges that we face. For me, my personal connection to active inference was mathematics. I was really interested in how statistics and probability was connected with neuroscience, and I wanted to connect this theory of mathematical modeling with actual systems, which again drew us to this project. Outside of research, I also enjoy math competitions, piano reading, and video games, certain types of video games that like strategy games that require some sort of exploration and problem solving. And here's my info at the bottom. Hi, I'm Herschel. So I originally came to active inference from the side of machine learning, deep learning, that whole space. What really captivated me about active inference is that I think it's the path to developing truly intelligent AI, which is what I really want to do. And I think it's also really applicable to solving critical problems that machine learning in that space just really can't do. I'm interested in the applications in many fields beyond just our autonomous navigation. I'm passionate about medicine, biology, neuroscience. Other than research, I love competitive debate. Reading, I love reading books all the time. And been playing tennis for my high school team. And I just love learning a lot of new things. I have a website where I also write Medium articles, and I put all of that there. I track my reading journey. So we'll begin with motivation and background, and then we'll go into the four main corners of our project, then implementation, how we did it, and then how we evaluated how well the model did, and then just the last conclusions and whatnot. So first, let's start with motivation and background. So the first challenge that motivated this project is defining action spaces. When you consider action spaces, you have to look at continuous spaces and discrete spaces. Each space has its own advantages. With continuous spaces, you have to worry about computational efficiency and suboptimal solutions. But defining discrete spaces that are super flexible is really tough, especially when you consider that you have infinitely possible discrete actions, but you need to define a space somehow. Our next challenge is abstractly representing the environment. So for planning, an agent needs to understand what its environment actually is. For humans, we can just say there's a tree or that's a computer, but an agent can't just do that. So how do we turn these raw sensor data that we can give an agent into meaningful ideas? There are some issues with deep learning, like it doesn't have an internal world model, and it learns correlations. And while deep learning scales by avoiding the structure, active inference actually builds up a structure from the ground up. And we want to combine deep learning scalability with active inference's structured understanding for a good environment representation. The last challenge that motivated this project is considering computational efficiency. In robotics, offloading computation to GPUs or cloud servers is often not possible when you consider issues like latency and bandwidth limits. This requires us to consider edge processing or on-device processing. Both deep learning and active inference are computationally intensive for various reasons, and our goal with this project is to maintain the active inference framework's interpretability and adaptability while maintaining real-time inference and control on edge devices. To address these challenges, we combined four main concepts. First, hierarchical active inference. As from the diagram on the left, the brain works hierarchically with higher level prediction and planning and lower level perception modules. Each layer updates beliefs to reduce prediction error. Hierarchical active inference models this top-down, bottom-up like loop by minimizing uncertainty at each level to guide adaptive behavior. Information from lower levels is compressed into higher levels, and you still retain these key concepts, which is the main thing, which will address a lot of our challenges. And it also allows, in practical use, computation can be distributed among multiple levels. The next concept is affordance theory. Affordance theory was originally described in the context of ecological psychology as abstract ideas offered by the environment that can restrict or assist possible actions. However, this is very adjacent and can be directly used with the active inference framework to enhance policy selection while contextualizing the environment. We can take the concept of affordances, which can replace traditional states with abstract ideas and reducing the need for compute for inference. And this serves as a complementary role as behavior emerges from interactions between the agent and the environment, which bridges the abstract cognition with real-world context. Another approach we took is the idea of scalable policy selection. To scale policies, you need to have some sort of structure that can allow you to maintain low computation while still scaling up the amount of policies you consider. In our case, we use a latent suitability state in an affordance map. What that essentially means is we have an affordance called suitability, which encodes numerical or categorical evaluations of some region or path that the drone is about to take. So as you can see in the diagram below, low suitability indicates high obstacle counts and it's not very desirable. But high suitability means you have lower obstacle counts and you're closer to the target location and the agent wants to be there. This contextualization allows you to scale up policy selection because you can filter out those low suitability actions. You don't need to consider them because they're just not suitable. And this reduced policy set can be efficiently evaluated through EFE without the need for some advanced hardware or off-sourcing compute. The last area we need to consider is autonomous drone navigation. So notoriously, autonomous drone navigation has a lot of different issues that we need to consider. So just quickly going over some of them. The first is that sensor data is often noisy, which makes perception and localization very tough challenges. The next is that environmental factors like low light, glare, or clutter can additionally reduce our sensing's reliability. After that, we have to consider that real-time adaptation to dynamic and uncertain environments is very difficult. If you have a drone autonomously navigating in an unknown environment, it needs to be able to move and think very fast to adapt to brand new situations and issues that it's never come across before. After that, we have to think about that the fact there's limited interpretability and robustness in existing navigation algorithms. We already talked about some of the issues with deep learning, but in the field of autonomous drone navigation, these issues are more and more important. Then high computational load restricts deployment on low power edge hardware because in autonomous drone navigation, we're navigating environments where issues like latency are amplified almost everything has to be on edge hardware, but this isn't always possible with the most frontier models. Finally, there's often difficulty in fusing multimodal data from LiDAR, camera, and IMU consistently. We need to have all these different data sources to enable all the different elements of our navigation, but to fuse them and provide them to the model is a challenge. So now let's go into the actual architectural structure. So we have a 3-tiered architecture. We have high-level inference and planning, and these lower levels, all of this builds up and sets up the high-level planning to be as efficient and streamlined as possible. We have our mid-level perception and encoding, which builds our world model. It builds it from observations and its suitability, and then creates a world model and beliefs about the world model, beliefs about the environment. Finally, we have low-level control, which right now is very simple. It just executes movement and records change in position to maintain egocentric navigation. Let's go over these areas a bit more in depth. So the first is perception, where we take environmental data and process it into a point cloud. So you can see that we have the airsim simulation and we collect data from the LiDAR and camera, which are 2 primary methods of perception. We turn these into structured observations, specifically target distance, azimuth, elevation, and obstacle distance, obstacle density. And we use these to update our world model's state space with distance, azimuth, elevation, and suitability here. Then we take our affordances, which calculate expected suitability scores for the region around us based on the same perception data we got from Microsoft AirSim. Then we move to high-level planning, where we sample optimal policies from a filtered action space that's created based on our affordances. And this high-level planning works to minimize expected free energy with its pragmatic and epistemic component. Finally, we do our final execution, setting it to a very simple low-level module for physical execution in Microsoft AirSim. So now let's talk about a factor graph of our architecture. Our architecture is currently very simple, so there's not much special about our factor graph. It's a typical message passing structure between t and t+1, but there's a very key difference. This S4, or suitability, actually feeds directly into the observation, and it dynamically weights that preference to then move into EFE. We'll definitely talk about this more in detail once we get to the planning calculations, but this is a very key difference, and it highlights a key problem with our architecture. Because it directly feeds in, it's actually completely deterministic, and there is no probability involved. It just, okay, I look at my information, I see this amount of suitability, that's my observation. We need to make this probabilistic so that the drone doesn't have 100% trust in its sensors, because sensors are noisy, as we mentioned earlier. Yeah, so that's definitely a feature improvement that we need to do. Now let's go more in depth onto the perception and world model area. So the first thing to consider is the multimodal data acquisition. As we mentioned earlier, our 2 primary methods are from the LiDAR and depth camera. So LiDAR gives us distance data. The effective range we chose is from 0.1 to 50 meters, which is kind of arbitrary, but we found this based on testing in Microsoft AirSim. This is the effective range that we need for our purposes. That is a depth camera, which is only from 0.1 to 20 meters, and this gives us very accurate depth data. This is an image you can see of what some kind of sensor data would look like. For us, what we decided to do was use a dbScan algorithm to cluster all of the fuse points we get. And we have an epsilon of 1.0 meters, which basically means that the max cluster size is 1.0 meters. So in each area of 1.0 meters, you're going to cluster into 1 point. And we have min samples 2, meaning for 1 cluster, you need at least 2 points. This process then abstractly represents the raw points into a discrete set of obstacles, and this inherently performs denoising. For example, if there was a random point somewhere in an individual point, then the dbScan algorithm would ignore that because it's below min samples 2. Then going more into this for pre-processing and fusion, we take our raw sensor data and filter it for some additional noise reduction and remove out of range points within the effective ranges we talked about. And there's an optional subsampling in case computational efficiency means that we can't handle large amounts of data. For fusion, we can just take both LiDAR data and camera data and transform it into a single unified coordinate frame, which creates one large point cloud, which is more similar to like the image you see here. Then we do our data packaging and output for the technical part of it. So far, everything's been done on Python, and we're calculating more information about the target, like angle, elevation, and distance. This is mostly supplied by information from the airsim functions, which is kind of like the replacement for the IMU since it's in simulation. Although obstacle data is also packaged here, we take the obstacle positions, which we got from dbScan, and the obstacle density, which is a very simple calculation that represents how dense the environment is. And this information is then finally packaged into a JSON file. And we use a ZMQ system to communicate between the Python and Julia areas of our project. So all of this is in Python, and ZMQ then sends it to Julia, which is going to go over our planning module, and it's going to process it. All right, so let's go into this actual suitability calculation. So our suitability looks like this. We have a weight, we have safety factor, another weight, and then density factor. The weights are just normalized to add to 1, and then we have these weights here. These are hyperparameters. There's a lot of room for improvement, which we'll talk about later. But here's how the safety factor looks. It's an exponential where essentially when d, the obstacle distance, is very close to 0, you immediately know it's unsafe because there's an obstacle right in front of me or right next to me. And our safety factor crashes as it's an exponential decay function. Then as d approaches larger and larger numbers, it gets safer and safer and safer because the exponential increases, and then we know, okay, I'm not close to an obstacle, let's just ignore and let's keep going. And then we also have this penalty, which is like, if there's an obstacle within 1.2 meters, we replace safety, or we multiply safety by an exponential -1/d, which basically says, okay, there's this obstacle that's some amount of close to me, let's quantify that, and then go from there. So this is kind of a penalty for very unsafe environments. When there's a lot of obstacles, it comes into play a lot. Then let's go to the density factor. It's based on obstacle density. Both of these are considered observations, 04 and 05, as we saw earlier. So we take the density factor, which is very similarly structured. It's based on obstacle density, and then there's a cutoff for both. But for this one, the cutoff is more noticeable. This is like just a density threshold that if it gets below this, the density factor becomes 1 immediately because we know it's very safe. And then steepness is just quantifies how sensitive it is to changes in density. So as density gets low, as you can probably guess, the factor gets close to 1, so that, okay, I know it's quite safe. And then as density gets very high, the factor gets lower to lower suitability. There's also another density penalty for high densities. It's a bunch of stuff, but essentially it takes the maximum of a hyperparameter and then a calculation with obstacle density and checks, okay, how much should I scale the factor to penalize this factor so that suitability begins to lower. That eventually ends up with a normalized score from 0 to 1, which represents this overall navigability and safety. Now you can clearly see that there's a lot of rule-based elements that require hyperparameter sweeps, and that is a very, very glaring problem with architecture that has a fairly arbitrary fix, which we'll definitely talk about later. Let's go over the overall planning process. So we start with waypoint generation. Once we have our internal suitability, we're able to do this where we generate 25 to 75 candidate waypoints based on obstacle density. So again, this is another example of the agent taking environmental context and using it to inform its planning. We do a dual strategy where the sampling 70% about it is exploring the nearby space, and there's some target bias sampling, an initial 30%, that's pushing the agent more towards the goal. We have an adaptive radius, which is where the action length is between 1 to 10 meters, which is again based on internal suitability. So we use a very simple calculation where the minimum is 1, and then you raise suitability to the power of 3 and multiply it by 10 minus 1. So this basically means as suitability approaches 0, then the action length would be approaching 1, and vice versa, where suitability is going really well towards 1, then our action length is going to be 10. There's an additional check that's performed after this to ensure that we have at least enough to reach a target when you're in some area that's nearby the target. So you can see from this whole process, we have flexible actions. If the agent's in a very open space, then there's absolutely no need for it to be taking a small action like 1. We'll be taking something more larger like 7 or 8. And vice versa. If you're in a very dense space, we can take actions of when. And yeah. So let's go more into how this process works. When we get this set of waypoints, we calculate the expected suitability. This is a very similar calculation as Safiki talked about with the intro suitability. It just has a few additional modifications and penalties. So one of them is that there's more conservative parameters used. We pretty much use stricter cutoffs like for distance and steepness, which just makes this a safer check. We then add some additional cluster and octant penalties. So we check for any dense obstacle clusters in any of the 8 octants around the waypoints. And if any octants is dense, which has like more than 5 obstacles, then its local density score is penalized. And if it's extremely dense, like even more, and it has more than 10 obstacles, its local obstacle distance is also penalized. We also have a few other penalties like corridor penalty, where if the path from the current position is checked for narrow gaps, and if the path is too narrow, then suitability is severely penalized. This means that we're not just considering where the agent's going to end up, but the process of how the agent's going to get there. Finally, we have this target proximity bonus, where again, if the agent is closer to target, waypoints moving more directly towards it receive an additional suitability boost.
Yeah, and something to add is these local density score and local obstacle distance are the same things as the factors that we talked about before. So we basically penalize or increase these for expected suitability based on these factors. Finally, we filter. So after all the calculations, the system discards all these waypoints with a score less than 0.8. And then you calculate transition for other states with a suitability of 0.95. And then we calculate EFE. So we evaluate EFE for this action set by encoding paths with EFE based on their location and all these factors. So our equation looks like this. We take in the current state, so distance, angle, and suitability, and then the action, which is a 3D vector, and then the agent's current beliefs as probability distributions. So we have the goal-seeking behavior, the uncertainty reduction term, and the VFE term, which essentially, we'll talk about later, but essentially uses VFE to penalize or increase EFE. All right, so let's break down each part of EFE and each term. So first, the pragmatic term. It's just a pragmatic weight, and then preference score, distance bonus, and this magnitude term. So preference score is just your preferences for distance, angle, suitability as a weighted average, which we'll talk about in the next slide. The distance bonus, which is just your expected distance minus the current target distance, and then a factor of 2. And finally, action magnitude. So larger actions would incur greater scaling of this, because your pragmatic value should increase, or rather be minimized, as you get closer to the target. So basically, in essence, a higher pragmatic value would lead to more efficient goal-directed actions, while the adaptive weighing does ensure some caveats in very dense environments.
Now let's go over the epistemic value. So just keep in mind, in general, in any active inference framework, the epistemic value is in charge of driving the agent to explore and reduce uncertainty in its beliefs. So for example, if the agent's like, for this state, I have a very low certainty in it, what action can incentivize and help me find more information about the state? That's what the epistemic value is encoding. So let's go over specifically in our architecture what we have. So the equation is very simple. We have this epistemic weight, which is by default 0.2. It's a hyperparameter. And we do dynamically increase this in our system in high density areas, which promotes more exploration and looking around for safe paths. We then multiply by an additional factor of 0.5. This is arbitrarily chosen by us. After that, we multiply by the total entropy, or which is encoding the uncertainty of the agent's beliefs. This is computed as the equation h of q is equal to h of the q of the location plus h of q over angle plus h of q over suitability. So in essence, it's just calculating the total entropy of our states as per the active inference framework. This is a more detailed equation as per the belief distribution for how the calculation works, where you have the summation and you take each part of the belief distribution and add this term epsilon to it and take the log of that. It's very standard calculation. And finally, in this, going back to the equation, we multiply by the action magnitude. Again, if you remember, our actions vary from length 1 to length 10, and this term just reflects that increased epistemic value for the larger actions. You might think this is a bit strange, but logically the motivation is if an agent is moving further, then it's able to uncover more information about the environment, and thus it has a greater epistemic value. Just note, because of the way things are set up with the architecture, we are multiplying this by a negative, and our total EFE ends up being negative. This is just how things are supposed to be. And overall, once we get this epistemic value, we see that a higher epistemic value is going to incentivize the agent to reduce uncertainty about its environment, thus balancing exploration and goal pursuit.
Our final part of EFE is this BFE penalty. This is a very non-traditional and not super necessary term, but it is still there, so we decided to talk about it. It's a small regularization term that links our planning to the inference because we don't have very explicit perceptual inference. We do this term. So lambda is just a small fixed hyperparameter, which ensures the penalty is about 10% of EFE, so it doesn't really affect EFE that much. And then VFE is just your variation free energy calculated during inference. It measures how well current beliefs explain the observation O, essentially just our traditional EFE, VFE. And we have complexity, or your entropy term, and then you have belief accuracy, so just your expected probability of observation over states, i.e. your likelihood, and then your prior belief, just a simple belief updating system, which is how VFE is structured. Also, this all leads into control, which is just our final steps. These are simple AirSim functions. They take in all these values. Most of these values are completely irrelevant, but you have x, y, z, and velocity. You move from waypoint to waypoint, and then rotate to yaw. Just make sure sensors stay straight. So you rotate to a given yaw based on which direction you are facing when your action is moving.
Well, that was a lot, but we finished covering our architecture, and now it's time to look at the actual experiment we conducted in Microsoft AirSim, going over testing results. So this is the way the experiment's set up. Again, our core simulator is Microsoft AirSim, which is built on Unreal Engine. It's a very useful thing. It's a high-fidelity open-source platform, which is built for rapid and safe testing, which was able to drive all of our development in this project so far. It provides very realistic drone dynamics and simulated sensor data from LiDAR and camera. So you can see we have this environment. It's very realistic, where the LiDAR and camera sensors are able to pick up very detailed images, these different things. This is a picture of our core environment. It's called AirSim Neighborhood, and it's a complex suburban environment that houses trees and other obstacles. So this was the very balanced environment to choose for a drone. It's not too sparse, where the entire thing is open, but it's not super dense, where our simple architecture can't exactly just, so it can at least have a chance. There's areas where there's open road, which is where the drone can adapt and take longer actions. There's also areas where sometimes targets are located near houses or trees, and the drone needs to take smaller actions. So this allows us to extensively test our architecture. We have verified targets that are made sure that it's at least possible, and we pseudo-randomly generated them in the range of 20 to 80 meters for the purpose of this experiment. We fully ran 97 episodes, and 96 of them passed with very low collision amounts, which we thought was pretty good. Let's go more in depth into the data we collected and the results we got.
For EFE minimization, as you can see, over all the episodes, the expected free energy reduces as the agent gets closer to target, as intended. It shows the agent minimizing uncertainty as both the pragmatic and epistemic values lower, as it understands, okay, I know where I'm going, I know what I have to do. The next is exploration and exploitation balance. So we concluded that the agent demonstrates an effective balance of exploration and exploitation. Let's look at the graphs to analyze this. So this is our main graph. It compares the pragmatic value and epistemic value. Red is pragmatic, blue is epistemic, in comparison to the distance. So the graph goes as distance to target decreases, and we have on the y-axis the log normalized component. We see that throughout the entire run, that the epistemic value is fairly consistent, and it's a pragmatic value that's mainly changing. So at the left side, the agent is prioritizing more exploration because initially it has more uncertainty about the environment, and this means that the dominating value is the epistemic value. At some point around here, the pragmatic value starts to play a much greater role. So as the agent gets closer to the target, the pragmatic value starts taking over, and the agent prioritizes exploitation, which means it's acting with more goal-oriented behavior. So it has less uncertainty, and it's working towards reaching the target as fast as it can. These are some more detailed graphs that show individual elements of the pragmatic and epistemic component and provide more information on the exploration and exploitation balance. Yeah, if you're interested, a lot of this is up on our website that we mentioned earlier. So for computational efficiency, which was a big thing for one of our challenges, we measured it for the time it took for each planning step. As you can see, EFE specifically, which was the main thing because VFE wasn't super impactful here, was very short, only taking 6.01 milliseconds on average with ARCs and FIR. And this demonstrated suitability-based waypoint filtering that actually reduced the computational cost. The total processing took 117 milliseconds on average, mostly due to AirSim calls and some other miscellaneous processing. But all of this computation was run on a standard CPU. There was no off-sourcing or anything. So this is pretty promising for the practical implementation of active inference, but there's definitely room for improvement. We talked with a lot of the ARCs and FIR people. They said this can definitely be improved. So we hope to get these computation down as we move to a real drone. Here's just the general results.
Yeah, and the last thing to look at was after this main experiment that was mainly used to evaluate our model, we did run it on a more challenging environment. The reason we're not looking at the main data from it is that the success rate was only 50%. 17 out of 34 episodes that we ran, with the condition that there was a 6-minute timeout per episode. So there was a couple of issues for why the drone didn't have that great performance. But as we're going to get to later, and as you've briefly mentioned throughout the entire presentation, this isn't due to fundamental issues with our architecture, but more so as to the implementation. And of course, our future work is going to address the main fundamental issues that do actually play an impact. So going more over them, we saw that the drone often got stuck and had higher collision amounts in this environment due to two main things. The first is myopic planning. So the agent essentially lacks a global strategy. It's planning more reactively than we wanted to, which is over considering immediate safety and proximity to the goal, which leads to poor longer term positioning. So for example, if a drone would get stuck in an area, it would be taking actions that maybe would help it a little bit, but don't strategically move it out of that bad area and out into the open. This also plays more into learning instability, where the agent is unable to fully learn from the mistakes it made, and it would abandon a mostly good strategy after a single failure.
Yeah. So in this challenging environment called Zhangjiajie in AirSim, it starts within all these trees, which makes it immensely challenging. But we have confidence that our architecture should be able to do this if these issues are circumvented. An example of this myopic planning would be like, it would get itself stuck in like one of these little buildings, and it just would not know how to get out because it doesn't have that long-term vision to think, okay, I can go up and around. Instead, it just thinks, I have to get to my goal, I have to avoid an obstacle. That's it. It doesn't have the ability to look forward. Thus, we look at some conclusions. Despite those issues, we did see that combining affordance theory and hierarchical active inference does enable efficient, safe, context-aware navigation, as we illustrated with our addressing those challenges in these complex 3D environments. So we were able to address all three of these challenges in different manners. First, for the first challenge, which was policy selection, we were able to use affordances to create discrete high-level planning with a flexible action space. We were also able to lower computation because we only have to consider certain paths because of the suitability filter. The second challenge, which was contextualizing the environment, we were able to use just affordances, which fundamentally contextualize the environment, and our suitability state was able to contextualize specifically the safety and navigability of the environment. Again, this also decreases computation for the obvious reasons that it just doesn't have to consider unsafe areas. It only considers certain parts. And challenge 3 was we were able to address computational efficiency and see that the model is efficient and capable of running on a standard CPU. And with our preliminary tests on our real hardware, we've seen that it's likely being able to run on edge device, in our case, a Raspberry Pi 4, but there are obviously more powerful devices that could run this even more efficiently. Now, let's talk about what we're going to do in the future, because this is a very much incomplete project and there's a lot more work to do. So we currently have a built drone. We want to do it fully GNSS denied and with the open source ArduPilot firmware. So we have a Raspberry Pi, which a little bit hard to see, but it's in this big black box over here. We have a LiDAR A2M12, which is currently not attached. We'll put a depth camera on it, specifically Intel RealSense D455. And this entire thing was built upon the Hawksworks F450 drone kit, which came with a Pixhawk 2.4.8, which is up here. It allows us to make very streamlined architecture, but there's a lot of issues with the GNSS denied and like frames and whatnot, because obviously when you move to the real world, GNSS without GPS, there can be a lot of issues. Our goal is to test the full architecture in the real world and collect sufficient data, like we did with our AirSim neighborhood environment. And we hope to see some success with this and with active inference as a proof of concept.
As you mentioned throughout the presentation, there were some miscellaneous issues that we're working on addressing right now. So we talked a lot about how we have rule-based methods that are essentially like band-aids on issues we notice in the sim. But the more fundamentally sound way to fix all of this is, of course, the Bayesian framework, Bayesian methods. One example is that for the point cloud, when we get the sensor data, instead of everything being deterministic, which then proliferates through our architecture with even suitability, we want to have a probabilistic representation of a point cloud. So you're representing probabilities of how likely different areas are to have a point. This is going to inherently fix some of the issues and simplify a lot of our calculations. This ties more into our second point, which is fine-tuning the suitability weighing and calculations. We have a lot of fixed hyperparameters and unnecessary calculations. Probabilistic methods are going to reduce a lot of this, but even the way we get some of those hyperparameters can definitely be improved on with more sophisticated methods. After that is action fine-tuning. So the flexible action approach that we took, using suitability to internally parameterize where action is already pretty good. But we think we can take a more sophisticated approach where once we sample our first action, we can then make more precise adjustments to where the action is using secondary and additional expected free energy steps, which is then going to make our drone's movement more and more precise while remaining still in a fundamentally discrete action space. Finally, due to some issues with AirSim calls, we have this whole stop and move cycle where the drone takes an action, stops to get its data, which is unnecessarily long, and then move on. We're planning on addressing this with things like a sensor cache and a couple of other code-based adjustments. And hopefully, eventually, the drone will be able to move continuously, where it's still playing discretely, but you're not going to see the drone stopping in between, which is obviously unfavorable in the real world.
Yeah, and just one example on the probabilistic side. So for a probabilistic representation of a point cloud, for example, this would forego the need of the corridor penalty, for instance, because if you have a probabilistic representative point cloud, there's literally a cloud which would prevent the drone from choosing an action that would be very close to the point cloud because it thinks, okay, there's some probability that I could be running into an obstacle here. Just an example.
And the last area is, this is directly addressing some of the challenges we talked about in our challenging environment, learning and cognitive maps. So we want to be modeling our transitions with the approach of cognitive maps. This means that we're essentially looking at expected and current suitability of regions rather than paths. We have a more true application of affordance theory. And this is also going to enable us to learn the tendencies of the environment. So for example, in the Zhangshi environment we talked about earlier, in a very dense area, you'll know that the drone is going to be tending to get stuck there, and thus, in general, those kinds of areas are unfavorable, and the drone is going to have the strategy of wanting to get out of those areas entirely, not just move to slightly safer areas. And there's a lot more concepts from cognitive maps that can help address even some of the more miscellaneous issues of our architecture. And this is going to move us towards a more true hierarchical architecture, where the drone and the agent is thinking in layers and really considering strategy with better environmental contextualization.
Thank you for listening to our presentation, and if you want more information on us and the research as it evolves, please visit our website. It'll be consistently updated as the research progresses.
All right. Next up is Bradley Alicia, Open Source Sustainability, Progress and Connections to Active Inference. This is a 53-minute recorded video. Here it goes.
Hello, my name is Bradley Alicia, and I'm going to talk to you today about our project, Open Source Sustainability. I'm going to talk about our progress over the past few years and connections to active inference. And this features a number of people's work, including myself, Jesse Parent, Morgan Huff, and GSOC scholars, which will be mentioned in the talk. We're from the Orthogonal Research and Education Lab, and we have a preprint on this work at ResearchGate. So what is open source sustainability? So open source sustainability is a way to understand how we can manage working teams and software infrastructure over long periods of time. There's been a history of trying to make software development better through different types of project management techniques. We've had things like Agile and DevOps come around to improve that process. This is held true for both industry and for academia. And we're trying to look at how to understand the key components of this longevity. So we started our project in 2022. And we've taken a number of approaches and we've developed these over time. We started in 2022 with an active inference agent-based modeling approach. And we developed that in 2022, and then we've been maintaining that since. In 2023, we worked with multi-agent reinforcement learning and a combination of reinforcement learning and agent-based modeling paradigm. In 2024, we worked with a large language model, which we are currently maintaining. And then up till this year, in 24 and 25, we worked on multi-agent reinforcement learning and reinforcement learning more generally. So we have three basic approaches, one of which is active inference. And in the talk here, I'm going to highlight a lot of work on reinforcement learning, a lot of work on active inference, and some on large language models. So the Linux Foundation has published this report called the Open Source Sustainability Ecosystem. And so they define open source sustainability as the tools, conditions, and platforms under which open source can thrive. So they talk about tools, which is licensing, workflows, and containerization. They also focus on conditions. So the conditions under which open source sustainability thrives is where we have healthy teams with trust and coordination. And then finally, they talk about platforms, which are automation techniques that enable working teams. They also pose some big questions. And so these are questions that people often encounter in practice. And there are no clear answers to these questions. A lot of projects struggle with this, and no one's ever really developed a good methodology to ensure that you do a good job, because a lot of teams are very diverse. They have, you have different types of projects, you have different aims and goals, so it's hard to really find a single set of answers. The first of these is how to push production builds in a distributed, decentralized manner. So a lot of teams in open source are working in a distributed, decentralized manner, and pushing to production is notoriously hard. It's difficult to coordinate people's efforts. It's also hard to put a lot of workflows into practice. And so this is something that, depending on the team, is easy or hard. It's relatively easy or hard. It's relatively easy or extremely hard. The second one is FOSS governance, and that is a social contract that Debian kind of proposed about 30 years ago, where they proposed a way to keep your organization relevant and grounded in the type of ethics that you want to see in the world. So a lot of open source software projects will drift from where they began, and they will decay in different ways. And we want to have a governance structure that maintains projects over the long period of time. The third point is how to maintain collaborations in software systems. So we want to maintain collaborations. We want to have healthy relationships in our teams, but we also want to be able to maintain software systems over long periods of time. And last year we had an interview with Stefan Bollman, who talked about containerization as a strategy for that, where you can build a container and run different types of programs in there, distribute it to different teams, and it makes it easy for them to implement different types. In this case, it was neuroimaging analysis. Then the fourth question is how to coordinate efforts and get things done. Very simple. Now we're going to be hitting on some of these big questions as we go along. But first I want to talk about implementations. So there have been attempts at this in the past. There have been platforms that people have tried to build, or different types of models that people have tried to build. And it's kind of hard to do because, as I said, open source projects are very heterogeneous. Some projects focus on, they use one set of tools, other projects use other sets of tools, and they have different aims and goals with their software. Some are driven by large companies, some are driven by small concerns, and others are driven by academic groups. And so they're going to have all different sorts of practices, all different sorts of goals, and their teams are going to be managed quite differently. In any case, the first implementation of this sort of way to measure open source sustainability was SourceCred. And SourceCred analyzed discourse, Discord, and GitHub activity. So they pick different tools that teams might use, and they find a way to analyze that activity. So you're dealing with producing code, you're dealing with discussions amongst colleagues, and you're dealing with other types of communications within, say, an open source community. And so this was proposed by Miyazono on the Protocol Research Labs blog in 2020. Another implementation is Git Compare, where it focuses more directly on GitHub and only GitHub. So you can, take all aspects of a project or all aspects of an open source community into account, or you can just focus on something like GitHub. And depending on how your measurements, how accurate your measurements are, how robust your measurements are, one strategy may be better than the other. So it might be better just to focus on GitHub if you don't really have a good methodology for analyzing discussions on Discord or Discourse. So Git Compare builds a model of general development activity for GitHub repos based on 5 criteria. So we're talking about GitHub repositories where a project is storing their code, they're implementing their developmental pipeline, and they're working on building software. And they want to basically know how popular this is with the open source community. And they also want to know how recent things are. And also they want to know if you can protect your assets properly. And, sometimes licenses aren't just about protecting assets. Sometimes they're about mediating conflict in the team. So they base their model on 5 criteria. There's a creation date, a license, forks, stars, and watchers. And so stars and watchers are sort of popularity mechanisms, social media type measurements. A fork is basically when I copy a project and I make a copy for myself so I can modify it, which suggests that people find your project generally useful. The license, of course, is the legal framework or the governance framework. And then creation date is going to be where it started. So you can look at the creation date. And if there haven't been updates since then, or, maybe in the last 2 years, that the project is not sustainable. So these are all things that they measure in Git compare. This is from the Git compare medium in 2018. And then another approach that was interesting that's been done is a governance surface. So a lot of times we develop these surfaces to describe all the different states of a system that we can describe, and then we explore that surface to find the transitions between states or sort of the trajectory of the project as a whole. And so this is a governance surface that was developed using an analysis of Discord with chatbots. So they analyzed Discord with chatbots, they developed this governance surface, and they described kind of, the discussion activity in that team or in that community. And this was published by Rennie in Qualitative Inquiry. So the final implementation I want to highlight here is a tool called Grimoire Lab, and it's put out by the Chaos software community. And so this is a tool that takes a number of places where you can track data in open source communities, such as GitHub, Slack, other places where teams meet up together and development happens. And so we can take these data, we can retrieve them, we can store them, we can do other types of things and enrich them with, all sorts of other analytics and charts and reports. So Grimoire Lab analyzes data in the service of being a management tool. This diagram here shows kind of how we can take data from an open source community and we can look at how well it's performing. And then we can look at those charts and graphs and improve our community. Places where it's failing, we can shore things up, we can optimize things. Now, our goal is a little bit different, and in the sense that we sort of base everything on agent-based models. And so we're not really interested in being a management tool, we're interested in scenario building. So agent-based models are famous in the social sciences for enabling scenario building, or asking what-if questions. So, we may not observe something directly in a community, but we can model a community as a simulation and then say, what if some intervention happens in the community? What if something good happens in the community? What if something bad happens in the community? What happens if you scale up the community? What does that look like? And so it gives us a sort of a scenario building tool. And so our goal is scenario building and insight, not performance optimization. Now, one of the interesting things about, say, using tools like Git or GitHub and many other project management tools, but we'll focus on Git for now, is that they introduce on individuals a certain amount of cognitive load. So cognitive load is the idea that you have too many things going on, maybe too many steps in your tasks that you need to perform, or too many things to think about at one time. And it impacts your performance. It slows you down, it confuses you, it doesn't lead to optimal outcomes. And so this is a blog post on Git and cognitive load. And this is a cartoon that kind of talks about how we use tools sometimes that are very arcane and very hard to master. And so if you can't master them, you can't really realize your goals. And so this is one of the main sticking points of sustainability, is that people can't go from idea to implementation very easily. And so, there are a lot of ways we can look at and measure cognitive load. One of those is looking at the complexity of programming environments. So we might say, for example, if we look at the complexity of programming environments, we might want to measure how long, if we have multiple long processes in our workflows, that might introduce cognitive load. If we require people to learn a multitude of tools to get their work done, that might also induce cognitive load. And then if we force people to memorize many similar or cryptic commands, we can also introduce cognitive load. So this cartoon basically spells out the problem with cognitive load in a lot of open source projects. And unfortunately, open source projects, there isn't a focus on mitigating a lot of these things. These are very common things and problems in open source projects. So this is just one example of the things we can measure and the kinds of constructs we can build looking at open source sustainability. There are a lot of things that are involved in this. So, if we think about like individuals in the team, and they're all sort of having to process a lot of information to get their work done, and they can do this in a very efficient way. They tend to stick with the project. They tend to be productive, and the project is a success. If they can't, then it's a failure. And so this is kind of, we'll feed into our active inference formulations and some of our reinforcement learning formulations as well. There's always a learning curve in any organization. You have to learn new tools, you have to learn new procedures. And that learning curve, if your learning curve is too steep, a lot of people won't bother to join the project. Sometimes project-wide compliance is important. If you have to comply with different regulations, sometimes that's a good thing, and sometimes that's an onerous thing. So this can work both ways. There's, of course, attentional resource management. Do you force people to multitask all the time, or do you have a work environment where people are doing one thing at a time? Because multitasking can be bad from the standpoint of focusing on any one set of issues. Multitasking can limit your productivity. There also has to be intrinsic motivation and reinforcement. Of course, we're going to address this directly with reinforcement learning. There's infrastructural lock-in. Oftentimes that's indirectly cognitive. That can affect your ability to get your work done. Expertise or mastery. So if you're an expert in a certain area, or if you're an expert with a certain tool, it makes it more likely that you can achieve what you want to achieve in your project. And then the coordination of goals. And the coordination of goals is I want to be able to coordinate my goals across the team. I don't want to just do things on my own and then someone else do things on their own and then combine those at the end. We want to coordinate our efforts in an active way. We want to be able to have this sort of collective cognition where we can, an environment where we can do that. So when we define our different terms here in terms of what we think about, how we think about open source projects. So to define our different terms about what we think of when we think about open source projects, we've identified three things. There's the project, their agents, and their tasks. And this diagram shows like a project leader, a maintainer, and a contributor. And those are different states of agent. So if we're thinking about this grid and we're thinking about this agent-based model, we have different classes of member of the team. We have a project leader, a contributor, a maintainer, and there are multiple types of agents. And those agents can coordinate their efforts or not. And so we're going to model it in an agent-based setting, but this relates to team members. So a project is defined as a set of tasks and agents with different competencies. So you have agents that are contributors, maintainers, project leaders. You also have tasks that are specific to contributors, specific to project leaders, specific to maintainers, specific to other types of people, maybe technical writers or something like that. When we think of agents, we think of individuals, and those agents usually have some sort of cognitive state. They also have maybe a task or an ascribed role. And agents see this division of labor in a project and have specific roles in a project, like contributors and maintainers. And then tasks are defined as units of work. Sometimes we have issues, which are just kind of single tasks that are, clearly defined, very tightly defined, to what we call in our simulations Mars Jupiter shot projects, which are these large multi-stage projects where you have to complete one part of the project before you know what the next part of the project will look like. So we have these tasks, these agents, and these projects, and now we're going to model them and measure them to some degree. We're going to create metrics, but we're going to mainly focus on simulation to see what this looks like. So again, we're going to turn to agent-based models or agent-based environments where we have, and of course in an agent-based model, you have this grid world, and on the grid world you have agents that can occupy individual cells. And those cells can be occupied by agents that have different roles, different internal states, and they interact with each other through rules. And if you have agents next to you, you can share information with them, and they create these structures across the grid that are these collectives. And so, we're going to be looking at collective behavior across the grid. We're going to be looking at individual behavior on the grid, and we're going to see how that evolves over time. So our agent is in a certain ij position. It'll produce a bunch of agents will produce a spatial distribution with specific states. So we have a red state, a blue state, and a gray state here. And so that's great. We can do that, and we can run the simulation. But then when we get our simulation results, we see that there's some patterns in here. And when you look at patterns with your eyes, sometimes you see spurious patterns. Sometimes you see patterns that are meaningful. So the problem we have is, how do we interpret macro-level emergent patterns? So that's going to be a problem that we're going to have, and we'll come back to that later. So, we want to think about other kinds of processes to model, not just agents that live on a grid world, but those agents living on a grid world do something. So ultimately, these agents are trying to solve different collective action problems. So, there are different aspects to this, but we don't want to just model collective action for the sake of modeling collective action. We want to map this to some process in open source. And so here we have branch development in Git, and we have pull requests. So we have different branches where different branches are created for different purposes by different agents, and they're all kind of pushing their work to a main branch where they're kind of taking the work from the main branch, creating their own branch, finishing their work, and then issuing a pull request back to the main branch. So this is collective action because all the agents have to coordinate their activities so that at the end, the main branch has like a coherent project, and it isn't just, everything that's smushed together and it's not workable. So, there are a bunch of things that drive collective action in this context. So the first is internal motivation. A contributor wants to work on an issue. So if a contributor doesn't want to work on an issue, they won't bother making a branch, and they certainly won't bother making a pull request. There also has to be cooperation. So sometimes agents can get together, make their own branches, and use a divide and conquer strategy to sort of address the available tasks and address what needs to be done. They coordinate their efforts through looking at these diffs, which are the differences between different branches, and addressing those accordingly, and then that leads to this finished project. So you have this sort of technological layer that allows us to make these branches, compare these diffs, and do this all in an automated fashion, which helps with the cognitive load. But it's also important to have this sort of internal motivation and this cooperative aspect of the behavior. And then, of course, there's the external motivation, which is sort of addressing a technical layer, which is that we have to make contributing to this project seamless and meaningful. So if the project is not, easy to contribute to, and it isn't really about anything, then people won't bother to do any of this. Another process we can model is the issue queue or the Kanban board. So Kanban boards are used ubiquitously in project management. Issue queues are also used to store issues, to move issues through different levels of priority from beginning to completion. And so there are a lot of things that drive this at the individual level, at the team level, and then sort of at the issue creation level itself. So individual prioritization can be characterized as what issues contributors should address first, later, and last. So when we build a Kanban board, we usually create these categories of, to do, in progress, urgent, and finished. And we have to decide as individuals where to put those issues. What's the state of our state of completion for an issue, and where do we put it? So maybe we don't want to work on certain issues at all. Maybe we find other issues to be very appealing, or maybe we take all of our issues and we move very slowly through them. Maybe we move faster, but we have to have this means of sort of addressing issues. Sometimes we procrastinate on them, and we have to have this model of moving on things so that things get completed. Then we have team prioritization. So in team prioritization, we can ask what issues are at what stage in project development. So if we have a team reviewing a Kanban board, that team will look at all the individuals and their collective prioritization techniques, and then they will just basically say, okay, this is what the state of the project is, and I'm going to give feedback to the individuals we're going to give feedback to the individuals to say what they need to do to improve these. And then issue creation is basically what is the fundamental unit of work. So all of our individuals must be in agreement on roughly the same fundamental unit of work. How big are your issues? And the team also has to be in agreement, or else you have a lot of conflict. You have a lot of fighting over, what exactly needs to be done, how much work needs to be done, and what's the priority. And a third process we can model are units of contribution over time. So this is a GitHub dependency graph for branches and forks. If you look at this, you'll see that they're different owners, and these lines sometimes they kind of join together, sometimes they branch apart, sometimes they're maintaining themselves in parallel, and these are all sort of a record of pull requests and commits within a project. And so we can look at different workflows or different sort of work processes where multiple people are contributing to different things over time and actually producing an outcome. And so we're interested in that because we're interested in knowing how maybe a certain thing like a Docker file gets passed through many different community members or contributors. It gets passed through many different contributors on its way to completion. So here we have a number of different, on this workflow network cycle, we have all these nodes, and we have a number of connections between the nodes. These 4 connections define this network cycle. So the first connection are generic changes that were contributed by 2 contributors and then merged by a third. The second is creating a Docker file, which was contributed by 1 team member and merged by another. There was another clone created at 3, and then 4 was a fork made by another contributor. So you have a number of people working on this, a number of contributors, you have a number of actions being taken, and you can analyze those as sort of getting work done and making the project, basically sustainable. Now, when we do this in terms of simulation, we have this problem of indirect measurements. That is, we're measuring these things, but we're not actually measuring things like cognitive state. We're not like putting people on a scanner to measure cognitive state. We're looking at their outputs on GitHub or their outputs on Discourse or something like that. And so we can't say for sure, or we don't really give them formal behavioral tests to look at their, say, motivations. So we don't know exactly why they're doing these things. We just know that they're doing a lot of them. So we have this problem of indirect measurements skewing our simulation output. GitHub contributions are an indirect measure of motivation. So we can say that people are motivated if they contribute to GitHub a lot. We can just make that assumption, but we don't know the details of it. Maybe they're doing it for a class project, which is motivation, but it's not the same as being like kind of motivated by the problem. And that's the problem. We don't really have a lot more information to go on than that. And so simulations based on these indirect measurements may not accurately reflect the dynamics we find in actual open source projects. We can only assume that if they're contributing a lot to GitHub, their motivation is high, and that motivation carries over across, time. So they're always highly motivated, essentially. We also have a problem with performing parameter inference on complex nonlinear models. So the problem with agent-based models, and we're going to use agent-based models as sort of like a baseline here. We're going to always be modeling our agents on agent-based modeling surfaces in frameworks. And we're going to be using things like reinforcement learning and active inference to model these cognitive states. So we have this, we're still working with agent-based models. We're just doing different things with them. We're building these hybrid models essentially. So the likelihood or probability functions for most agent-based models can rarely be evaluated in practice. So we can build likelihoods of motivation, but we don't know what the conditions are. We couldn't build like a model with conditional probabilities unless we went out and did more experimentation with people who work with open source projects. And even then, it wouldn't be complete in terms of getting data for, across a wide range of projects. So we have to keep that in mind when we're talking about these models, is that they're incomplete in terms of their ability to characterize every behavioral state. So these are our Google Summer of Code scholars. So this project was built around Google Summer of Code, getting students over the summer, having them produce. We've done this over the last 4 seasons, from 2022 to 2025. And we have had 6 people in our team who have come in through this route, and each of them have contributed something different. So Brian McCorkle, his picture's right there on the top, he worked on active inference and collective active intelligence, thinking about active inference and collective behavior. Himanshu Shogul, who's next to him there, he worked on multi-agent reinforcement learning and building Q-learning / agent-based models as hybrid models. So he was interested in agent-based Q-learning. R.V. Rajagopalan implemented agent-based modeling in MISA, which is a Python package which allows us to do more than, say, working with something like NetLogo. Just having that framework where we can actually build more sophisticated tools. Shubham Soni did some more work on multi-agent reinforcement learning in this Q-learning agent-based hybrid model. Sarah Bastawala, who's right there next to her name, developed the LLAM OSC, which is large language models with agent-based models. So these are large language models that create sort of tasks for agents in an agent-based model. And the tasks, of course, are conversational and sort of text-based. So if you want to create a bunch of issues for your agents, you create them with the large language model. You create conversations with the large language model, and then the agents work from that. So it's very interesting work, very exciting work. And then Vidi Rodhira, she worked on reinforcement learning, but a different sort of approach to it than the multi-agent approach. She worked on what they call SARSA, which is a model of inputs and outputs, and then merging that with agent-based models. So it was a hybrid model. These students used a number of tools to implement this stuff. For the multi-agent reinforcement learning at the upper left, they use temporal difference learning, Q-learning, and SARSA. We'll get into those details later. Some of our students also used MISA / NetLogo. This is at the upper right. So MISA is implemented directly in Python. NetLogo is a classic package that has a lot of prepackaged models that you can implement, and then you can build from there. So this offers a lot of flexibility for implementing the guts of the agent-based model. LangChain, of course, is a large language modeling tool or toolbox, and that's at the lower left. And then the lower right is PyMDP, which is, of course, the toolbox for active inference. So let's talk about the OSDC first. This is a model of collective active intelligence. So this is our active inference approach to open source sustainability. And in this case, we're characterizing the activity of our computational agents using a Markov decision process in Python, and that's our PyMDP, or MDP in Python. This model implements a multi-arm bandit, so it focuses on explore-exploit problems. And as we'll see, the SARSA approach also explores this sort of collective behavior as a multi-arm bandit problem. basically a multi-armed bandit. The name of the multi-armed bandit comes from when people pull the lever of a slot machine. So you're like priming this stochastic process, and you'll have like in front of you, if you've ever gone to a casino, you'll see people sometimes put like 5 slot machines at once, and they'll pull the arms down and then see what they get. That's what you're doing in a multi-armed bandit. And you're trying to figure out whether you should explore a space or exploit a space. So if you think about that in terms of issues, should you explore an issue deeply, or should you explore more issues more in a more shallow way? We implement this in different ways so that we can look at that as a sort of a factor for driving open source project behavior. The second point is building a statistical description of the mind. So this, of course, is the internal components or the internal model of each agent. So we want to build a statistical description of that mind. We want to give it beliefs, and we want to have each agent minimize its own free energy. And so this is something that, of course, we also want the agents to sort of be able to figure out what other agents are thinking so that they can match their beliefs and minimize their free energy together. So this is kind of where we're going with this in terms of the collective part of it. And then, of course, when we reduce our error, it reinforces causal relationships that are necessary to complete the project. So getting the agents to see what the causal relationships are between different parts of the project. If we can reduce their inferential error, then we can get all the agents to move in the same direction. So this was implemented using Interactively. So this is the link to Interactively. It was used to do 2 things. Number 1 is to implement decision problems in a single agent, as we said. So each of these agents have some decision process going on inside of them. And then 2 is to implement a theory of mind to infer the state of neighboring agents. So the agent on the left is trying to characterize the state of the agent on the right, because the agent on the left doesn't know what the agent on the right is thinking. And if they're both thinking the same thing, they're able to maximize utility in the same way, then they'll be able to cooperate better and do things like divide and conquer. So this is where you have this agent is asking this other agent, is this what you're thinking? And they say yes. So that's the way this project worked. And it has ties to the reinforcement learning that we'll talk about next. So in the context of an agent-based model, this is an agent-based grid again. The activity of one agent influences activities of their neighbors. This is typical of an agent-based model. So we expect those internal states to spread as they're able to infer each other's state, and we get these blocks where all the agents are doing the same thing. But we also get the spatial distribution of states. And because this is a spatial array, we have things like adjacency and distance that we can characterize the sort of spread of these ideas. So, sometimes you'll have a block of contributors thinking one way and another block thinking another way. It's either thinking the same way about a problem or having sort of the same level of motivation or whatever. If theory of mind is achieved, 2 neighboring cells should co-activate. So that's where they share covariance in their activity. And these are, pairs where you can see that they're kind of activated together. Another thing that Brian McCorkle worked on the active inference part. So another thing Brian McCorkle was interested in, and it's kind of on the cutting room floor now, but I bring it up because it really does have relevance to sort of these internal states in the mind. And that is Mick Ashby's ethical regulator. So Mick Ashby is the grandson of W.R. Ashby, who came up with the Evergood regulator theorem in cybernetics. And Mick has been working on this ethical regulator and super ethical systems idea. He published a paper in 2020 on this. And he has this whole model of how we can encourage ethical behaviors. And this goes well beyond active inference. But it shows you how we can take a simple active inference model and kind of think more deeply about things like ethics in projects. So do people act ethically in the project? Sometimes projects get blown up because people act unethically. They steal credit for ideas. They cut other people out of the project, or they're not honest about what they're doing. or sometimes they try to make money off of an open source project when the license explicitly states otherwise. So we want to encourage ethical behaviors, and we want to make sure that those are all there in place. And we coordinate our division of labor and resources amongst contributors so that everyone's acting ethically. And as a model of cooperation, we have to take into account fairness and efficiency. So when we talk about regulation, then if we look at our agent-based model, we have these different types of regulatory behaviors. So if one agent influences another, we can have the zeroth order behavior. If agents influence each other and they have this theory of mind, there's a first order behavior. And if multiple agents are influencing each other collectively, that's a second order behavior. So there's also the sustainability auditing tool, which was worked on after the project in 2022. This was implemented in NetLogo Web, so this is an agent-based model there. And this was kind of developed out of the active inference approach. And so in this case, we're modeling two variables. We're modeling churn and we're modeling maximum sensory probability. So churn, of course, is the turnover in the number of agents. High churn suggests that the community has a low degree of cooperation, a low degree of theory of mind. And then maximum sensory probability, remember we need to have some sensory information to make active inference work. And that is the probability of a given signal from other agents or the environment. So we have to have a signal from other agents, a signal from the environment, and then that's what activates sort of the agent's cognitive state. So this is the agent-based model for our multi-agent reinforcement learning approach. This is modeled in NetLogo. We have our agents as stick figures, and they have multi-agent reinforcement learning, driving their behavior, their internal state. They also have these squares, which are the resources of the project. And we can populate this with a large or a small number of contributors. We can then divide them up into categories, new maintainers, contributors, and then have solved issues and unsolved issues. And the idea is that they solve all the issues to maintain a sustainable project. And then we have these different issue sizes. So Earthshot, Moonshot, and Mars-Jupiter shot. These are just different sizes of issues. Earthshot issues being single issues, Moonshot issues being a collection of issues that are interdependent, and Mars-Jupiter shot issues that are things that are kind of like multiple different sub-projects, basically. So a little bit about multi-agent reinforcement learning. This is a simulation where we use multi-agent reinforcement learning. It's a population of agents acting on a common grid world. The agent is motivated by its own rewards. Its actions advance its own interests. So in individual terms, it's self-motivated. But then sometimes, of course, those agents have to interact with their neighbors, with other agents in the population. And those interests can either be coordinated or mutually opposed. So we can see here that we have these two different colored agent populations, and they're kind of mixing over time. We can model different scales of project size using multi-agent reinforcement learning. So this shows the prevalence of Earthshot issues, Moonshot issues, Mars-Jupiter shot issues, and accepted pull requests over time. And you can see that they kind of increase with time. And this is just one run of the simulation. So again, our Earthshot issues are single issues. Our Moonshot issues are issues that can be broken down to multiple single issues. And then our Mars-Jupiter shot is a problem that can't be broken down directly into multiple issues, but need different sub-projects to be completed before the next sub-project. And as such, they're sort of modular. So we use that to look at multi-agent reinforcement learning. This is where we also used multi-agent reinforcement learning with Q-learning, but also SustainHub, which is this reinforcement learning with a SARSA model. So SARSA is state action, reward, state action. So it describes you monitor the state, you take an action, you get a reward, you monitor the state, you take an action. And so that's kind of the difference. We have Q-learning for multi-agent and the SARSA for the SustainHub or the single reinforcement learning. And so this is another simulation. This, I think, is also from Shubham, where he's simulating Earth issues, Moon issues, Mars issues, and then accepted pull requests. And the accepted pull requests are always sparser than the other issues being solved. So that's, it's kind of typical because you're combining all your issues into a single pull request. So this is kind of a way to monitor or at least model things going on in a community. The question is it something that is sustainable or not? And that's a little bit harder to determine. So let's walk through some of these methods for reinforcement learning to see maybe how they compare with active inference. So we start with Q-learning. So for any Markov decision process, we identify an optimal action selection policy. So what we want to do with that action selection policy is maximize the expected value of the total reward. Okay, so then this determines the quality of a given policy. An action A sub t with respect to state S sub t provided a learning rate of alpha. So we have this equation down here where we have these different components. We have alpha times Q, where we're evaluating the action and the state, the quality of each action and state that evaluates the current action selection value. We add that to this estimate of optimal future values, or the state of highest quality. And so we're looking for the maximum quality. And then that's our kind of the direction we're going in Q-learning. We're trying to find that maximum future value, the maximum quality of a given set of policies. Now, the multi-arm bandit is also used then in reinforcement learning, like we saw with active inference. It's used for task allocation, role matching given prior performance. It encourages specialization while allowing for flexibility. And it utilizes what we call on-policy temporal difference learning, which we'll get into next. And so it's important to recall the different community member types: maintainer, contributor, innovator, knowledge curator. And we can use this to think about how to allocate different tasks to these different classes of contributor, or these different classes of project member. So temporal difference learning can be stated as a state value function of a finite state Markov decision process under a policy pi. V sub pi is equal to the state value function of the Markov decision process with states, rewards, and a discount rate importance, which states the importance of future rewards. So we have, instead of our learning rate, we have a discount rate. And then we estimate v pi s, which is the function for the state value. And we evaluate this policy pi. We obtain the reward r, and we update our value function. Now, some of the metrics that were created in the reinforcement learning work, and this was done by V.D. Rahira, she developed 5 different metrics that work in this context. So the first is the harmony index. So remember, I said there are different things we want to measure, and then there are different things that we can sort of have as like an output. So the first is the harmony index. This captures workload balance and task success rate. This basically measures how well balanced workloads are, how much cognitive load there is for each agent, and then the success of agents at those tasks. Then there's the resilience quotient, which measures adaptability during disruptions, such as dropouts and workload spikes. It means basically how resilient are you to different types of disruptions in your work, in the project. There's reassignment overhead, which tracks inefficiency caused by reassigning tasks. There's an initial density of agents. So basically, it's where if you have a dense setting of agents to start with, it's going to give you a very different result than a very small number of agents. And we can use that to sort of normalize a lot of the heterogeneity in open source projects. And then the contributor maintainer vision. So if we don't have a good vision, agents won't know if there's anything for them to do. But if the vision is there, then at least they have in their mind sort of a mental model that they have something to do. And so they go to find specific tasks to do, to solve specific issues. The next thing I want to talk about is how large language models were used. So This was Sara Bastawala, of course. This is Llama OSC. This is an open source large language model based on the Llama platform, and it's used to generate project tasks and issues. And so she basically developed this large language model, agent-based model hybrid platform, or this hybrid model. And that gives us a model of how to act upon tasks and project structure. So you would generate like all these different issues using a large language model. You generate conversations, and then the agents would know how to act from that and give the project structure. The workflow is in LangChain that's in Python. And this allows for large language models to be used as a reasoning engine where you can have sequences of actions where agents decide what tools to use and what order to use them in. So, and in this work, she had like two basic models of open source communities. So instead of thinking them as very heterogeneous structures or thinking of them as idealized structures, she thought of them as either a benevolent dictator model or a meritocratic model. And so in the benevolent dictator model, which is characterized by Linux, in the Linux kernel, you have some single person who drives the project forward with their deep technical skills. So Linus Torvalds is the benevolent dictator in the Linux example. And then the meritocratic example is indicative of the Apache Foundation, where anyone can engage at any level that they want. And so there's no leader, there's no dictator. It's just kind of like people do what they can in the project. I want to get into the way we're thinking about integrating a lot of these models together. We want to bring them together in the next phase of this project. So, one of the things we need to understand are the dynamics, or what does a team look like over the course of a project. So sometimes, people leave projects, sometimes people join projects. We have these sort of Locke-Volterra dynamics in our agent-based model. And that's, kind of an interesting thing because none of those are described by any of the models that we've talked about. So this is a point for future work. We also know that like some of these dynamics, because you get a lot of people leaving, a lot of people joining, a lot of flux and churn, that it can create vulnerabilities as well as opportunities. And so if we want to know how to sort of build a model that can help us understand maybe what those opportunities are, those vulnerabilities are, there are some ways forward. So one way is to build these sort of what we call metabrain models, where you take different models and you put them together, different layers of different types of representations, put them together as a structure that sort of, communicates selectively between the models, but processes different types of information. So in this case, we think about the large language model as handling semantically defined tasks. Active inference is handling sort of the internal brain state of an agent. And then the multi-agent reinforcement learning as the motivational structure, which means that, you have this brain state and motivational structure working together on tasks that are semantically defined. And then maybe an agent-based model as sort of the collective driver of collective behavior. So you have this agent-based model sort of coordinating all these different brains composed of large language models, multi-agent reinforcement learning, and active inference models. So I want to finish with sort of a thought from Jesse Parent, and he's another person in our lab who's contributed to this work. And he's been thinking a lot about project management and a lot about how we often create tools that don't go anywhere, or we have like initiatives that kind of die because no one finds them relevant. So he says sustainability translates to problems in academic communities. Sometimes if you go to an academic community, you find that someone earns like a grant for tool building, so they get funding for tool building. They build these great tools, and then the funding runs out. And so they have this open source tool that they put out in the world. The funding runs out, and it becomes an unmaintained tool, eventually to die a premature death. So that's one path that's suboptimal, I think, from the standpoint of open source sustainability, where you get money to build something, you build it, and then it dies. The other example that he gives is that someone builds a tool, And because it's not really relevant to anything, the tool is ignored and not maintained. And so then that's bad. But it gets worse because then someone else builds a similar tool. And that dies because it's ignored and not maintained. So you end up with this graveyard of tools that are all maybe pretty decent, but because no one's finding them relevant and no one's putting the money into maintenance, people keep reinventing the wheel and then the wheel breaks apart. So that's not good. So, Jesse makes this observation that academic communities more generally will often build out infrastructure, which goes nowhere and is disconnected from real world impact. So that's something to think about if we're thinking about the Active Inference Institute or our own lab or other institutions where people build infrastructure, it goes nowhere, or it's not connected to the real world in relevant ways. And sometimes you just can't, you can't avoid it because you don't necessarily know what people will find relevant. But that's part of sustainability that we haven't addressed and maybe is sort of the secret sauce in this whole equation. So thank you for your attention.
All right. Next up is going to be Andrea Heot's Kaleidoscopic Cognition, How the Brain Can be Modeled and Use Modeling Without Having a Model. It is a 52-minute video. Here we go.
Good afternoon, everyone. Today, I want to share a paper with you, Radical Embodied Relation at Any Scale, from Remembering to Navigating. My name is Andrea Hyatt, and this is for the Active Inference Institute Symposium for 2025. So this is a bit of a radical embodied understanding of mind, and it works at any scale, as the paper says. So it's supposed to expand some of our fundamental assumptions about brains, memories, minds, and bodily movement and how all those relate. So the title of this talk is Kaleidoscopic Cognition, How the Brain Can be Modeled and Use Modeling Without Having a Model. I know that sounds paradoxical. And if you know me, you know I like paradoxes. Holding paradox is sort of the point of a lot of this work, but that title might seem impossible, actually. So how can the brain model without having models? And how can we use representations without them being stored somewhere? These questions have been really important in neuroscience and philosophy. Some might even say they've been plaguing neuroscience and philosophy of mind lately. Like we just can't move past them. But there's recent research on the hippocampus, which is the part of the brain that I studied, little seahorse-shaped structure on both sides of your head in both lobes. And it's forcing us to rethink some basic assumptions about a lot of these words that I've already mentioned. So what we're discovering is that the brain, or I would rather actually talk about the central nervous system and the bodily sensory movement of it all, but let's just say the brain, doesn't work like a computer with shared, stored files. Instead, it operates more like a kaleidoscope. And I know that might sound crazy, but actually, it's a very helpful, strange new vision that we kind of need right now. And that it feels strange is probably a good thing. So it's this idea of creating shifting patterns through different but direct refraction of experience. So if you think of the encounter and then the body and then whatever that encounter is becoming as part of the body and sort of going back into the encounter as, then you can think of it more as something prismatic or kaleidoscopic. So this framework is coming from neuroscience, at least as I read certain studies and as I've been part of certain areas of that field, and especially grid cells, place cells, these kinds of things, which are in the hippocampus. And I think it has profound implications for how we understand these words that we've been taking for granted, like memory, thinking, but also navigation and everything that we've ever thought about as cognition, not only in humans, but when we try to understand this activity that unites us across different life forms. I'm going to be talking about the hippocampus as a kaleidoscopic function, a way of trying to visualize some of this new research, which is moving us beyond either or patterns that we assume and that I think we're all sort of stuck in at the moment in brain research, even though we say we're not. But I want to push us a little bit towards this kaleidoscopic or prismatic idea of cognition. And hopefully that'll help us move beyond these representation wars and ways of talking that have sort of paralyzed us in cognitive science. The idea is to synthesize insights from 4 key papers that, when read together, will reveal something pretty extraordinary about cognition. And so these are the 4 papers. And the first one is my paper, the one that's kind of framing this, and I guess the sort of foundational text for it. And in there, I argue that recent hippocampal research forces us or allows us to reconceive what a neural representation is and to think of it as a communicative assessment, rather than something stored or findable or some sort of hieroglyph in the brain. And I introduced the concept of waymaking, which is just a way of talking about this process that we call cognition or this process that we call locomotion, but on the same track. There's also a brand new Nature neuroscience paper by Penn and colleagues, which came out around the same time, which talks about, well, it's called path integration in the hippocampus by shifting reference frames. And I really see this as just crucial empirical work and just great timing that it comes out now, because it has a lot to do with what I'm trying to discuss here. And it's showing us that grid cells don't maintain stable patterns, but are constantly shifting between reference frames, even though there is a stability. So there's a paradox built into this, but it gives us a good way to understand this notion of kaleidoscopic modeling that I'm trying to introduce here. And then we have the Lenz and Clark and Friston paper from 2017. Sorry if I said somebody's name wrong there. The active inference approach to ecological perception, because I think there's a lot of ideas in there that fit very well with this. And also just the mathematical and theoretical framework needs to be built up for how we might do this. And I think active inference is probably, and especially also Bayesian ideas in machine learning and so on, have already started figuring out ways to maybe think about layered mathematics in the way that I'm talking about here. But also just the ecological side of it is very fitting, that organisms engage in modeling behaviors without storing models. And of course, sometimes we slip up and say models are in the brain, but if you really look at what is actually being said, it's not that the models are in the brain stored somewhere, it's that the whole body is modeling. This last paper too, which inspired my first paper, and it's from Jacob Belmond and the Doller Lab, which is where I worked at the Max Planck Institute. It's called Navigating Cognition, Spatial Codes for Human Thinking. And it shows us that the mechanics we use for physical navigation are the same ones we use for abstract thought, even though thinking and geographical navigating can't be resolved as like the same thing. We can use the same metrics to understand them, but those metrics cannot be based on these either assumptions that, you know, like we've been sort of using, whether it's like global and local or even mental and physical, like conceptual space, physical space, memory, navigation. Those ways of talking and our use of the word representation as we're talking about them in cognitive neuroscience has to shift. So all these papers together point towards a unified understanding of cognition as kaleidoscopic, or at least as constellatory is another word I use, demanding we find ways to model it kaleidoscopically rather than binary, and these binary assumptions that frame so much of the way we talk about all of these topics, the way we even use the words, and the way we model them, even if we don't realize that's happening. So by introducing this kaleidoscopic cognition, I'm trying to push us a bit into a dynamic, immediate, irreducible understanding of what we mean by representation, which is actually a communication. So we also understand that we're going to do this through communicating about the patterns of regularity, and that this communication isn't findable, but it is representational. So that's a little tricky. This holding paradox idea is really good, and also this kaleidoscope where you have similar patterns, but based on the input of the light, you can even think of it as prismatic, I guess. You're going to get different results. but those will all be tied to similar patterns. So again, I've mentioned paradox quite a few times, and the main paradox is that motivates this framework is representations without representations, models without models, or modeling without models, or representing without representations, maybe is a better way to say it. But traditional neuroscience always assumes that cognition requires stored models, internal representations that the brain builds and maintains. So when you remember something from your childhood home, there must be some neural structure that is appearing in your brain that represents that home, right? So when you navigate through a city, you have some kind of map in your head. This is just the way we talk about it. Most people, of course, don't actually think you can, pull a little map out of your brain or actually find some kind of structure in the brain that's going to represent home in some kind of one-to-one way. However, we still talk about it that way in our papers, and we still assume this language. So the reality is that organisms are navigating these complex environments without anything that looks like explicit stored representations. And in fact, there's so much going on all the time that any of our actual experiments is just looking at a tiny bit of it. So if we find some brain activity that corresponds with a particular memory that we have, that's actually just one little snapshot in a way of something that we were directly looking for. And this is still on this flatland kind of way of thinking about what we're doing in these experiments, and also what the body is doing in relation to the brain, the environment, and all these ongoing movements that we are. So animals find their way home, they recognize patterns, they make predictions, including humans, of course. And yet, when we observe them and we watch the activity of, rats who've been so helpful for us, for example, in neuroscience, then the only way we can really communicate about what's happening there is through creating these representations, images, or, that we record the cell activity and then we see pictures of it. And all of that is representational, but it's not inside the rat. It's us creating things to understand this ongoing movement. And that gives us a visual, a video, a screen image, whatever. And those are the representations, and those are the communications. And that is a communication. I mean, the screenshot or the recording is meaningless except as communication. And it's important. We're doing that, obviously, in order to better understand this whole process and ourselves. And it's a very real thing, but it's not findable somewhere. So the hippocampus is really central to making more scientific, rigorous sense of what I just said, and getting over this assumption and use of language that's binary and that does talk about representations as if they're inside brains rather than as if there are communications towards understanding brains. So for a long time, we actually literally looked for engrams in the brain, stored memories, and that was the hippocampus was like, the sort of heart of where all that came in the 50s, looking for engrams and memories because of HM and so on. And then in the 70s, we started thinking of the same area of the brain as the brain's GPS, because John O'Keefe found cells there that fired in relation to what the animal was moving through. So, you got place cells and grid cells and things like this. But this recent research is even showing us that actually these cells don't maintain stable patterns. They're always shifting, remapping, re-anchoring. We don't have like a representation in the brain that corresponds to something outside. Instead, we have this ongoing communication, this process, this something like light coming into a prism and being refracted. That's where this kaleidoscopic comes from, that shifts as the encounter takes place. So all of these cells are shifting, remapping, re-anchoring as the encounter is changing. Just as if light comes into a prism, it's going to change in different ways without any kind of, stopping and starting there. Even though when we study it, we have to look at it that way. So this is where this idea of kaleidoscopic cognition comes in, and it does sound fantastical, maybe psychedelic, but it's actually a really accurate way to begin to envision this. And that it feels strange and even hard is actually part of that. Because what's more like the vision, and again, we're talking a bit in metaphors here, but it's more like something is refracting between and as the encounter and the organism, which includes this whole nervous system. And that is the guiding action. That is the perception in action. And obviously, this is really hard to talk about, but That's what I'm trying to do here. I think we have to find ways to sound strange, be strange, and move towards finding other ways to really understand what's happening here. So we create recordings and photos and videos and representations to understand this. Those are real and communicative, but how could we create more kaleidoscopic ones? How can we begin to use our technology in ways that are more like this process so that we get used to thinking like this instead of creating things that are still stuck in this binary sense of as if we've taken a picture of some kind of whole thing that is mental, that is a memory. So before we get to that, let me just talk about this one question about representation, which I've brought up, but how can the brain have representations and not have them at the same time? How do we hold this paradox without falling into something like computationalism or just total relativism, which is, always the trap here. So that's where this hippocampus paper comes in, which you can find easily and read. And it's arguing that representations are communicative acts, that they're ways we assess and communicate about these unbroken intimacies, not things we like find stored in brains. And I think that's something that's pretty obvious in neuroscience, but we don't talk about it as if it is. And that is a very big obstacle, actually. And of course, there's been tons of representation debates. I mean, we've really wasted, or maybe not wasted, but so much energy and time has gone into getting stuck and going round and round in loops over this idea. Even with active inference, I think we all know this idea of talking about models is in the head becomes a trap, and it's time to get out of it. So that's why I'm not in this paper, but in this presentation, presenting this idea of kaleidoscopic or constellatory cognition to kind of just try to pop us out of that way of positioning ourselves in cognitive neuroscience and in the way that we do our models. So we can understand these immediacies like are refracting differently according to the position from which they're measured. And they're not in the thing that's being measured. So weather maps are a really simple, good example. We create a weather map. It represents weather patterns, but the map doesn't contain the weather, even though it's tricky how we confuse those things with what weather is. But, there is no like stop and start to a storm in the sense of you can just pluck it out of all the rest of the ongoing atmosphere or something like that. It's and we need and create these representations of things like that so that we can communicate about them, so that we know, okay, a big hurricane is coming and we need to evacuate or whatever. These are really important representations that we create. But the map is the communicative tool that we use to understand and predict those atmospheric dynamics. The dynamics, of course, they're dynamic. They're ongoing. They're unlocatable. You don't find partly cloudy somewhere. You don't find 70 degrees somewhere. Those are things those are representations. And that's the same thing that we're talking about when we're looking at brains. It's something like 70 degrees when we're talking about a representation in the brain of memory or anything else. So that process that we call weather refracts differently from every position on the planet too. We could think about that and how, depending on where you are, you're going to see that refraction differently. It's going to be assessed differently, even though, of course, it's real what is being assessed, and it's also ongoing. And also your assessment of it on one particular day from one particular position is going to be different than someone else from another day. And that doesn't mean any of it's less real. And in fact, it'll still probably mean there's a whole lot of regularities that are shared. What you're calling a storm and what they're calling a storm will have a lot of overlap, but it won't be the same thing. And it won't be something that we, have found and then move on from. So neural representations work that way too. When we look at an fMRI image or we record neurons, we're not seeing stored memories or cognitive maps inside the brain. We're creating representations, measurements, assessments that help us communicate about this ongoing central nervous system, bodily, environmental dynamic, which is pretty wonderful actually, and which we really do want to understand. And that's why what we're doing is so important in all these fields. But the hippocampal literature shows us that cognition and navigation, for example, which have kind of been fit into these different sides of a binary of mental and physical, for example, just to kind of caricature it a little bit. We've assumed for a long time that those needed to be reconciled somehow, that they were somehow different things, and how could the same part of the brain be doing them? But recently we've started to understand, okay, they're just like refractions of the same process. At least that's how I'm putting it here. They're different assessments of this embodied waymaking that is happening all the time. And depending what we're looking for or where we're standing or what day it is, it's going to be a little bit different. But also there are going to be regularities that we can that remain, that help us understand it better if we communicate about it through representations. So when you remember a past event, you're kind of moving through or navigating conceptual space. You could think of it like that. You're using the same mechanisms, right, to move through that sort of space that happens when you're moving through geographical space, but those aren't the same thing. It's just that, there's similar regularities there in terms of what is happening. So I use this word waymaking, which comes from Taoist philosophy, to capture how that cognition and locomotion can be continuous, can be the same process, even though when we're talking about something like remembering our childhood and when we're talking about something like walking to the park, we're talking about different things. And there's no need to try to resolve those. The same way we wouldn't try to resolve wavelengths, that have been refracted from the same light source or the same, we could think of it somehow as multisensory prisms if we can. But, we can't measure and find that in some absolute sense that there is a memory or there is a little diagram in the head that's going to be found every time we go to the grocery store. So anyway, the hippocampus doesn't store maps. It's operating kaleidoscopically. It's refracting sensory encounter into bodily action. At least that's the kind of wild idea I'm throwing in on this presentation. I haven't tried to put it in a paper, of course, but at least not yet. But I do think we make these maps, these representations, to try to understand what is multi-layered, multi-dimensional, refracted in our measurements of it, even if in itself it's not. So just, thinking of it like that can help us kind of avoid some of these traps of arguing about pure computationalism versus pure relativism, or